Let us start the chapter of fluid dynamics. This chapter of fluid dynamics is going to have two parts to it. The first part of fluid dynamics deals with the concept of energy equation. The second part of fluid dynamics deals with the concept of momentum equation. So I can mention over here energy equation and applications. And the second chapter deals with momentum equation so let us say momentum equation and applications. Now both these chapters, energy equation and momentum equation, they belong to the application of Newton's second law. Newton's second law. Newton's second. Now let us see what we study in energy equation and applications. In this chapter of energy equation and application, we will first of all start with the concept of Bernoulli equation. Bernoulli's equation. After having studied Bernoulli equation, we are going to study the various limitations and assumptions made in Bernoulli equation. So let us say, after studying this thing, we have limitations and assumptions in Bernoulli equation. Assumptions in Bernoulli equation. After having studied this thing, we are further going to see the concept of power or the equation of power used in Bernoulli equation. After studying this thing comes the next part of this chapter, and that part is application. Now in this application of Bernoulli equation, we are going to start with the concept of velocity measurement. After velocity measurement, we'll be looking forward at discharge measurement. And finally, we'll be seeing one more concept known as free liquid jet. Free liquid jet. This completes the concept of applications of Bernoulli equation. After seeing Bernoulli equation comes the final part, and this part is regarding the concept of vortex motion. So third part over here is vortex motion. Under vortex motion, we'll be classifying vortex motion, or let us say types of vortex motion. After seeing types of vortex motion, we're looking at equation of pressure equation of pressure in vortex motion. And finally, we'll be ending with some standard results. Standard results. Standard results. This completes the chapter of energy equation and applications. Let us now see what is this Bernoulli equation. To understand Bernoulli equation, what we'll do is we'll first derive it and then we'll write the statement for Bernoulli equation. So let us say if I want to derive Bernoulli equation, how do I move forward? Let us see Bernoulli equation. Now you see, we know according to Newton's second law that summation of force along a particular direction has to be equal to mass times acceleration along a particular direction. Let us say over here, this S stands for, S over here stands for streamline direction. Streamline direction. S over here stands for streamline direction. Now, we have to look at what are the various forces that can act on a fluid element along a particular streamline. Let us see. If you imagine that this is a particular streamline, and on this streamline you have a fluid element over here. Let us say this is a fluid element we have over here. This is a fluid element. Now this fluid element is going to experience what all forces? The first force it is going to experience is by the virtue of gravity. That is the weight of this fluid element. So let us first of all write down the first force we are having over here is Fg, where Fg stands for gravitational force. Gravitational force. Apart from gravitational force, what forces are there? I see that there is going to be a pair of forces over here, and these forces are the pressure forces acting on this fluid element. So second force we have is, let us say, Fp, where Fp stands for pressure force. Pressure force. Next, apart from these forces, you'll observe that due to viscosity there is going to be some shearing nature taking place. Let us say there is some shearing force over here. So third force we have over here is Fv, where V stands for viscous shear force. Let me just write it as viscous force. Now these three forces are extremely strong forces. Apart from these three forces, there are three more forces acting. Fourth force acting over here, let us say, is turbulent force, Ft. Turbulent force. Then you are having extremely weak forces, which are surface tension force. Surface tension force. Surface tension force. And finally you have compressible forces. Fc, let us say, compressible forces. incompressible forces. These are the various forces that can act on a fluid element. Now, if I go by Newton's second law, I would have to write over here that Fg plus Fp plus Fv plus Ft, that is turbulent force, plus Fs along with Fc along a particular streamline has to be equal to mass times acceleration along streamline. This is a perfect equation we have. If we solve this equation and get a general equation, then that would help us understand the energy equation of a fluid element. But the problem is, solving this and getting a general equation is extremely difficult. For that purpose, what we do is we neglect or ignore some of these terms because they are relatively very weak. First, we start with assuming that these two forces over here are extremely weak. If we neglect these two forces, our equation now simplifies to Fg plus Fp plus Fv along with Ft along a particular streamline has to be equal to mass times acceleration along the streamline. This equation we are going to call as Reynolds equation. It is called as Reynolds equation. Now again, solving a Reynolds equation and getting a general equation out of it is very difficult. So we make another assumption now. This time we neglect Ft over here. Please observe, when I'm neglecting these forces, I'm starting from the later half. That is the last part over here. Because those forces are weak. I told you previously that these initial forces are extremely small. Neglecting them is very unreasonable. Therefore, we are starting from the latter forces over here. Once I neglect this Ft, the equation now simplifies to Fg plus Fp plus Fv all along the streamline is equal to mass times acceleration along the streamline. This equation is a very famous equation in the subject of fluid mechanics known as Navier-Stokes equation. It is known as Navier-Stokes equation, commonly referred to as NS equation. Again, the problem is solving this and getting a general solution is very difficult. So we make an assumption, and this assumption is, you can say, relatively an unreasonable assumption, or it is not a very good assumption. What we do over here is we neglect Fv. The moment we neglect Fv, what happens is you're eliminating the real nature in a flow. Once you eliminate the real nature in a flow, whatever equation you're going to write now should be valid only for ideal flow. So now the equation comes down to Fg plus Fp all along the streamline is equal to mass times acceleration along streamline. This equation over here is known as Euler's equation. Euler's equation. Now what we are going to do is we are going to apply Euler's equation on a differential fluid element, and from there we are going to develop a general solution. Let us see how to apply Euler's equation on a differential fluid element. You see over here I am having gravity force and pressure force. Only two forces are required. Let us start. Let us say I have over here a streamline. This is a particular streamline I'm having, and on this streamline I'm choosing a fluid element over here. A fluid element. This is a fluid element, extremely small. Let us define the geometry of this fluid element. Let us say the cross-section area over here, the cross section area of this fluid element, let us say, is equal to dA. The cross section area is dA. The length over here is equal to ds. The length is equal to ds. If the cross section area is dA and the length is ds, I can mention over here that the volume of this fluid element I have chosen is equal to dA times ds. Next thing, apart from these two things for geometry, I also show that there is a very fundamental force, that is a gravity force going down. So right now I'm talking about this Fg over here. So let us say this, since it is a very small fluid element, I'm saying the weight over here is dW. Next thing, I have to mention about the pressure forces. So let us say over here I'm having some pressure force. This pressure force is equal to P times the cross section area, that is dA. Then I have a pressure force over here. I have a pressure force over here. Now this pressure force is supposed to be equal to P plus, now some extra term is supposed to come in. So let us say dou P by dou S times ds. This is the additional force I'm having, dou P by dou S times ds, whole multiplied to dA. Whole multiplied to dA. Let me further say that the angle made by the streamline along with the vertical is equal to theta. So I hope you are understanding the geometry of whatever I've drawn over here. Now, what I do is, for my assistance, I will take a triangle over here. I'll take a triangle over here. Let us say this is dz over here and this is ds over here. ds is this length, dz is the vertical I'm having, and this angle is theta. If I mention cos theta over here, the value of cos theta would be equal to how much? It should be equal to adjacent upon hypotenuse. Therefore, dz upon ds. This is the value of cos theta. After having taken all these things, I am now going to write down the equation of Euler. I can now say, according to Euler's equation, so let me mention over here, by Euler's equation, now gravity force along streamline is going to be, let us say, for the sake of easiness, let us say this direction over here is a negative direction along streamline. So this is negative. So I can write over here, gravity force along streamline is minus dW times cos theta. Fine. I'm done with the gravity force. Now the pressure forces, I can say plus P times dA, and this is negative, therefore minus P plus dou P upon dou S times ds whole times dA. These are the forces, must be equal to mass times acceleration, therefore must be equal to differential mass times acceleration along the streamline. This is the equation I'm having. See that plus P times dA and minus P times dA can be cancelled off. If they get cancelled off, I can now write down minus of, dW is gamma times volume, differential volume, multiplied to cos theta I know is equal to dz upon ds. Dz upon ds. This is this value minus dou p upon dou s times ds times dA. Fine. Dou p upon dou s times ds times dA is equal to differential mass over here is equal to how much? It is equal to density times volume, that is differential volume, multiplied to acceleration along the streamline. This is the equation I'm having. Now recall the concept of acceleration along streamline from kinematics chapter. In kinematics chapter we have studied that. In kinematics chapter we have studied that the value of acceleration along streamline has to be equal to, it has to be equal to dou Vs upon dou T plus Vs into dou Vs upon dou S. This should be the value. Now what I'll assume is, I'm making an assumption over here for my derivation, that if the flow is steady, then what happens? If the flow is steady, automatically the value of dou Vs upon dou T should become equal to 0. Therefore, now the value of As should be equal to, this time I'm not going to write dou Vs by dou S, I'm rather going to write Vs into dVs upon ds. Why I write dVs upon ds? The reason is, since it is no more a function of time, it is completely a function of s, therefore the partial derivative should become a complete derivative. So As is this much. What I will do is, I will put in the value of As over here. So now I am rewriting this equation. I am rewriting this equation over here. So let us say the equation now is minus gamma, differential volume is dA times ds multiplied to dz upon ds minus, again since the flow is steady, dou p by dou s should become dp upon ds times dA into ds should be equal to density into differential volume, again we know is dA times ds multiplied to acceleration along streamline is v into dv upon ds. V into dv upon ds. If you observe over here, I can cancel off dAds, dAds and dAds throughout. After having cancelled dAds throughout, I can rewrite this equation as, let us take all the terms on one side. So I have over here, further I can also cancel off ds, right? Excuse me. I can also cancel off ds over here throughout in the denominator. So now the equation comes down to dp plus rho v dv plus gamma times dz is equal to 0. Let us divide this entire equation by density. So we have dp by rho plus v dv plus g dz is equal to 0. This is the equation we are having. This equation over here is known as Euler's equation. It is known as Euler's equation for steady flow. Euler's equation for steady flow. Now what we will do is we will integrate this equation. Let us integrate this equation. So I can say by integration integral of dp by rho plus v square by 2 plus g times z has to be equal to a constant. It has to be equal to a constant. This equation over here is known as Bernoulli equation. It is known as Bernoulli equation for steady flow. Bernoulli equation for steady flow. This is known as Bernoulli equation for steady flow. Now I make one more assumption. Let us say this time the assumption made over here is the flow, let us say the flow is incompressible. Flow is incompressible. Flow is incompressible. We know that when the flow is incompressible, the value of density has to remain a constant. If the value of density remains a constant, then this equation is going to turn into P by rho plus V square by 2 plus G times Z is equal to constant. Let us take G in the denominator. So Z is equal to a constant. Let us say that constant I am representing by capital H. This equation over here is an equation we are going to study with throughout this chapter, and it is known as Bernoulli equation for steady and incompressible flow. Steady and incompressible flow. So the equation now we are going to look at is this P by rho g plus V square by 2g plus Z is equal to a constant capital H. This is known as Bernoulli equation. Before we go any further, let us first of all discuss what each term over here is signifying. Each term on the left hand side is signifying a specific type of energy the fluid is having in a flow. Which flow it is? The flow we are discussing is steady and incompressible flow, and again we are neglecting viscous effects. Now what are these terms over here? The first term over here, it is talking about pressure energy. It is talking about pressure energy, and this term is known as pressure head. It is known as pressure head. The second term over here is talking about kinetic energy, and this is known as kinetic head. This is known as kinetic head, also called as velocity head sometimes. The final term is talking about potential energy, and this is known as datum head. Datum head. Head over here means energy per unit weight of the fluid. So this is representing pressure energy the fluid is having per unit weight. Similarly, kinetic energy the fluid having per unit weight. Similarly, potential energy the fluid is having per unit weight. And the sum of all these heads, is equal to the total head or total energy per unit weight the fluid is having. Total head, which is total energy the fluid is having per unit weight. Basically, it says that the statement for Bernoulli equation now is the net mechanical energy the fluid has in an ideal flow, while the flow is also steady and incompressible, has to be constant. So now I can say this equation over here is talking about law of conservation of energy in the case of a fluid flow. So let me write the statement over here. The statement is the net mechanical energy, the net mechanical energy of a fluid in an ideal flow, in an ideal flow remains a constant, That constant is known as total energy. If you divide by the unit weight of the fluid, or if you look at the total energy per unit weight of the fluid, you get it as total head. After having seen Bernoulli equation, now let us look at the various forms in which Bernoulli equation can be written. So let me mention over here various forms of Bernoulli equation. Various forms of Bernoulli equation. We are going to mention Bernoulli equation in three forms. The first form in which we will mention Bernoulli equation, it is known as energy per unit mass. Energy per unit mass form. Now, according to energy per unit mass, the Bernoulli equation is written as P by rho plus V square by 2 plus G times Z is equal to constant. This is the equation of Bernoulli equation in energy per unit mass form. We have already discussed what each term represents. So in this form, each term is representing energy per mass. Therefore, this is pressure energy per unit mass of fluid. This is kinetic energy per unit mass of fluid. And this over here is potential energy per unit mass. Moving further, the second form of Bernoulli equation is known as energy per unit volume. Energy per unit volume. According to energy per unit volume, Bernoulli equation is written as P plus rho V square by 2 plus rho Gz is equal to constant. It is equal to constant. Now this equation is important for us. We have to define each term over here. We have to define each term over here. The first term P. How do we define this first term P? This term P over here is known as static pressure. It is known as static pressure. How to understand the static pressure? Imagine there is a flow taking place in a pipe. When a flow takes place in a pipe, every section of fluid is pushing its adjacent section with certain amount of pressure. That pressure is static pressure. And how do we measure the static pressure? Very simple. Whatever is the pressure measured by a piezometer that is going to give you static pressure itself. The second pressure we are having over here is rho v square by 2. This pressure is known as dynamic pressure. This is known as dynamic pressure. It is known as dynamic pressure. How do we define this dynamic pressure? The pressure at which the fluid's velocity becomes equal to 0 is known as dynamic pressure. So basically, imagine that the fluid is moving and suddenly at a particular point you block the flow. So imagine you are having a pipe. Let us say there is a pipe over here. In this pipe there is some flow taking place, and suddenly in between some kind of an obstruction is developed. Let us say this obstruction is developed. Now what happens? Let us say this is a streamline coming. At this particular point on the streamline, the fluid's velocity becomes equal to 0. We call that point a stagnation point. But because the fluid's velocity is becoming equal to 0, its kinetic energy is decreasing. If its kinetic energy decreases, some other form of energy is supposed to rise up. The energy that is rising up is pressure energy, and that rise in pressure is known as dynamic pressure. So I can define dynamic pressure as rise in pressure due to drop in kinetic energy. Rise in pressure due to drop in kinetic energy is known as dynamic pressure. Now, please observe this particular point, which is a stagnation point. This point is stagnation point. What is the pressure at stagnation point? We were already having static pressure at stagnation point. Apart from static pressure, we are having an additional pressure, that is dynamic pressure. So at stagnation point, static pressure and dynamic pressure both have combined. This pressure is known as stagnation pressure. So now I can say that at stagnation point, the pressure is equal to P plus rho v square by 2. The sum of these two pressures is known as stagnation pressure. Stagnation pressure. The sum of these two pressures is known as stagnation pressure. Next, moving further, the last type of pressure we are having is represented by rho gz. It is rho gz. This pressure over here is known as hydrostatic pressure. It is known as hydrostatic pressure. Hydrostatic pressure. How to imagine this hydrostatic pressure? Let us say you are submerging a fluid particle, any particle, lower and lower in a fluid. As you keep submerging, the potential energy is decreasing and the pressure is going to rise up. That rise in pressure is known as hydrostatic pressure. So now I can say this over here is rise in pressure due to drop in potential energy. Due to drop in potential energy. Again, we are having a summation of static pressure and hydrostatic pressure. Previously, we have seen summation of static and stagnation pressure. Now we are having summation of static and hydrostatic, that is P plus rho gz. Summation of static and hydrostatic pressure. This over here is known as piezometric pressure. Piezometric pressure. It is known as piezometric pressure. So now sum of static and dynamic is stagnation. Sum of static and hydrostatic is known as piezometric pressure. Now comes the final form of energy equation, which we have already seen, and that form is energy per unit weight form. Energy per unit weight form. According to energy per unit weight form, we are having P by gamma plus V square by 2G plus Z is equal to a constant capital H. This is the equation we have. P by gamma over here is known as static head or pressure head. P by gamma is known as static head or pressure head. Static head or pressure head. V square by 2G is known as dynamic head or velocity head. Dynamic head or velocity head. And finally you're having Z, which is known as datum head. Datum head. Apart from these three heads, we are having combinations also, as we have seen previously. The first combination we are having is a combination of static and dynamic head, that is P by gamma plus V square by 2G. What is this equal to? P by gamma plus V square by 2G is known as stagnation head. It is known as stagnation head. Stagnation head. If you remember, static pressure plus dynamic pressure was stagnation pressure. Similarly, static head plus dynamic head is going to give you stagnation head. Likewise, the last combination we have is P by gamma plus Z, and this over here is represented by H star. It is represented by H star, and this over here is known as piezometric head. It is known as piezometric head. It is known as piezometric head. This is regarding the various forms of Bernoulli equation. After having seen Bernoulli equation, the next thing we have to think of is when can we apply this? You see, whenever we derive an equation, we create some boundaries or some assumptions under which the derivation is valid. Now, if you are going beyond these boundaries, then you'll have to do some manipulation in the equation as well. That is the topic we are discussing right now. We are going to talk now about limitations and assumptions involved in Bernoulli equation. So let me write over here limitations and assumptions in Bernoulli equation. Limitations and assumptions in Bernoulli equation. Let us start with the first limitation, and this is something which we have discussed when you are deriving. If you remember, while deriving Bernoulli equation, we have eliminated the variation of velocity with respect to time. In acceleration, we were having two parameters. One parameter was dou v by dou t, other parameter was v into dou v by dou s. We have only taken v into dou v by dou s, we eliminated dou v by dou t. What does it mean? It means that we are assuming that the flow happens to be steady. So the first point we have over here is flow is steady. So first point is flow is steady. Simple point. Now comes the second point. If you remember, while deriving Bernoulli equation, we were having a problem with density also. If density varies in the fluid, then the equation we have, the refined equation we have, is not valid. So therefore density has to remain constant. What does this mean? It means that the flow is incompressible. Flow is incompressible. Incompressible. This is the second point we have. Come to third point. Now this third point might not be that much important, but theoretically remember this thing. Especially for civil people, this is of no importance, this third point. The third point is, let me give you the background. You see, we are talking about energies in Bernoulli equation. We have concept pressure energy, kinetic energy, potential energy. But when you are having a fluid flow taking place, there is one more energy which also interacts, and that is heat. The concept of heat transfer is beyond the scope of Bernoulli equation. So Bernoulli equation is not at all talking about heat transfer. This is one more limitation. So you can say that heat transfer effects are neglected. So third point we have over here is heat transfer effects. Transfer effects are absent or neglected. Are neglected. Now this point might be important for mechanical people from thermodynamics point of view. If you remember in your thermal subjects, you come across an equation known as SFEE, steady flow energy equation, which is very similar to Bernoulli equation. Only thing is you add an extra term. That extra term is added in order to overcome this limitation. So this point, let me mention, it is purely mechanical based point. Next thing, next point, very important. Very, very important point, and this point is something which many people do not know in spite of having studied fluid mechanics. This is regarding how to apply Bernoulli equation if you are having a rotational flow and in the case of irrotational flow. So let us say this is regarding Bernoulli equations application in rotational and irrotational flow. Let us do one thing. Let us draw a set of streamlines. Imagine you are having a set of streamlines, and let us say this flow happens to be irrotational flow. Irrotational flow. Let me take another set of streamlines. Let us say rotation is taking place in between. The flow is rotational over here. The flow is rotational over here. So I'm having rotational flow. These two flows I'm having. Now, coming to this flow, irrotational flow, let us say these streamlines over here are represented by psi 1, psi 2 and psi 3. And the total head along this streamline is H1, H2 and H3. Again let us say over here I am having psi 1, psi 2 and psi 3, H1, H2 and H3. at H1, H2 and H3 I'm having. Now let us say I take some point over here. This is point A. This over here is some point B. Now let me ask you a question. Forget about losses. I haven't spoken about losses still. So forget about losses. Tell me, can I mention over here that total head at point A and total head at point B, both of them are same? Yes. I can say that capital H at A has to be equal to capital H at B. Same thing I'm doing over here also. Let us say this is a certain point A and this is certain point B. Can I again mention over here capital H at point A and capital H at point B, both are same? Yes, I can say HA is equal to HB. Now comes the next thing. What if I take a point over here? Let us say this is some point C. Can I say that capital H at A equal to H at B equal to H at C? Yes, it is correct. What if I write over here, it is also, let us say there is some point C over here. I choose a point C. Can I say it is equal to H at point C? There is a mistake. This is wrong. Now I can say over here HA equal to HB, but they are not equal to HC. Why so? This is our fourth point and one of the most important points in Bernoulli equation. Remember, in the case of irrotational flow, you can apply Bernoulli equation across streamlines. What does it mean? You can say that total head 1, 2 and 3, all of them are same. All the streamlines are going to have same total head, so you can apply Bernoulli equation across streamlines. But when it comes to rotational flow, different streamlines are going to have different total head, which means that capital head at streamline 1 is not equal to capital head at streamline 2 is not equal to capital head H at streamline 3. So total head at different streamlines are also going to be different. Over here you can apply Bernoulli equation along streamline, but when you jump streamline, when you go across a streamline, you are not supposed to apply Bernoulli equation. So tell me, if I have a point over here, let us say some point D, I have a point over here, certain point D, can I say this is also equal to HD? It is correct. Can I say it is equal to HD? No, I should say it is equal to HD. Let us say I have a certain point over here, point E. Can I say HD equal to HE? Yes, that is correct. HD is equal to HE, which means that you can apply Bernoulli equation along streamline, but you are not supposed to apply Bernoulli equation across streamline. In the case of which flow? Rotational flow. If the flow is irrotational, never mind, you can go along a streamline, you can go across a streamline also, still Bernoulli equation is applicable. This is the fourth limitation or fourth assumption we have. Moving further, fifth point. Fifth point again is an important point. This is going to talk about involvement of shaft work. This is not exactly a limitation, but it is something, we are trying to overcome the limitation we are speaking about over here. Shaft work basically means involvement of either some machine which is giving power to the system or which is taking away power from the system. So pump and turbine. So from our subject's point of view, pump is something which is adding energy or power to the system, and turbine is something which is extracting energy from the system. What to do in this case? See, very simple. Please observe over here. Imagine you are having a flow taking place. Let us say there is some pipeline, you are having a flow taking place, and in between you install a pump, and then the flow moves forward. Let us say something like this. I take two sections over here. Let us say this is section 1 and this over here is a section 2. My question to you is, can I say total head at section 1 and total head at section 2, are they equal? No, they are not equal. So I can say over here these two things are not equal. Are you following this thing? Why are they not equal? Because pump, when it comes in between, it is going to supply more power to the system. Pump is supplying more power to the system. So now it is not equal. Let us say I ask you over here, let me rather ask you, who is greater? Total head at section 1 is greater or total head at section 2 is greater? Think about this. Pump is giving energy to the system. So of course, after the fluid crosses the pump, it should have more energy. Therefore, over here, total head at section 2 is greater. By how much is it greater? Next question. By how much is it greater? Let us say it is greater by some quantity delta H. By some quantity delta H. This delta H I am going to refer as HP from here onwards. HP over here stands for head of pump. In simple language, you can say HP over here is energy gained by fluid from pump per unit weight. Excuse me. Per unit weight. We know that head basically means energy per unit weight. So HP over here stands for energy gained by the fluid from pump per unit weight of the fluid. So now I see that the difference between these two is HP. Let us say I want to equate both of them. I want to equate both these sides. So what am I supposed to do? If I write H1 over here and I write H2 over here and I want to write an equality sign over here, when is it possible? When can I write an equality sign? Provided I consider this HP also. And how do I consider it? You see, H2 is greater. If I want to equate to H1, I should subtract over here exactly by the difference. Now I can say both of them are equal. So this is how you are going to manipulate your Bernoulli equation whenever you are having a pump. Since pump increases the energy in the system, you are supposed to subtract the head of pump. So if I complete this equation, if I write the entire equation, excuse me, if I write the entire equation, I am supposed to have something like this: P1 by gamma plus V1 square by 2G plus Z1, and section 2 is P2 by gamma plus V2 square by 2G plus Z2. I cannot write equality now still. I am supposed to write minus HP and then I can say equality is valid. This is your Bernoulli equation whenever you are having a pump involved. This is Bernoulli equation when you are having a pump involved. Now think what is going to happen if you have a turbine involved. While you think, I'll be writing some things. Let us say, again you are having a pipeline, in between you are having a turbine, fluid is moving forward. I take over here two sections as I have done previously, section 1 and section 2. Again I ask you, is H1 equal to H2? The answer is they are not equal. I hope you have come down till here. H1 is again not equal to H2. The question is, who is greater? If H1 is not equal to H2, put in the inequality. You see, as I move forward, let us say I am the fluid over here, I am moving forward. turbine is going to take away some energy. Later on, I'm going to have lesser energy, which implies initial energy was higher. Therefore, I can say H1 is greater than H2. Fine. What is the deficit over here? Let us say the difference over here is delta H, and this deficit I am going to represent by HT, head of turbine. Now please tell me, how would you define head of turbine? How would you define HT over here? Again, it should be energy per unit weight, is it not? And which energy per weight, per unit weight? It is supposed to be energy given, energy given by fluid to turbine per unit weight. Per unit weight. So energy given by the fluid to turbine per unit weight. Now please answer me. If I want to rewrite this thing, I am having H1 over here, I am having H2 over here. How should I fit in HT on the right hand side so that I can put equality over here? You see, previously you were subtracting. Now the logic is very simple. You are supposed to add. It is the opposite case. Now you can say both of them are equal. H1 is equal to H2 plus HT. H2 plus HT over here. Now if I rewrite this thing entirely using the general idea of our Bernoulli equation, then the equation would come out to be something like this. You have P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2. I'm sorry, I can't still write equality. Tell me, what should I put over here so as to write equality? I'm supposed to put plus HT, then I can say these two are equal. So this over here is my Bernoulli equation if I'm having a turbine involved. So you know now that whenever a shaft work is involved or shaft power is involved in the form of a pump, turbine, fan, blower, anything, you should have an idea how to manipulate your Bernoulli equation so as to use it. Now the last thing, and probably the most important thing, and let me give you a spoiler now. This last term or last concept we are going to deal with is going to have the concept of head loss. All of you might have heard of head loss somewhere or the other, sometimes in other subjects as well, wherever FM, fluid mechanics, is involved. Now, where does this concept come from? Please recall, when we were deriving Bernoulli equation, we have assumed ideal conditions. We have assumed no viscosity at all, right? So now the limitation I am having over here is, sixth limitation we are having, the refined Bernoulli equation you are having is valid only for ideal flow. So Bernoulli equation, the way it was derived, is valid only for ideal flow. But you see, the beauty of Bernoulli equation lies in its flexibility. Even though it is handicapped, it is having many limitations, but it is so much flexible, it is so easy to be manipulated with. Therefore, we can overcome this limitation also. And how do we overcome? Let us see. Imagine that there is a particular passage. Some system is there, flow is taking place. I am having a flow. I am having a flow taking place in this direction. Let us say there is a flow taking place in this direction. I have over here a section, section 1. I have over here a section, section 2. Now, if the flow is ideal, I can say total headed section 1, total headed section 2, both of them are same. Fine. There is no problem whatsoever. But what if the flow is real? Let me write over here that the flow over here is a real flow. The flow taking place over here is a real flow. What happens whenever a real flow takes place? Imagine while I'm walking over here forward, it is a real motion. Whenever a real motion takes place, then there is going to be resistance against the real motion. This resistance might be by the virtue of friction. In our case, it is going to be by the virtue of friction. Apart from friction, there are going to be resistances by eddies. We'll come across these eddies much later. Okay, please follow this much, that whenever a real motion takes place, someone is trying to oppose that real motion. Someone is trying to resist that real motion. What do you do now? If you want this real motion still to take place, then you give away some amount of energy to this resistance and ask him to keep quiet. Let us say I am moving forward, I am giving away some amount of energy to the frictional resistance so as to overcome them. Now whatever energy I am giving away to the resistance, tell me, is it something which I desire? No. If it is not desired, this energy I am going to call from here onwards as loss. So let us say that you are going to have some resistance in the opposite direction, resistance opposing your real flow, and whatever energy you are giving to overcome this resistance, it is called as loss. If it is a loss, tell me logically that as I move forward, am I supposed to have same total head, higher total head, or lower total head? For sure I am going to have lower total head. That means the value of total head at section 1 is going to be greater than the value of total head at section 2. H1 is greater than H2. Again I have a deficit, again I am having a difference, and let me tell you, there is going to be a difference over here of delta H, and this delta H from here onwards I am going to denote by small h, and this small h is known as head loss. It is known as head loss. The question is, how do I define this head loss? So first of all, it is a loss, and loss per unit weight. Let me not directly use the word loss. I can say over here energy given by the fluid to overcome resistance against flow, resistance against flow per unit weight. Energy given away by a fluid to overcome resistance against flow per unit weight. Now since this is not a desirable energy transfer, we are calling this as loss, and since it is per unit weight, we are calling it as head of loss or head loss, let us say. Now next question, let us say this equation, I want to remove the inequality and I want to write this equation. Suggest me, what am I supposed to write over here? H1 and H2 I am having. Suggest me how to fit in head loss and make an equality sign over here. Logic is simple. If he is weaker than H1, add over here head loss. Now you can say both of them are equal. Now you can say both of them are equal. So you are having H1 is equal to H2 plus head loss. Moving further, if you want to write this in the conventional form of Bernoulli equation, you can say that, you can say P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2. Again, I'm sorry, I wanted equality now. If I write over here, head loss, then I'm going to get equality. This is my Bernoulli equation in the case of a real flow. So whenever you have a real flow, don't think that Bernoulli equation is completely handicapped. You can't repair it. No, it can be repaired. And this is how you repair Bernoulli equation in the case of a real flow. From here, I want to conclude a very important point where many people do mistakes. And that is regarding the direction of flow. Now, first of all, direction of flow whenever is discussed, remember, it is discussed only for real flow. For ideal flow, I cannot tell you the direction of flow. The question itself should tell you where flow is taking place from till where. But when it comes to real flow, I can understand a very important thing. Please observe over here. Observe over here. This is a real flow taking place. And what is the direction over here? The direction can be understood from here. And that is, flow always takes place, a real flow in the absence of a pump should always take place from higher total head to lower total head. Because you see, H1 is higher than H2, therefore a real flow in the absence of pump, again I am mentioning the thing, in the absence of pump should take place from higher total head to lower total head. So let me write this in the form of a note, and please remember this note and ponder over it. Also think about why am I saying in the absence of a pump. So the note is in the absence of a pump, real flow. It is very important to note, I am mentioning over here about real flow only. Real flow takes place from higher total head to lower total head. Lower total head. This is a very important point. And also over here is this part important, in the absence of pump. You see, whenever you have a pump installed, it is possible for the flow to take place from lower total head to higher total head. A very good example is the piping system in the building you are in. Now imagine that this over here is a sump, that underground water level you are having, below your building you have water level, that is sump, let us say. And you have over here, don't mind my diagrams, this is supposed to be rough only, okay. You have over here your overhead tank. Now if I connect a pipe from overhead tank to the sump, from here to here if I connect, then what would happen? A real flow. Now you see, real flow should take place. Real flow should take place from higher total head to lower total head. Higher total head is over here. Don't think the datum is high, therefore total head is high. No, I am not talking about that. I am talking about the complete set P by gamma plus V square by 2G plus Z over here is greater than the set over here. So now what will happen? The flow will take place in this direction. Is this desired? No. The desired direction is from the sump to the overhead tank, is it not? You want the flow to take place from the sump to the overhead tank. How to do that? You are supposed to give some mechanism which carries the fluid or which gives energy to the fluid, and that is pump. That is why you are going to have a pumping system over here. So when a pump is involved, it is possible for you to take the fluid from lower total head to higher total head as well. So this completes the concept of limitations and assumptions in Bernoulli equation. Now, let us look at a factor known as kinetic energy correction factor. Kinetic energy correction factor. It is given by alpha. Important concept, especially for examinations like IES and state level service examinations. Let us first of all see what is the purpose of this factor. Let us imagine you are having a pipe. You are having a pipe. In this pipe, let us say there is a fluid flow taking place. A real flow is taking place. So if I look at a particular section, by the virtue of no slip conditions, I'm supposed to have zero velocities over here. I'll be having maximum velocity at the center. So let us say somewhere over here I'm having maximum velocities. So let us say this is U max. And at any random point, I'm having a local velocity U. The local velocity is U over here. If I ask you, what is the value of kinetic head over here or dynamic head over here, generally you would answer it is equal to V square divided by 2G. You would answer the value of dynamic head is equal to V square by 2G. And what is V over here? V over here is the average velocity of flow. Average velocity of flow. It is the average velocity of flow. But the problem is, you are supposed to take the average velocity head at every particular point. Instead, what you have taken is, you have taken the average velocity and you are taking its head. There is a difference. If you want to understand this difference, let us take a very simple example from numbers to understand this thing. Let us say I'm having nothing to do with fluid mechanics, basic mathematics. I give you three numbers. Let us say I give you number, suppose I give you number 3, I give you number 6, I give you number 12. I ask you to find out the average of their squares. This is my question. Let us say average of squares. How much would that be equal to? These are very simple numbers. You can imagine the squares. The square of this thing is 9, the square of this thing is over here 36, and finally 144. If I take their average, I'm supposed to have 3 plus 12 is 15, 15 plus, let us say, 48. 15 plus 48 is going to give me 63. This would be the average of squares. Instead, what you do is, let us say, you end up finding the square of averages. If you find the square of average, how much would that be equal to? Look at the average of these three numbers. It is 9 plus 12 is 21 by 3 is 7. 7 square is equal to 49. And now both of them are not equal. Something very similar is happening over here also. You are supposed to find the velocity head at every point and then get its average. Instead, what you have done is you have taken the average velocity and then you are finding its velocity head. So there is an error developed whenever the velocity profile is non-uniform. In order to overcome this error, you are supposed to multiply a correction factor over here. That factor is alpha, which is known as your kinetic energy correction factor. How to calculate the value of this alpha? Let us see now. Imagine that same problem we are having. The cross section of a pipe is something like this. of any flow, let us say something like this, and I am having local velocity equal to u. Local velocity is equal to u, and let us say this local velocity is functioning over a small area. That small area is, let us say, area dA. Over certain small area dA, this local velocity is functioning. So let us say this is some area dA. Over this area dA, the local velocity is u. If I wish to find out the value of differential kinetic energy flux over here, then I can say differential kinetic energy flux, that is kinetic energy per unit time, it would be equal to half into dm dot multiplied to local velocity is u, therefore u square. That means this is equal to half into dm dot is equal to density. It is equal to density multiplied to differential area multiplied to velocity, again multiplied to u square. So u square over here. So this is equal to half into density multiplied to u cube times dA. This is a value of differential kinetic energy flux. And I can say complete kinetic energy flux has to be equal to, half times density times integral of u cube times dA over the entire area A. This is a value of complete kinetic energy flux. Save it as some equation number 1. Now, I can also say this complete kinetic energy flux is equal to alpha multiplied to, that is correction factor multiplied to kinetic energy flux calculated by taking average velocity, and that would be equal to how much? Half into rho AV, this is the mass flux, multiplied to V square. So this is equal to alpha into half rho A into VQ. So this over here, let us say, is equation 2. All I'm going to do is, I'm going to equate equation 1 and 2 because they have the same left hand side. So now I can mention, since equation 1 equal to equation 2, therefore half rho integral of u cube times dA over the entire area A is equal to alpha into half rho AVQ. I can cancel half rho and half rho on both sides. If I look for the value of alpha, the value of alpha over here would come out to be 1 by AV cube into the value of alpha would come out to be 1 by AV cube into integral of u cube times dA. This is the value of kinetic energy correction factor. And this integral is taking place over the entire cross section of the flow. So the formula is 1 by AV cube integral u cube times dA. You know what is capital A? It is the entire area. Capital V is the average velocity of flow. U is the local velocity, and dA is the area at which the local velocity is functioning. Now, talking further about this alpha, please remember the value of alpha should be greater than or equal to 1. It should be greater than or equal to 1. When is equality possible? For equality to be possible, there should be no error when calculating the value of kinetic head taking average velocity. That is only possible provided every local velocity is same. In other words, the velocity profile is uniform. So I can say alpha is equal to 1 only in one case, and that case is velocity profile is uniform. Velocity profile is uniform. Otherwise, alpha has to be greater than 1. One more standard value of alpha, it is better if you can remember, that is alpha is equal to 2. And when is it equal to 2? Alpha is equal to 2 when you are having laminar flow through pipes. Laminar flow through pipes. Also remember that in general the value of alpha for turbulent flow is lesser than the value of alpha for laminar flow. Why is it so? Because in the case of turbulent flow, the velocity profile approaches a uniform velocity profile. Whereas in laminar flow, the velocity profile is far away from a uniform velocity profile. In the case of pipe flow, the value of alpha for turbulent flow, in the case of pipe flow, the value of alpha for turbulent flow ranges from 1.1 to 1.3. These numbers can keep on changing based on the intensity of turbulence. So this value is for turbulent flow through pipes. Turbulent flow through pipes. Let us take an example. Imagine that there's a passage something like this. This is the passage I'm having. Through this passage, there is a fluid flowing. Let us say I have some flow taking place over here. There is a flow taking place over here. I locate 2 points. Suppose this is some section 1 over here. This is another section 2 over here. My aim right now is to find out the difference in piezometric heads of point 1 and point 2. So basically the question over here is delta H star, which is equal to H1 star minus H2 star. This is equal to how much? This is the question. So I aim to find out over here difference in piezometric head. Now you might be wondering why difference in piezometric head is required. This difference in piezometric head is going to be later on very important for finding velocities and finding discharge in a particular flow. Now think about it. How do I find out difference in piezometric head? The most basic way is to install piezometers. So let us say I take over here above section 1 and above section 2 I install 2 piezometers. So let us say over here I am having a piezometer moving up something like this, and over here I have a piezometer something like this. These are 2 piezometers I am having. Once I install piezometers, the working fluid is going to rise up in order to show the pressure level. So let us say the working fluid over here is rising up till here. Let us say the working fluid is moving up. Similarly, the working fluid over here is moving up. Let us say something like this. Now, Let me assume over here a reference datum. Suppose this over here is a reference datum, z is equal to 0. Therefore, this height over here I can say is going to be equal to z1. This height over here is going to be equal to z2. And then I can say from this particular point, if I move further up till this elevation, I am having static head, that is P1 by gamma. Similarly, from this point, if I move up till here, I am having static head for this point 2, that is P2 by gamma. That is P2 by gamma, which implies the sum of this till here, that is Z1 plus P1 by gamma, is supposed to give me H1 star. And this till here is going to give me H2 star. So I can say that this entire thing over here is H1 star. Let us say this is H1 star. And the entire thing till here, this is H2 star. Let us say this is H2 star. Fine. Now the question we started with was finding the difference in piezometric head. So I can say now that the difference in piezometric head should be the difference between these two levels, which is equal to, let us say, this much. This is going to be the value of delta H star. Now this was not that difficult. Now let us move further. Imagine that this flow was having high pressures. Imagine very high pressures over here in megapascals and all. So is it going to be practical for you to use piezometers? Because if you use piezometers, you would require very high height of the piezometer in order to maintain these pressures. So in most of the cases, even though this is correct, in most of the cases it is not practically applicable. Please understand the difference. There is no technical fault over here, but practically it is not applicable because you would require high piezometers, sometimes in measures of tens of meters. That is not possible. So therefore we have to think of some other method in order to find out difference in piezometric head. Let us again choose that passage. The passage we have chosen was something like this. Imagine that this is a passage. This is a passage. I had chosen 2 points over here. Let us say one point, point 1 is over here. Another point, point 2 is over here. My aim is still the same. My aim over here is to find out delta H star, which is equal to H1 star minus H2 star. So the value of delta H star is how much? Is still the aim. Previously we have installed piezometer that was giving you the correct answer, but in many cases if the pressures are very high, it was not practical enough. For that purpose, now what we are going to do is, instead of installing piezometer, we are going to install manometers. So let us say I choose to install manometer, a U-tube differential manometer under point 1 and point 2. So let us say I have a manometer over here. I have a manometer. Under these 2 points. So this, let us say, is a manometer. Now since point 1 is having lesser velocity, on account of higher area it should have lesser velocity, and it is having lesser datum, therefore it should have higher pressure. So if it is having higher pressure, then I can say that the manometric fluid is supposed to go down. Let us say the manometric fluid over here is taking a lower level, and the manometric fluid over here should assume a higher level. Let us say the manometric fluid over here is assuming higher level relative to the left limb. Let us say something like this is happening. Now what I do is I choose a reference datum. Regarding reference datum, please remember this thing. It is up to you to choose a reference datum, whatever is convenient to you. In this particular case, I find that this level over here is convenient to me. So this is, let us say, a horizontal line, and this is my reference datum. After having chosen this as a reference datum, now I am going to mention some elevations. Let us say this elevation over here is Z1. This elevation over here is Z2, and the difference between the meniscus level of the manometric fluid, let us say, is equal to HM. Now you see, the value of HM is something which we will know by the reading in the manometer. So please understand that HM, Z1 and Z2, all these three quantities are known to you. So your delta H star can be in terms of these things. There is no harm. Furthermore, we also know that this is working fluid. The flow taking place over here is of working fluid. So I represent the property of working fluid by gamma W. Similarly, this is manometric fluid. I am representing the property of manometric fluid by gamma M. This is the value of gamma M over here. Fine. Now, after having mentioned these things, let us go back to the concept of manometry. According to manometry, we know that these 2 points over here are supposed to have same pressure. The reason being, these 2 points are lying on the same elevation level, and the fluid from here till here is continuous throughout. For that purpose, let me mention this point as some point A and this point over here as some point B. I can now say that the value of PA must be equal to PB. PA must be equal to PB. And from here I am going to get the value of delta H star. Let us see how. Let me push it over here. So whenever you require, you can see from here. Let us start writing the value of PA is equal to PB. I have mentioned already that PA has to be equal to PB. Now look at this point, point PA. I can say the value of PA has to be equal to the pressure over here plus whatever is the pressure due to the liquid column from here till here, which is PA is equal to P1 plus, P1 is the pressure at point 1 plus, since I am coming down, I can now write gamma working multiplied to Z1. Fine. This is the value of PA I am having. Now come to this point PB. Again I can say it is equal to P2 plus whatever is the pressure on account of liquid columns over here. So that is equal to P2 plus. Now please be careful, we have done this thing previously in statics. I am supposed to come down only till here. And that much of difference or distance is how much? It is Z2 minus HM. So therefore, gamma working multiplied to Z2 minus HM. You have reached till this point. Now moving further down, that means you are supposed to further add over here plus gamma manometric into HM. So gamma manometric into HM. This is the value I am having. After writing this equation, let me now write this as P1 plus gamma W times Z1. Let me couple it up. Now I am going to take P2 plus gamma W Z2 on the left hand side. Therefore I can write it as negative of P2 plus gamma W times Z2. What am I left with now? I am left over here with two terms. One is gamma M HM. The second term is negative of gamma W HM. So that is gamma M HM minus gamma W HM. This is the value. Now look at these terms over here. What is this term over here representing? This term over here is representing P1 star. This is representing P1 star. Similarly, this term over here is representing P2 star. This is representing P2 star. Now P1 star over here stands for piezometric pressure at point 1 and P2 star is piezometric pressure at point 2. So therefore I can now say that the value of delta P star, P1 star minus P2 star is delta P star, it has to be equal to HM common to gamma M minus gamma W. This is a value. I have got the value of delta P star now, that is difference in piezometric pressures. But what I want over here is difference in piezometric head. How do I get that? All I have to do now is to divide this thing by gamma of working fluid. So let us say I am dividing by gamma of working fluid. After dividing this by gamma of working fluid, I am going to get now that delta P star by gamma W, delta P star by gamma W is basically equal to delta H star, and the value of this delta H star is equal to HM multiplied to gamma M minus gamma W whole divided by gamma W, whole divided by gamma W. Now this value is now going to be delta H star is equal to HM multiplied to gamma M by gamma W is SM by SW. I can say so because we know that the ratio of density, ratio of specific gravity, ratio of specific weight, all of them are supposed to be same. Minus gamma W by gamma W I can write as 1. So now I have got my result. The value of delta H star when a U-tube manometer is installed is going to be equal to this much. Now let me write this result over here. I can write it as delta H star is equal to HM multiplied to SM by SW minus 1. This is the result we are having. Now you can modify this result under something which you have to remember. So please highlight this thing. You can modify this result in certain cases. In which case? Imagine that the fluid that is running through this passage or flowing through this passage is having very less density compared to the fluid in the manometer. For example, you are having a gas over here. The simplest gas you know of is atmosphere air, and air has a density approximately you can say 1.25 kg per meter cube. And let us say this over here of course has to be a liquid. The simplest liquid you know of is water, and it has to have a density of 1000 kg per meter cube. We know this thing. Now imagine you are taking the ratio of 1000 to 1.25. 1000 upon 1.25 you'll get as 800. So this value Sm by Sw in this particular case is 800. You are subtracting 1. Now if you subtract 1 from 800 or you do not subtract 1 from 800, it is not going to make much of a difference. That means you can neglect this minus 1 provided Sm by Sw is very high, relatively high with respect to 1. In simple language, whenever the density of the manometric fluid is much greater than the density of working fluid, that time you neglect minus 1. So I can write this as if Sm is much greater than Sw, it implies that Sm by Sw is much greater than 1, which implies now in this particular case alone delta H star has to be equal to Hm multiplied to Sm by Sw. Let us rather say approximately equal to, not exactly equal to, approximately equal to this much, and that would still give you a correct answer. Fine, but do not use this when you are having a liquid and liquid. If you have a gas and liquid, fine, you can use this thing. This is regarding the concept of finding the value of delta H star, that is piezometric head difference, whenever you have a manometer connected. And when do you require a manometer? In two cases. One case I have mentioned to you already, that is when the difference in pressures is extremely high or the pressures themselves are extremely high. Second case, if the fluid running over here is a gas, you cannot install a piezometer. Remember the limitations piezometer was having. If those limitations are still applicable over here, then you have to install a manometer. So when you install manometer, the result is going to be this much. In this case, it is going to be approximately this much. Remember these results, we are going to use them later on in pitot tube, in venturi meters and so on. Let us now talk about a very important equation which you will be coming across till the final chapter of hydraulic machinery also, which is equation of power. Equation of power. How to write the equation of power, we are going to see. Now first of all, one question should arise over here. Why am I speaking about power? Why am I not speaking about energy? There are two things, energy and then you have power. See, power actually is the rate of consumption of energy or work, you can say. So you can say rate of energy or work per unit time. This is a very simple way of understanding what power is. Rate of consumption of energy or rate of work being done per unit time is known as power. Now you see, I am having two basic parameters which I am not worried about. I am rather worried over here about power. Why is it so? The reason is, in our subject we are not interested in mass, we are rather interested in mass flux. We don't have a particular amount of mass that is traveling, we are having a continuous supply of mass taking place. Since we are worried about mass per unit time, parallelly you can think that we are not worried much about energy, rather we are worried about energy per unit time. Just like mass per unit time, volume per unit time is important, even instead of energy, energy per unit time is important, and that is going to give you power. Now let us see how to develop the equation. Let us start. I know that power is rate of consumption of energy per unit time, so I can say power has to be equal to energy upon time. Now let us talk about energy. We also know that energy per unit weight of fluid is equal to head. Energy per unit weight of fluid is equal to head. From here I can deduce that energy is equal to weight times head. Weight is equal to m times g multiplied to head. Let me put this value of energy over here. If I put it over here, I'll be getting power is equal to m times g times head per unit time. Now look at this. Mass per unit time we know is equal to mass flux. So I can say this is equal to m dot into g times head. H stands for head over here. If it is so, I can now rewrite the equation of power as, and this is what we are going to remember from here on, power is equal to m dot is rho into q. So I am having rho q gh, or you can also say, if I take rho and g together, I am having gamma into q into h. This is the formula for power we are going to remember throughout our subject of fluid mechanics. You will be using this actually in hydraulic machinery as well. So power is equal to rho q gh or gamma qh. Now the question is, which power is this? What type of power is it denoting? Is it power loss, or is it some kind of pumping power, turbine? What kind of power exactly it is? How to identify that? You see, the logic is very simple. Whatever type of energy I was speaking about, same type of power I am having over here, is it not? If so, I can say whatever type of head I am having, same type of power it is. So I can conclude from here that the type of power corresponds to the type of head, So if you take over here pumping head, then it is going to be pumping power. If you take head of turbine, it is going to be turbine power. If you take head loss, you are going to get power loss. So this is the concept of power. Let us talk about the topic known as free liquid jet. Free liquid jet. Important topic. Very simple questions have appeared in almost every examination. Even questions from here have appeared in examinations like IIT JEE. Now let us see what we have to study in free liquid jet. Imagine there is a nozzle. This is a nozzle, let us say. I am having a nozzle over here. Through this nozzle, I am issuing a fluid. When I issue a fluid, the fluid is going to create a trajectory over here. This fluid is issued with an initial velocity v at an angle theta with respect to horizontal. This velocity v is going to have two components. One component is in x-axis, that is u. The other component is in y-axis, that is small v, let us say. And the initial angle made over here is theta. Theta is the initial angle. So I can say that the value of u has to be equal to complete velocity multiplied to cos of theta, and the value of small v, that is y component of velocity, is equal to v times sine theta. Sine theta. Now this trajectory made over here, it is going to be parabolic in nature. This is parabolic. We will be proving it that it is parabolic in nature in some time. Apart from this, you have to know three more parameters. The first parameter over here is the range. This R stands for range. Range basically is the horizontal distance covered by this trajectory. From range, we have to speak about the maximum height attained by this trajectory. So H over here stands for maximum height. Maximum height. Maximum height. Apart from this maximum height, we have one more topic to discuss about, and that is known as time of flight. So let us say capital T is time of flight. Time of flight. So in total, we are going to speak about four parameters. Four parameters over here. The first one being the parabolic nature. Apart from parabolic nature, we are going to speak about range, maximum height, and finally we are going to speak about time of flight. Now let us continue with the concept of free liquid jet. We are first going to talk about the equation of trajectory. So let me draw a diagram first of all. Let us say this is the nozzle I am having. Through this nozzle, a jet has moved something like this. Okay. Let us say any random point on this particular jet is, let us say, x comma y, any random point. The angle over here with respect to horizontal, this angle we know is equal to theta, and we have also mentioned that this velocity is equal to v. Initial velocity is v over here. Now if I wish to calculate the equation of trajectory, what I'll do is I'll start with the basic equations of kinematics. According to kinematics, we know that S is equal to ut plus half of at square. This is a very basic equation. Now what I'm going to do is I'm going to apply this equation. I'm going to apply this equation purely for x-axis. Purely for x-axis. Let us say this initial point over here is my origin. So this is 0, 0. I know that in x-axis there is going to be no acceleration whatsoever. So what I'll do is from here to here I know the displacement is equal to, the displacement over here is equal to x. The displacement is x. The displacement is x, vertical displacement is y. So now if I apply this equation for x-axis, I'm going to get over here, x is equal to, now horizontal velocity is equal to v cos theta. So I can write v cos theta multiplied to t, and I don't have anything to do with acceleration in x-axis, therefore this term is not going to contribute at all. So let us say x is equal to v cos theta. If x is equal to v cos theta, then from here I can say that the value of time t is equal to x upon v cos theta, x upon v cos theta. Let us save this equation over here as some equation number 1. This equation is equation number 1. Now I am going to write the very same equation but for y-axis. So let us say I am again writing over here that s is equal to ut plus half of at square. S is equal to ut plus half at square. This time I am writing this equation only for y-axis. I see the displacement in y is equal to y itself. The initial velocity in y is equal to v sine theta. Now, in place of time t, I am going to put in this value, that is x upon v cos theta, v cos theta. Next thing, plus half of. Now, what is the acceleration? What is the acceleration in y-axis? You see, we are taking upward direction as positive. Therefore, downward direction acceleration has to be mentioned as negative over here, and that acceleration is minus g. Multiply to time square. Time square means this particular value square, that is x upon v cos theta whole square. This is the value of y. Now if you observe over here, I can cancel off v and v. Furthermore, sin theta by cos theta is going to give me tan theta. So now I can write over here this value of y is equal to x times tan theta, x times tan theta. Next thing, minus of g upon 2 times v square into secant square theta would come on top. Secant square theta, whole of this multiplied to x square. Now I want you to observe over here. The value of g we know is a constant. For a given trajectory, we know that the angle theta also is a constant. If angle theta is a constant, then I can say tan theta and secant square theta, both of them are constants. And for a given trajectory, we also know the initial velocity is a constant. So even this is a constant. Therefore, we are having this equation over here. We are having this equation over here in the form of y is equal to ax square plus bx plus c, where the value of a is equal to this entire thing, that is minus g secant square theta upon 2 times v square. This is the value of a. The value of b is equal to tan theta, b is equal to tan theta, and the value of c is equal to 0. Now since y is coming in this particular format, I know that this format is the equation of parabola. This is the equation of parabola. Since it is an equation of parabola, I can say that the free liquid jet on Earth's surface is supposed to create a parabolic trajectory with this particular equation. With this equation. Now let us talk about the maximum height. Recall that the nozzle is something like this and you are having a trajectory which is something like this. Let us say this is this we have. This over here is the maximum height. This is the maximum height, capital, let us say. I wish to find out how much is the maximum height over here. Now, think of what all criterias are supposed to be valid at this particular point. At this particular point, I can say one thing, that at this point the component of velocity in y-axis has to be absolutely equal to 0. The reason is, we know that the velocity for a trajectory is going to be tangential to the trajectory. At the maximum height, the tangent is completely in x-axis. It has no component whatsoever in y-axis. Therefore, the y component of velocity has to be 0. If the y component of velocity has to be 0, recall a formula from again kinematics which says that v square minus u square is equal to 2 times acceleration times displacement. This is a very famous equation in kinematics when acceleration is constant. Let us apply this entire equation in y-axis now. If I apply this equation in y-axis, I see over here the final velocity v is equal to 0 minus initial velocity. Now recall, the initial velocity in y-axis was equal to how much? It was equal to v times sine theta. V times sine theta. So I can write over here capital V square sine square theta is equal to 2 times acceleration times displacement. So twice acceleration is minus g and displacement over here itself is the maximum height, capital H. Now I can write from here that v square sine square theta is equal to 2 times g times h. If it is so, from here I can say that the value of h is equal to v square sine square theta upon 2g. V square sine square theta upon 2g. This is the value of maximum height attained. Now I like to remember this formula in a slightly different manner. What I am discussing this is a different way of understanding. If it is not convenient for you, forget about this. But still give it a try once. You see, I can take 2 points over here. Let us say I choose this particular point as some point 1 and this particular point as some point 2. These 2 points I have chosen in the flow. Mind you, both these points are exposed to atmosphere. That means the pressure head here and the pressure head here, both of them are supposed to be 0 in static measure. So if the pressure heads are equal to 0, let us now write down the equation of Bernoulli. That equation is going to be, let us say, between these 2 points, if I write the Bernoulli's equation, I am supposed to get over here v1 square by 2g plus z1 has to be equal to v2 square by 2g plus z2. Now you see, if I take the value of z1 as 0, automatically the value of z2 is equal to capital H. From here I can say capital H is equal to v1 square minus v2 square whole divided by 2g. This is the value you are having. Now it's the same old thing actually. Whatever we got previous, same thing is repeating over here. Now v1 over here is equal to v itself, so v square, and v2 is equal to the x component of velocity only, so therefore it is equal to v square cos square theta whole divided by 2g, and this again is going to give you v square sin square theta by 2g. This again is going to give you v square sine square theta by 2g. What does this tell you? This is telling that whatever is the loss in velocity head, it is a gain in datum head over here. So whatever velocity head I am losing, that I am gaining in the form of datum head. I lost the velocity by this much magnitude. So if I calculate its head would be equal to how much? V square sine square theta whole divided by 2g, because we know velocity head is equal to v square 2g. So therefore the corresponding head for this velocity will be equal to v square sine square theta divided by 2g. Now this much of velocity head is lost, so it should be compensated in some other form. Which form is it compensating? Is it pressure? No, because we know that both these points are having same pressure, zero pressure. So it is getting compensated in the form of datum head. So whatever is the loss in velocity head, same is the value of h. Now let us talk about the time taken for the entire trajectory to take place, which is known as time of flight. So to understand time of flight, let us say that this is a nozzle I'm having. Through this nozzle, a trajectory something like this is taking place. The velocity is over here. This velocity we know is equal to capital V. Angle is theta. This is equal to V cos theta. And this over here is equal to V sin theta. The time taken for the flight. To understand this thing, let us first of all imagine the motion only till here. So starting from here till here. This is the initial motion. It is also called as ascent. Ascent basically means that you are moving in the upward direction. The second part of the motion is from here till here, which is known as descent. That is, you are moving downhill now. Now remember this thing. By symmetry, we are going to have the time of ascent equal to the time of descent. So now I can say that complete time taken for the trajectory to take place has to be equal to time of ascent plus time of descent. And since time of ascent and time of descent, both of them are same, therefore I can say complete time is equal to 2 times time of ascent. 2 times time of ascent. So if I just calculate the value of time of ascent, I am good then. Let us see how to calculate the value of time of ascent. We know that the displacement from here to here in the vertical direction is equal to v square sine square theta divided by 2g. Now what I can do is, I can write the equation of, we know this equation from kinematics, that v is equal to u plus at. This is the equation we are having. Let us say we write this in y-axis. If we write this in y-axis, we are going to get from here that the value of time is going to be equal to v minus u whole divided by a. Let us say, if I want time of ascent, I can say final velocity over here is the velocity over here, u is the initial velocity over here. If I put in these values, I am going to get over here the value of time of ascent is equal to, the final velocity in y-axis is going to be equal to 0. Initial velocity in y-axis is equal to v sin theta, and acceleration over here is minus g. Acceleration is minus g. If I calculate from here, the value of time of ascent would be equal to v sin theta divided by g. If this is the value of time of ascent, then I can say since total time is equal to 2 times time of ascent, from here I can say that the value of time taken is therefore equal to 2 times v sine theta divided by g. This is the complete time taken. This is the complete time taken. After getting this, we can now talk about range. Recall what range is. Range is this horizontal distance. So from here till here, what we have is range r. How to get the value of range? Again, I am going to use a very simple equation which we have already used for finding out the equation of trajectory, and that equation was displacement is equal to ut plus half at square. Half at square. Now what I am going to do is I am going to write this equation purely for x, and I am going to substitute t as capital T, that is the time taken for the entire trajectory, because range is completed when you have completed the trajectory. So now I can write r is equal to u, we know, is equal to how much? V cos theta. Complete time is equal to 2 times v sine theta whole divided by g. Now this entire thing over here has to be 0 in case of x-axis, because we know acceleration in x is equal to 0. From here I can say that the value of range is equal to, now v times v is equal to v square. 2 sine theta cos theta should give you sine 2 theta whole divided by g. So the value of range is equal to v square sine 2 theta divided by 2g. We got divided by g. Let us now talk about how to measure the local velocity in a flow. This is a common problem and very important problem also in almost every examination you come across in which you are having fluid mechanics involved. For measuring the local velocity at a particular point, let us not straight away find out which device is required. Think logically. What is required for measuring local velocity? Think from Bernoulli equation point of view. Now Bernoulli equation says that P by gamma plus V square by 2G, V square by 2G, Z. This is your total head. So Bernoulli equation says is equal to some capital H, which is called as total head. Now imagine that from this total head I want only this term V square by 2G. How to get only this term V square by 2G? What I'll have to do is, from here, from this total head, if I subtract P by gamma P by gamma and Z, that means I'm removing these two things off, then I'm going to only V square by 2G. What I basically mean is V square by 2G is equal to capital H minus P by gamma plus Z. And we know that P by gamma plus Z is equal to H star, that is piezometric head, which implies if I want velocity head or velocity, all I have to do is find the value of total head, and from that total head eliminate the value of piezometric head. If I get capital H and H star, indirectly I have got the value of velocity then. Now the question is how to get the value of capital H and how to get the value of H star. This is our question. To get the value of capital H, total head, I am going to use a device. This device is going to create stagnation at a particular point in a flow. The point at which I want the velocity, at that point we are going to create stagnation. This device is known as pitot tube. It is known as pitot tube. So I am going to get the value of total head by using a device known as pitot tube. And how do I get the value of H star? See, getting the value of H star is the most simple thing. In its name itself, you know the device. What do you call H star as? Piezometric head. For finding piezometric head, what device is required? Piezometer. So for finding H star, we require over here piezometer. We require piezometer. A very common interview question is, how do you measure the local velocity in a particular flow? Now what people do is, they straight away answer that we are going to use a pitot tube. That is a correct answer, but not completely correct. Just imagine if you use pitot tube, you are going to get total head only. But you don't want only total head. Along with total head, you also want piezometer. So immediately the question will now change to, is pitot tube alone sufficient to measure the local velocity? Now what will you answer? Is pitot tube sufficient? No, pitot tube alone is not sufficient. So what else is required along with pitot tube in order to measure local velocity? In order to measure local velocity, along with pitot tube, I require something known as piezometer. Now next question. This is also again an interview question. The question is there any flow in which you can find out the value of velocity just by using pitot tube? The answer is yes, there is a particular flow. And that flow is specific only to civil engineering branch, and that flow is known as open channel flow. In the case of open channel flow, only pitot tube is sufficient. There is no requirement of piezometer. You will understand it once we draw diagrams. And let me tell you beforehand itself that there is one more device which combines both these effects. It has the effect of pitot tube as well as piezometer combined, and that device also we are going to see. It is known as pitostatic tube. It is known as pitot-static tube. Pitot-static tube. So this is a summary of the concept of measurement of velocity. We have not seen any equation till now. We have not seen any formula. We are just working with the basics. The concept is, in order to get the value of velocity, you have to find out two heads. The difference in these two heads. Which two heads? One is total head, the other is piezometric head. How to find out total head? You require a device known as pitot tube. How to require piezometric head? You require a device known as piezometer. Once you get the difference, you are going to dynamic head or velocity head. From there you can get the value of velocity. Let us continue with the concept of velocity measurement. In velocity measurement, I am going to first start with the basic device, that is pitot tube along with the piezometer. So let us say the first device we are having is pitot tube. Along with this, we are also going to have a piezometer installed. Let us say this is the first case we are having. Now suppose you are having a passage. There is a passage something like this. In this passage, let us say there is a fluid flowing. There is a fluid flowing over here. Now in this passage, at a particular point, let us say at this point, let me call this point as some point A, I wish to find out what is the value of local velocity. To find the local velocity, I am going to start with installing a pitot tube first. How does a pitot tube look like? It is a very basic tube with an elbow to it. Just imagine you are having a tube and you make another tube integrate like this. Two tubes at 90 degrees, if you integrate continuously, that is a pitot tube. So basically a pitot tube over here would be an elbow tube. Let us say something like this. It is taking this kind of a position, something like this, let us say. Now, the moment we install a pitot tube over here, at this particular point, stagnation takes place. And if stagnation takes place, over here, the fluid is supposed to rise up to stagnation head. So let us say you are having the fluid over here rising up till stagnation head. Let us say the fluid is rising up till here. If I measure this height, I can say that this height over here is equal to h stagnation. This is equal to h stagnation. And please recall the value of h stagnation, it is supposed to be equal to static head, that is P by gamma, plus dynamic head, that is V square divided by 2G. This is the value we are having. After installing this, my next aim is to eliminate off the value of P by gamma, and that I am going to do by adding over here a tube which is known as a piezometer. So how would a piezometer look like? This is very simple. Piezometer, all it is going to do is, it is going to expose this particular tube to this particular passage to atmosphere. So let us say slightly ahead, not very far away, just one, let us say, one moment ahead of A, we are installing a tube which is exposing to atmosphere. That is something like this. Something like this. Now what happens is the fluid is going to rise up till the static head level. Let us say the fluid is rising up till the static head level. Now if I measure this height over here, this height, it is going to be static head. Static head, let us say H static, which is equal to P by gamma. It is equal to P by gamma. Now if I assume over here a reference datum Z is equal to 0, then I can say that this height over here is equal to datum head. It is equal to datum head. Therefore this complete height over here, starting from here, is supposed to be equal to piezometric head, that is P by gamma plus Z. This is the complete height, that is piezometric head. In other words, you can say it is equal to H star. Again, this height over here is equal to datum head, and we can say complete height from datum head up till the elevation in pitot tube, it is going to be total head capital H. It is equal to capital. Now if you look at this difference over here, this difference over here, this difference is going to be equal to difference between total head and piezometric head. This is our aim, and this is equal to your V square divided by 2G. This is equal to V square divided by 2G. Let us say this V square by 2G over here is equal to delta H. It is equal to delta H. So we have everything set up over here. This device, we are going to call it as pitot tube. It is pitot tube. This device is your piezometer, and both of them are required to find out the value of velocity head. Once you have the value of velocity head, so let me move further. Once you have the value of velocity head, that means you are having the value of V square by 2G is equal to delta H. Once you have this value, you can then say that the value of V square is equal to 2G times delta H, which further implies that the value of V is equal to root over of 2G times delta H. This is the value of velocity. But the problem is, this velocity over here sometimes has errors. Therefore, this velocity we are going to call as theoretical velocity. We are going to call as theoretical velocity. The actual velocity is going to be a fraction of this theoretical velocity. For that purpose, what we do, we define something known as coefficient of velocity. Let us see what this coefficient of velocity is. We define something known as coefficient of velocity. This coefficient of velocity is represented by C with a subscript V. The value of this coefficient of velocity CV is equal to actual velocity upon theoretical velocity. Theoretical velocity. Therefore, if I intend to find out the value of actual velocity, I am supposed to multiply CV with theoretical velocity. So now I can say that the value of V actual is equal to theoretical velocity multiplied to CV, which implies CV multiplied to, we already know the formula for theoretical velocity, it is root over of 2g times delta h. This is the value I am having of actual velocity. Now the value of CV, if it is not given, then we are going to assume it as 1. So let me write a note over here, a note. If CV is not mentioned, assume CV is equal to 1. This is the assumption. Mostly the value of CV is going to be slightly less than 1, but very close to 1. You will find mostly in the range of 0.95, 0.97, 0.98 and all those things. Very, very close to 1, but slightly less than 1. Apart from this, you should also know that CV sometimes is also called as probe factor. So in some questions, if they use the word probe factor, don't be confused, it is only CV. This is regarding the concept of velocity measurement using pitot tube. Now you should know one more thing, that this is having a limitation, and that limitation over here is you cannot use a pitot tube along with piezometer whenever you are having a gas flow, because if gas flow takes place, it is not possible for you to have a meniscus of gas with atmosphere. So therefore, pitot tube along with piezometer cannot be used for gases. What I am going to do next is, I am going to integrate both these tubes. If I integrate a pitot tube along with piezometer, I am going to get something known as a pitot static tube, and this pitot static tube is useful for measuring velocities in both liquids as well as gases. Let us take the next case now. Let us talk about pitot static tube. So the second device we are having over here is pitot static tube. Pitot static tube. Now, a simple pitot static tube would be something like this. Imagine you are having a passage, something like this, let us say. Something like this, and you are having to find out the velocity at a particular point. Let us say at this point you want to find out the value of velocity. Let us say this point is some point A. The flow is taking place in this direction. The flow is in this direction. Now what I do is, I install a tube something like this. I install a tube something like this. Let us see. Let us say something like this. And inside this tube I am having a manometric fluid installed. So let us say the manometric fluid is assuming this position. The manometric fluid is assuming this position, and throughout where I am not drawing anything, that is a working fluid. So let us say this over here is having a property gamma m, and over here I am having gamma working. It is given to me that the deflection between these two levels is equal to hm. The difference is equal to hm. Now my aim is to identify the velocity at this point A. Now you can observe that over here this part of the tube is acting like a pitot tube, and over here this part of the tube is acting like a piezometer. So I am having a pitot tube, and in that same pitot tube I am coupling a piezometer. That is why it is called as pitot static tube. This is creating stagnation effect, and this is creating static effect. So the value over here for the velocity is supposed to be equal to root over 2g times. Now since you are coupling with a piezometer, you are supposed to write over here delta H star. You are supposed to write over here delta H star. Now we have already calculated some time back, if you remember, we have seen that the value of delta H star is going to be equal to hm multiplied to sm by sw minus 1. This is a value. If I put in this value of delta H star, I am going to get the value of velocity is equal to root over of 2g times hm multiplied to sm by sw minus 1. This is the value of velocity, and this velocity over here is a theoretical velocity. The value of actual velocity, V actual, is supposed to be equal to how much? It is equal to coefficient of velocity multiplied to theoretical velocity. Therefore CV multiplied to root over of 2g into hm multiplied to sm by sw minus 1. This is going to be the value of actual velocity. As a matter of fact, from this particular topic, this particular diagram itself, there was a previous gate question asked for 1 mark. In that question what happened was, over here air was flowing, and over here the fluid was mercury. The manometric fluid was mercury. So this was a condition. So let me do one thing. Let me take it further away so that we can create the question. Excuse me. Let us say this is the question we are having. This is a question. Now the options given over there was something like this. Let us say first option given over there was, there was no CV involved, so forget about CV. One option was root over of 2g into hm. Second option over there was root over of 2g into hm multiplied to 1 minus sm by sw. One option over there was root over of 2g into hm multiplied to sw by sm minus 1, and finally you are having one more option which said root over of 2g into hm multiplied to sm by sw. These were the options. Now, I have mentioned already that the actual option or actual answer in the absence of CV is supposed to be this thing. This is supposed to be the answer in the absence of CV. But you see over here, none of the options is matching what I have mentioned over there. So what is the answer? This was a 1 mark question in GATE examination civil. In GATE examination civil paper. And you can say similar kind of question possible in IES and other examinations as well. There is no calculation involved over here. So in almost every examination you can have such a question coming. The key over here you are supposed to look at are the names of the fluid. You are having over here air and you are having over here mercury. Now you know by logic that the density of air is much less than that of mercury. So I can write over here the correct answer is supposed to be that thing only, but tell me Sm by Sw over here, how much is it in comparison to 1? Is it closer to 1? It is comparable to 1? Is it lesser than 1 or is it greater than 1? We know that it is greater than 1, of course, because mercury's density is greater than air. Moreover, this value is extremely high. It is going to come in the range of 10,000 something. So this is much greater than 1. In such a case, we have mentioned already, I can neglect the value of minus 1 over here. So now the value of velocity is approximately equal to root over of 2g into hm multiplied to sm upon sw. I am supposed to write minus 1, but I neglect it now. So this is the value of velocity I am having. In this particular case, the correct answer would be option 4. Let us start the concept of discharge measurement now. We have already seen how to measure velocity. Now it is time for us to measure discharge. So the topic is discharge measurement. Discharge measurement. This discharge measurement is sometimes also referred to as flow measurement also. Flow basically is representing discharge. Now you see, for measuring discharge, the logic is, if you go by continuity equation, then we know that Q has to be equal to area times velocity. So for measuring discharge, we require two things. One is the value of area, other is the value of velocity. Area over here is a cross-section area. Let us say you are having a pipe in which the flow is taking place. Suppose, for example, this is a pipe in which the flow is taking place. Then the cross-section area is something which we already know. The cross-section area is known to you. So you can say this is something which is a known quantity in general. What is not known is the value of velocity. But please be careful, velocity over here is not any random velocity. Because let us say if you are having a real flow taking place, and of course you are going to have real flow only, so we know that at this particular point the velocity has to be equal to 0. Again at the point over here the velocity has to be equal to 0. At the center you are going to have maximum velocity. You are going to have variation in velocity throughout the cross section area. Then which velocity am I supposed to take over here? This velocity we know has to be equal to average velocity. It is the average velocity at a particular cross section. And this is the unknown quantity. This over here is unknown quantity. unknown quantity. So our aim indirectly is to identify the value of average velocity in a particular flow. Now at this moment, please stop for a moment and then think about, we have already seen how to measure velocity. Can't we use velocity from that particular device and put it over here to get discharge? The answer is no. Because pitot tube along with a piezometer or a pitot static tube, these things are not measuring average velocity. They are actually measuring local velocity at a particular section, at a particular point rather. For example, if you install a pitot static tube over here, at this particular point if you install, you are going to get the local velocity for this particular point. Similarly, if you install over here, you will get the local velocity, which is of course higher, at this particular point. Let us say this is u1, this is u2 over here. What we want is average velocity. That is why using pitot static tube or pitot tube along with a piezometer is not helpful in identifying the discharge. We have to look for different devices now. The first device we are going to look at over here is known as obstruction flow meter. It is known as obstruction flow meter. The first device is obstruction flow meter. Let us now discuss about the working principle of obstruction flow meter. The word obstruction should give you an idea that in the flow we are going to create an obstruction. But let me tell you, this obstruction we are creating is not a complete obstruction. It is a partial obstruction. For example, let us say you are having a passage, a pipeline, let us say, something like this. This is a pipeline, let us say. In this pipeline, when the flow is taking place, so suppose you are having a flow taking place over here. You are having a flow taking place over here. What we do is, at any cross section, we are going to create an obstruction. Let us say a partial obstruction is created, something like this, for example. Let us say some obstruction like this is created at a cross section. Let us say something like this. Now this cross section over here has decreased. For example, if the diameter over here was capital D, we are having a diameter which is lesser. Let us say this is D1, this diameter over here is equal to D2. And of course, the value of D2 over here has to be lesser than the value of D1. Now what happens if you are creating a smaller diameter? You are going to get lesser area as well. You are going to get A2, which is lesser than A1, which further implies that the value of V2 has to be greater than the value of V1. So now we are going to get two different average velocities, and of course the average velocity at section 2 is greater than the average velocity at section 1. What happens next? It implies, now this is very important for us, this implies that the value of pressure at section 1 or section 2 is going to be less than the pressure at section 1. I am using Bernoulli equation over here. Imagine same datum throughout. If the velocity is velocity is increasing, the pressure has to decrease. So this section is supposed to have lower pressure. Let me write over here. This section is supposed to have lower pressure, and relatively this pressure section is having higher pressure over here. So what we are doing basically is we are creating a difference in pressure. Please understand that measuring pressure difference is easier for us. I can install devices like, let us say, Borden gauge or a YouTube meter, something like this I can install, and I can get the value of difference in pressure over here. Once I get difference in pressure, from that difference in pressure, using Bernoulli equation and continuity equation, I can get the value of average velocity. Once I get average velocity, I can get the value of discharge. Let us see how we can measure the difference in pressure. Suppose the streamlines of flow, while they are moving forward, these streamlines are going to converge. Let us say these streamlines are converging over here. As the streamline converges, of course, the velocity v2 over here has to be greater and the velocity v1 has to be lesser. And as we have mentioned, p2 over here, written p2 over here has to be lesser than p1. Now what happens is, after these streamlines converge, they are not going to develop off straight away. These streamlines are going to converge even further. So let us say they are converging even further. They are forming a particular cross section over here. This is a very important cross section. It is known as vena contracta. It is called as vena contracta. Vena contracta. Now, due to the formation of vena contracta, the value of velocity over here further increases. And once the value of velocity further increases, due to that you are going to have even lesser pressure over here. So instead of installing a pressure difference device between section 1 and section 2, we are going to install a pressure difference device between section 1 and vena contracta. After vena contracta, the streamlines are further going to develop. The streamlines will further develop. This is how the streamlines are going to move forward in the case of an obstruction flow meter. So in simple language, you can say that an obstruction flow meter creates a partial obstruction which is going to create a region of lower pressure. Once you get this lower pressure, this is the lower pressure now. For me, the lower pressure right now is this particular point. This is low pressure region and this is high pressure region. Once I'm having difference in pressure, I can find out this difference in pressure, use Bernoulli equation along with continuity equation to get the value of average velocity. Once I get the value of average velocity, I can then get the value of discharge. So let us say over here I'm installing over here a YouTube manometer. Since this region is having higher pressure, the manometric fluid over here should be compressed down. Let us say the manometric fluid is pushed down over here and the manometric fluid will rise up over here. And the difference between these two levels I can denote as the difference between these two levels let us say is equal to hm. This difference is equal to hm. This is a general way how an obstruction flow meter functions. Now you can have different types of obstructions. Different types of obstructions are going to give you different type of flow meters. For example, this particular obstruction is creating a sudden contraction and sudden expansion. We call this kind of obstruction flow meter as orifice meter. It is called as orifice meter. You can have one more device where you are having gradual contraction, then a throat action, then gradual expansion. That I am going to draw next. It is called as venturi meter, very famous device. You can have one more kind of meter where you are having gradual contraction but sudden expansion, as though you have a nozzle and then you are not having a diffuser at all. This is called as nozzle meter. So 3 meters you are having. One is orifice meter, one is venturi meter, one is nozzle meter. This is regarding the basic principle of obstruction flow meters. Let us take the example of a venturi meter, and from venturi meter let us derive the expression of discharge for any obstruction flow meter. Let us see. Imagine you are having some pipeline like this. There is a pipe, something like this. To this pipe, you are installing a venturi meter. Now let me tell you, a venturi meter is going to have 3 parts. One part is a nozzle. A nozzle, let us say something like this. You have a nozzle till here. A nozzle, something like this. The second part is a throat. It is going to maintain a constant cross section, something like this. The third part is a diffuser. Let us say something like this, a diffuser. And then you have the rest of the pipe. So this is a general diagram of a venturi meter. Now in this, let us say the flow is taking place in this direction. The flow is taking place in this particular direction. Now what I do is I define 2 sections. Let us say this is some section 1 and this over here is some section 2. Between these 2 sections, I am going to install a YouTube manometer. So suppose I install over here a YouTube manometer, something like this. Let us say this is a YouTube manometer. I know that section 1 is supposed to have higher pressure. For that reason, let us say the manometric fluid over here is pushed down and over here it rises up. So you are having some manometric fluid filled in over here. This is, let us say, manometric fluid. Now let us say the distance between these two I measure. This distance is equal to, let us say, hm. This distance is equal to hm. So this is a rough diagram of a venturi meter. This part over here I have already mentioned. This part over here is known as nozzle. This part is known as diffuser, and this part over here is throat. this is through. This is a rough diagram of our venturimeter. Now let us see how to get the value of discharge from here. Let me keep it over here. Now I can apply Bernoulli equation between section 1 and section 2. So if I apply Bernoulli equation between section 1 and section 2, I am going to get P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z. This is the equation. 1 stands for section 1, 2 over here stands for section 2. Now after writing this, what I am going to do is I am going to keep the piezometric heads on one side. So let us say I am going to write over here V2 square minus V1 square whole divided by 2G has to be equal to, now I am taking V2 square and V1 square alone over here. This has to be equal to P1 by gamma plus Z1 minus P2 by gamma plus Z2 minus P2 by gamma plus Z2. This is the value we have. Now we know that this term over here is H1 star, and we know that this term over here is H2 star, which implies that H1 star minus H2 star is our right hand side. In other words, it is equal to delta H star. It is equal to delta H star. From here I can write that the value of V2 square minus V1 square whole divided by 2G has to be equal to delta H star, which further implies, from here I can imply that the value of V2 square minus V1 square is equal to 2G times delta H star. 2G times delta H star. So this is the equation I'm having. V2 square minus V1 square is equal to 2G times delta H star. What I'm going to do next is I'm going to apply continuity equation. So let us say if I apply continuity equation, from here I can get that. From here I can write that. We know that A1 V1 is equal to A2 V2. A1 V1 is equal to A2 V2, which further says that the value of V1 is equal to A2 by A1 times V2. It is equal to A2 by A1 times V2. This is the value of V1. I am going to put this value of V1 in the above equation. Now, which implies that V2 square minus, in place of V1, if I put this, I am going to have A2 upon A1 whole square times V2 square has to be equal to 2G times delta H star. This is the value. Now what I'll do is I'll take V2 square common. If I take V2 square common, I'm going to get V2 square multiplied to 1 minus A2 square upon A1 square is equal to 2g times delta H star. Now, if I write this part of the equation, I'm going to get that. I'm going to get V2 square multiplied to A1 square minus A2 square upon A1 square has to be equal to 2g times delta H star. Next step I can write is V2 square is equal to, I am transposing or transporting this particular term over here, A1 square upon A1 square minus A2 square into 2g times delta H star, delta H star. I want the value of V2. So what am I supposed to do now? I'm supposed to apply square root on both the sides. So by applying square root on both the sides, I'm going to get V2 is equal to A1 upon root over of A1 square minus A2 square into root over of 2g times delta H star. This is a value I'm having. Now let me save this thing. This, let us say, is my equation of average velocity at section 2. This is the equation of average velocity at section 2. Now if I want over here the value of discharge, what I have to do is I have to multiply average velocity with area. So I can say that the value of Q has to be equal to A2 times V2, area times velocity, A2 times V2, which implies the value of Q has to be, now if I multiply A2 over here, I am going to get A1 times A2 whole upon root over of A1 square minus A2 square multiplied to root over of 2g times delta H star. This is the formula for discharge when we use an obstruction flow meter. Now let me tell you, if you use a venturi meter or an orifice meter or a nozzle meter, any of these obstruction flow meters, the formula for discharge is going to remain the same. The reason being, the principle followed by any of these three meters is the same. Since the principle is same, we are going to have the same formula. Of course, design is different, so the values might differ, but the formula is not supposed to differ because of the principle. Anyway, over here, what you have got is going to have some error. Why is there going to be an error? You see, if you remember, we were having a cross section known as vena contracta. Whatever velocities we are getting is not exactly for section 2, it is actually for section vena contracta. If we are having velocity for vena contracta, you are supposed to multiply area for vena contracta. We do not know that area. So we have done an error, a deliberate mistake has been done by us by multiplying with area at 2. So please strictly read this particular velocity not as velocity at section 2, even though I have written so. Even though I have written velocity at section 2, strictly speaking, this velocity is for the velocity at vena contracta. It is at vena contracta. Vena contracta. I am supposed to multiply with the area at vena contracta, which I don't know. So I have done a mistake over here by multiplying it with the area at section 2. Now, how to overcome this error? To overcome this error, first thing is you have to accept it is an error. Since we accept it is an error, we are going to call this particular discharge as theoretical discharge. So remember, this formula I have written is not the actual discharge, it is a theoretical discharge. Now comes the concept of actual discharge. How to get the value of actual discharge? For getting the value of actual discharge, we are going to define a particular ratio. This ratio is known as coefficient of discharge. It is known as coefficient of discharge. Coefficient of discharge. This is given by CD. Coefficient of discharge given by CD. How do we define this CD? The value of CD is equal to the ratio of actual discharge to theoretical discharge. So it is equal to Q actual upon Q theoretical. Q actual upon Q theoretical. From here we can conclude that the value of Q actual, has to be equal to CD multiplied to Q theoretical. It is supposed to be equal to CD multiplied to Q theoretical. Furthermore, there is one more extended formula for CD. The value of CD is going to be a product of, value of CD is a product of two coefficients. One coefficient is CV. We have already seen this CV. I hope you remember. CV stands for coefficient of velocity. One more coefficient over here is CC. CC stands for coefficient of contraction. So now I am having two things over here. One is CV. CV stands for coefficient of velocity. Coefficient of velocity. Another is CC, which is standing for coefficient of contraction. Coefficient of contraction. Now, what is the value of this coefficient of contraction? Recall that when you are having an obstruction flow meter, please don't mind my diagram, it is rough. When you are having an obstruction flow meter, when the streamlines were moving forward, this was section 2 and somewhere here was section vena contracta. You are having a section vena contracta. The value of coefficient of contraction CC is equal to the area at this section, that is area at section C upon area at section 2. So upon A2. This is the value of coefficient of contraction. Furthermore, by using continuity equation, I can also say that this has to be equal to V2 upon Vc, because we know that A2 V2 has to be equal to AC into Vc. So please remember this formula, that coefficient of contraction is equal to area at vena contracta upon area at actual contracted section, which is slightly greater than vena contracta, or the ratio of velocities correspondingly. Fine. After having got these things, let us now write down the formula for Q actual. We can now write down the value of Q actual to be equal to coefficient of discharge multiplied to Q theoretical, which implies the value of Q actual has to be equal to coefficient of discharge multiplied to Q theoretical. We have seen was A1 into A2 upon root over of A1 square minus A2 square into root over of 2g times delta h star, 2g times delta h star. Now what I'm going to do is, in this formula, I'm going to break down this formula into two parts. Forget about CD. CD is something which is already understood. One part of the formula is this part. Another part of the formula is part. These two parts are there. Let us say this is the first part of the formula, and this over here is the second part of the formula. So let us observe only this thing. This is our formula right now. It is having two parts. In this first part, you are supposed to talk about the cross-section areas at section 1 and section 2. Sometimes what happens is, instead of giving you cross-section area, they give you diameters. Now, when they give you diameters, still you can find out the area, it's not a big deal. But if you want to directly use diameters, then what happens? So let us say, if D1 and D2 are given, So right now we are talking about the first part, of a formula. If D1 and D2 are given, then I can say A1 times A2 upon root over of A1 square minus A2 square is equal to, now A1 we know is pi by 4 times D1 square, A2 is again pi by 4 times D2 square, whole divided by root over of A1 square is pi by 4 square into D1 power 4 minus A2 square is pi by 4 whole square into D2 power 4. Now if I see over here, I'm having pi by 4 whole square. So this is equal to pi by 4 whole square multiplied to D1 square times D2 square, whole divided by. Observe over here, I can take pi by 4 whole square common, and if I remove it outside the root, it is going to be only single pi by 4. So I have over here pi by 4 into root over of D1 power 4 minus D2 power 4, which further implies that I can replace this A1 into A2 by root over of A1 square minus A2 square. Excuse me. I can replace A1 A2 by root over of A1 square minus A2 square. This entire thing can be replaced by pi by 4 times D1 square into D2 square, whole divided by root over of D1 power 4 minus D2 power 4. So the first part, what we have seen, can be replaced by this thing, So whatever you have seen over here, in its place, you can write this particular term. Now coming to the second part. Second part is talking about root over of 2g delta h star. So you are having, second part says that you are having root over of 2g delta h star. This is the value. Now we have already discussed that the value of delta h star can be replaced by, I am rewriting 2g, I am worried now about delta h star. I can write this delta h star also as hm multiplied to sm by sw minus 1. I can write like this. So this also can be taken in the formula. If imagine hm, sm, sw, these things are given, better use formula. I know that delta h star is equal to delta p star divided by gamma, which is equal to delta p star divided by rho g. I know this also. So now in place of delta h star, if I write delta p star by rho g, what am I going to get? I am going to get that this value is also equal to root over of 2g into, now delta p star by rho g, delta p star by rho g, which implies that I can write this is equal to, this is also equal to root over of 2 times delta p star divided by rho. So if he gives you the value of pressure directly, use that particular value. If he gives you delta h star, better use this. If he gives you hm along with sm and sw, use this particular part. So you should know to manipulate the formula. Still, the formula would remain the same. So what have we learned from here? This has been slightly lengthy. You see what, let us conclude this thing. What have we learned from here? We have learned how to find out the value of discharge. But then we have also seen the problem with the discharge we calculated. It was a theoretical value. It was a slightly overestimated value. For that reason, you had to coin one more term, which is known as coefficient of discharge. Now this coefficient of discharge multiplied to theoretical discharge gave you the actual discharge. Fine. This coefficient of discharge is again having two parts. One is coefficient of velocity, and it has to be multiplied by coefficient of contraction. Coefficient of contraction basically was the cross section area of vena contracta upon the cross section area at section 2. Fine. After having seen all those things, we have then extended different terms which we can replace in the formula for Q theoretical. So when it comes to area term, that area term, you can replace that area term by this thing. If diameters are given, you can replace the area term by this thing. And when it comes to delta h star terms, you can replace root over of 2g delta h star by this or by this thing. This is regarding the concept of discharge measured using obstruction flow meters. Let us now talk about the head loss in obstruction flow meter. Head loss in obstruction flow meter. Head loss in obstruction flow meter. Let us again construct a simple obstruction flow meter. Let us say you have over here a pipeline. Imagine an orifice meter over here. Let us say this is some section 1 and this over here is some section 2. Two sections I have chosen. I am now writing down the Bernoulli equation between these two sections. Let us say the flow is taking place in this direction. Flow is in this direction. So Bernoulli equation over here along with head loss would be P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2 plus head loss. This is the equation. Now what I am going to do is, I am going to take head loss term on one side and push all the other terms on the other side. So let us say head loss is equal to, I can write this as P1 by gamma plus Z1 minus P2 by gamma plus Z2. Now I am having only velocity heads remaining. I can write them as minus V2 square minus V1 square whole divided by 2G. This is what we have. Now, if you observe, this term over here represents H1 star and this term over here represents H2 star. And we are having H1 star minus H2 star, that is equal to delta H star. So now what I can do is, I can write the value of head loss is equal to delta H star minus V1 square, sorry, V2 square minus V1 square whole divided by 2G. This is the value. Now, what I am going to do is, again going to write down in place of V1, I am going to write down V1 is equal to A2 upon A1 times V2. This is the value of V1. If I write this, I am going to get from here that the value of head loss is equal to delta H star minus V2 square minus A2 upon A1 whole square times V2 square whole divided by 2G. Now what I'll do is, I will take V2 square by 2G common. So I'm going to have head loss is equal to delta H star minus V2 square by 2G common to 1 minus A2 square upon A1 square. A2 square upon A1 square. Now, I can simplify this as, head loss is equal to delta H star minus V2 square by 2G, V2 square by 2G multiply to A1 square minus A2 square whole divided by A1 square. This is the value. Now what I am going to do is, I am going to multiply and divide by some terms. Let us say I multiply over here with A2 square and I divide over here with A2 square. There is no harm in doing so. I multiply over here with delta H star, and I am multiplying over here also with delta H star. If I do so, let me rearrange this and write down. I am going to get the value of head loss is equal to delta H star minus, I am having A2 square into V2 square upon 2G delta H star multiplied to A1 square minus A2 square whole divided by A1 square into A2 square multiplied to delta H star. This is what we have. Now please observe, this term over here is very important. In this term, the value of A2 square into V2 square is equal to, since we included head loss, the value of A2 square into V2 square has to be equal to Q actual whole square. Q actual whole square. Next thing, you are having over here in the denominator, you are having A1 square into A2 square whole divided by A1 square minus A2 square into 2G delta H star. So whatever I have chosen this thing, these two things along with 2G delta H star. These things I have taken. This value is equal to Q theoretical square. Q theoretical square. And delta H star of course is delta H star. Delta H star is of course delta H star. So in place of this, if I put Q actual square, and in place of this if I put Q theoretical square, my equation now is going to change. It is going to change. Head loss is now going to become equal to delta H star minus Q actual square upon Q theoretical square multiplied to delta H star. We already know that Q actual upon Q theoretical is coefficient of discharge. So therefore, now I am going to get from here that the value of head loss in an obstruction flow meter has to be equal to delta H star minus CD square multiplied to delta H star multiplied delta H star. If I take delta H star common over here, I am going to get, now this is the ultimate formula, you have to remember, the value of head loss is going to be equal to delta H star common to 1 minus CD square. This is the ultimate formula for head loss in obstruction flow meter. So if the value of head loss is given to you, then from there you can deduce the value of CD, or if the value of CD is given to you, from there you can deduce the value of head loss. Again, this formula is valid for every obstruction flow meter, regardless of whether it is Venturi flow meter or orifice flow meter or nozzle flow meter. Any case, you are going to have the same formula. Only thing, the values will keep changing, formula does not change. After having seen the formulas, let us take a question for measuring discharge. A direct question is given to you. A venturimeter having through diameter of 120 mm, that is D2, through diameter is D2, is connected to a pipeline having a diameter of 300 mm, that is pipeline diameter D1, 300 mm, through which a fluid of a specific gravity 0.85 is flowing. If the pressure difference between the entry and the throat, now mind you, he has given you delta P star over here. The pressure difference in the venturimeter is equal to 4 kilopascal. You have to identify the flow rate in liters per second. Fine. This is the question we are having. Let us write the given data. Given data over here is the value of D1 is equal to 0.3 meters. The value of D2 is equal to 0.12 meters. The value of specific gravity is equal to 0.85, which is equal to, or density we can say is equal to 850 kg per meter cube. Apart from this, he has given you the value of delta P star. It is equal to 4000 Pascal. These things are given to us. Now, he is asking us the value of discharge, but you see nowhere he has mentioned anything regarding head loss or the value of CD. So over here, head loss also is not given, CD also is not given. Both these things are not given to us. If these things are not given to us, we are going to assume that theoretical discharge is being asked. Theoretical discharge being asked, I can write the formula for Q theoretical. Q theoretical is equal to, now tell me the first part which was concerning with the area, are we going to write A1, A2, or we are going to refer the formula with diameters? Of course with diameters over here, because diameters is given to us. So I am going to write over here pi by 4 into D1 square times D2 square upon square root of D1 power 4 minus D2 power 4. Now the first part is finished. Multiply to root over of. Second part, tell me, are we going to prefer 2g delta H star or 2g into Hm multiply to Sm by W minus 1 or 2 delta P star by rho? If you see over here, delta P star is also given, density rho is also given. So we would prefer over here 2 times delta P star divided by rho. This is the formula we are having. Now let us put in the values. If I put in these values, I am going to get the value of Q theoretical is pi by 4 times D1 is equal to 0.3, so 0.3 square, D2 is equal to 0.12, so 0.12 square, whole divided by root over of 0.3 power 4 minus 0.12 power 4 into root over of 2 times delta P star is equal to 4000 whole divided by density is equal to 850. Density is 850. If you calculate this entire thing, you are going to get the value of Q theoretical. Q theoretical is equal to 0.035 meter cube per second. But the question is asked in liters per second, therefore I can say it is also equal to 35 liters per second. So the answer over here is 35 liters per second. The answer for this question is 35 liters per second. Now this was quite a simple question. Let us complicate the same question and see. I am having the same question over here. I am going to slightly extend it. The question again reads, venturi meter having throat diameter 120 mm is connected to pipeline having a diameter of 300 mm through which a fluid of specific gravity 0.85 is flowing. If the pressure difference between the entry and throat section of the venturi meter is 4 kilopascal, flow rate is how much? Now let us say over here I am including some more data. The data I am including is over here the value of head loss is equal to 10% of delta H star. The value of head loss I am giving is 10% of delta H star. Now you see, by giving this extra data, I am indicating that now what I want is not theoretical discharge. Now what I want is actual discharge. So now the question is, Q actual is equal to how much? We know that the value of Q formula wise, Q actual has to be equal to coefficient of discharge multiplied to Q theoretical. We have already calculated Q theoretical. In the last slide, we have seen Q theoretical was 35 liters per second. Fine. Now the question is, how do we calculate the value of CD? Recall the relationship of CD and head loss. Recall the formula. The formula said that head loss is equal to delta H star multiplied to 1 minus CD square. 1 minus CD square. Now from the given data, head loss is 10% of delta H star. So I can say that this head loss is 0.1 into delta H star has to be equal to delta H star multiplied to 1 minus CD square. I can cancel off delta H star and delta H star over here. I am left with 0.1 is equal to 1 minus CD square, which implies CD square is equal to 1 minus 0.1 or equal to 0.9, which implies the value of CD is equal to root over of 0.9. Root over of 0.9. The value of CD is root over of 0.9. That is equal to approximately, it is equal to 0.95. This is the value approximately of CD. Once I have got the value of CD, I can now use this particular result over here. I can use this result and now I can say the value of Q actual is equal to 0.95 times 35 liters, which implies the value of Q actual is equal to 33.34 liters per second. This would be the answer. This would be the answer. The value actual now is equal to 33.34. Now you see, just by giving this data of heads, the question has indirectly talked about Q actual. Whenever CD is indicated or head loss is indicated, now you are not seeing the value of only Q theoretical, you have to look for the value of Q actual. You have to look for the value of Q actual now. Now let us do one more thing. Let us say there is an alternate method for finding out the value of Q actual over here. Let us see how to look for that alternate method. I hope you have taken this thing, so I am erasing it off. Now let us see this the alternate method for finding out the value of Q actual. So again, Q actual is how much is the question. This time we are looking for the alternate method. The alternate method is, if you see 10% of delta H star is lost. Let me write over here, 10% of delta H star is lost. It is lost. What does this imply? This also is implying that 10% of delta P star also is lost. So now I can say that 10% of delta P star is lost. In the flow meter, you are losing 10% of delta P star. What does this imply? This implies actual delta P star has to be equal to the remaining value. The remaining value would be 90%. If 10% is lost, only 90% is remaining. So it is equal to 90% of given delta P star. What is given delta P star over here? It is equal to 4000 Pascal, which implies that the value of actual delta P star has to be equal to 90% of 4000 Pascal is equal to 3600 Pascal. This is the value of actual delta P star. Once I get this value, I am going to avoid CD. I am going to use the concept of Q theoretical only, but in this Q theoretical, I am not going to put delta P star is 4000, I am going to put delta P star is equal to 3600. That means the value of Q now, this is Q actual only, Q actual is pi by 4 into d1 square times d2 square upon root over of d1 power 4 minus d2 power 4 multiplied to root over of 2 times delta P star actual by density rho, delta P star actual by density rho. So what am I going to from here? This is equal to pi by 4 times d1 square, we know it was equal to 0.3 multiplied to d2 square was equal to 0.12 square divided by root over of d1 power 4 is 0.3 power 4 times, sorry, not times, rather minus 0.12 power 4 multiplied to root over of 2 times delta P star actual is equal to 3600 upon density is equal to 850. If I do this calculation, I am going to get 0.03334 meter cube per second, and this value we know is equal to 33.34 liters per second. By getting the value of Q actual. So this is the alternate method. One method you have seen already. In that method, you are finding out the value of CD and using the conventional formula CD multiplied to Q theoretical. The second method is not finding out the value of CD, forgetting the value of CD. Instead, we are taking the actual value of delta H star or delta P star, and that if we take, CD is covered in over there, then again you are going to get the value of Q actual. Either way, you should get the same answer. This is regarding the concept of obstruction flow meter. Let us summarize the concept of velocity measurement and discharge measurement using various devices. Let us talk about velocity measurement first. Now you are having a setup over here. Let us say this is a pipe. In this pipe I want to measure velocity at a particular point. Suppose this is the point I am having. At this particular point I wish to measure the velocity. We have discussed already that for measuring the velocity head, we have to measure two heads, stagnation head and static head. The stagnation head is measured using this device, which is our pitot tube. So let us mention this as pitot tube. Pitot tube. Now pitot tube is measuring pressure head along with velocity head. In order to get only velocity head, I have to remove off the pressure head. And how do I do that? I add over here another device, and this device is piezometer. Piezometer. Now, in the case of piezometer, I am going to measure only static head or only pressure head. So this height over here is only pressure head. That means the remaining height in this is going to be only this much. This is representing my velocity head, in other words v square upon 2g. So this is how you are going to measure velocity at a particular point in the case of pitot tube. Now please understand one more thing, that pitot tube is used for measuring local velocity. We are not measuring average velocity at a section. If we were measuring average velocity, then it could have been used for measuring discharge also. Anyway, now what I'm going to do is, I'm going to combine the effect of pitot tube and piezometer in a single device, and that device is known as pitot static tube. Please observe over here. In the case of a simple pitot tube having only one orifice, which was creating stagnation effect. It was creating stagnation effect. But now when it comes to pitot static tube, you are going to have the same effect over here. Along with that, on the periphery you are going to have smaller orifices through which you are going to create static effect. This is going to create static effect. So you have stagnation effect. Apart from stagnation effect, you are having static effect also. Now what happens in this particular tube, let us say the fluid rises up to some level. That level is stagnation head. And in this tube, the fluid rises up till some level, and that level is static head. Whatever is the difference between these two, this is going to represent your velocity head, that is v square upon 2g. This is representing v square by 2g. So in simple words, you can say that a pitot static tube combines the effect of both pitot tube as well as piezometer. So this is regarding the concept of velocity measurement. Now let us move further to discuss the concept of discharge measurement. We have discussed already that for discharge measurement, we are going to use something known as obstruction flow meters. Obstruction flow meters. Now let us see various obstruction flow meters. I am going to start with the most famous one, which is known as Venturi meter. Please observe over here. This is a typical Venturi meters diagram. You are going to have a pipe to which you are connecting a Venturi meter. This Venturi meter has three portions. One portion over here is a nozzle, and the mid portion over here is a throat, and the final portion is a diffuser. Now regarding Venturi meter, one important aspect regarding its design is, remember, the diffuser is supposed to have a smaller angle compared to a nozzle. So let us say the angle made over here, let me say that the angle made over here, this angle, let us say, is diffuser angle. I am representing by beta. This angle is a nozzle angle. Let us say I am representing by alpha. The thumb rule over here is the value of alpha has to be greater than beta. That is, the nozzle angle should always be greater, diffuser angle should always be lesser. What is the reason behind this thing? Please understand that in the case of nozzle, the flow is accelerating. In the case of accelerating flow, you won't be having eddy losses or minor losses. But in the case of diffuser, the flow is retarding. Why so? Because you are seeing over here area is increasing, so by continuity equation, velocity should decrease. So over here you are having retarding flow. In the case of retarding flow, you are going to have minor losses taking place. In order for these minor losses to be smaller, or in order to reduce these minor losses, what we do is we try to create smaller increment per unit length. In order to create smaller increment in area per unit length, you make the angle of beta lesser and lesser. So you can say alpha is lesser than beta. The reason being, over here minor losses in diffuser can be reduced. So by making the angle beta lesser than the angle alpha, you can keep on reducing the minor losses. Anyway, if you see over here, you can connect these two portions with a manometer, let us say. When we were in general, when we use this thing, we connect these two manometers, and the manometric difference, let us say, is equal to hm. Manometric difference is hm, and we know how to use this in the formula. We have already discussed the formula. But right now, if you see over here, he has used two piezometers over here. Using these two piezometers, you can get the value of delta P. Once you get the value of delta P, even that can be used in the equation of discharge. We have discussed regarding these equations already. Let us move further to the other devices. Look over here. You have another device which is known as an orifice meter and another device which is known as nozzle meter. Both these devices are again a part of obstruction flow meter only. Okay. In the case of orifice meter, let us say you are having an orifice plate. So this over here is known as orifice plate. This is known as orifice plate. An orifice plate is going to create a contraction. Let us say this is a contracted area. But we have discussed already that the smaller cross section in a flow takes place slightly beyond the contraction. This smaller cross section over here, it is known as vena contracta. Vena contracta. I hope you remember these things. It is known as vena contracta. Now, you have this area over here. Let us say this area is A1. This area over here is A2. Using these two areas, you can find the value of discharge when you connect an orifice, when you connect a manometer over here. Now, apart from orifice meter, you have one more device which is known as nozzle meter. In the case of nozzle meter, you are going to have the nozzle part, but you do not have the diffuser part. Okay, so this area over here is serving as A2. And this area over here is serving as A1. This cross section area is serving as A1 over here. Okay. So I can summarize like this. In the case of venturi meter, I am having gradual contraction, gradual expansion. Nozzle meter, I am having gradual contraction but sudden expansion. In the case of orifice meter, I have sudden contraction and sudden expansion. Fine. After having discussed all these things, let us now talk about when is the value of coefficient of contraction going to be higher. Let us say I have three devices over here. Let us say I have venturi meter, I have nozzle meter, and I have orifice meter. Three devices I am having. Orifice meter, let us say. Orifice meter. Let us now talk about coefficient of discharge. Coefficient of discharge. When is the value of coefficient of discharge going to be higher? You see, whenever the expansion and contraction are going to be sudden, the vena contracta formation is going to be more significant. If vena contracta formation is more significant, coefficient of discharge is going to be lesser. In the case of orifice meter, this is around 0.65. Coefficient of discharge is around 0.65. Somewhere near 0.6 to 0.65 you can say. Next, in the case of nozzle meter, it is slightly better than orifice meter. Why is it better than orifice meter? It is at least having gradual contraction. Fine. So therefore, this is something better. It is going to have around 0.85. 0.85 is the value, general value for nozzle meter's coefficient of discharge. Coming to venturi meter. Over here in venturi meter, the formation of vena contracta is least. Therefore, coefficient of discharge has to be highest. This value is nearly 0.95. It can go up till 0.98 as well. 0.95 to 0.98. Now, this coefficient of discharge has a direct result on head loss. How so? Recall the formula for head loss we had developed. Head loss was equal to how much? It was equal to delta H star into 1 minus CD square. Delta H star into 1 minus CD square. Now you see, if the value of CD is higher, what does this imply? It implies that the value of head loss is going to be lesser losses. Then it means that the meter is going to have more accuracy. Now you see over here, in Venturi meter the value of CD is highest, therefore I can say head loss is least, therefore accuracy is highest over here. In the case of orifice meter, the value of CD is least. If CD is least, then head loss is going to be highest. In the case of orifice meter, accuracy is very less. And lastly, I can say that in the case of nozzle meter, you are having a moderate value of coefficient of discharge. If this value is moderate, you can say even head loss is going to be moderate in the case of nozzle meter. Head loss is going to be moderate, even accuracy is going to be moderate over here. Let us take this now. The question says a horizontal pipe carrying water has velocities of 2 meters per second and 1 meter per second at the left and right ends. Now first of all, he has mentioned over here that the pipe is horizontal. If the pipe is horizontal, from here itself I can conclude that the value of Z throughout is going to be equal to constant. So let us say Z is constant over here. The velocities are 2 meters per second and 1 meter per second, fine. The pressure head difference is how much he's asked. Let us see. Imagine the pipe is something like this. Where I personally solve questions, I do not draw pipes, I just draw a line for a pipe. If the pipe is inclined line. If the pipe is horizontal, something like this. Let us say the pipe is something like this. This, let us say, some section 1 I am having, and this is some section 2 I am having. These are the sections I am having. Now, since he has not mentioned anything about losses, I can assume over here the value of head loss has to be equal to 0. If, let us say, head loss is equal to 0, I can write the Bernoulli equation as P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2. This is the equation I'm having. Now, if you observe over here, since Z is constant, I can cancel off Z1 and Z2 on both the sides. He is asking me over here the pressure head difference. Pressure head difference is equal to how much? So I can say pressure head difference, that is delta P by gamma, is basically equal to P2 by gamma minus P1 by gamma. If you observe P2 by gamma minus P1 by gamma, it is equal to V1 square minus V2 square whole divided by 2G. Put in the values of V1 and V2. This is the value of V1 and this over here is the value of V2. So V1 is equal to 2 meters per second, V2 is equal to 1 meter per second. From here I can mention that delta P by gamma is equal to 2 square minus 1 square whole divided by 2G. This value comes out to be equal to 4 square minus 1 square, that is, 4 minus 1, that is 3 by 2G. 3 by 2G I can say is equal to 1.5 by g. Therefore, the answer that is correct is 1.5 by g, which is option C. Look at this question now. The question says, a conical tube of length 2 meter is fixed vertically with its smaller end S1 upward. The velocity head at the upper end is 1.27 meters. Sorry, the velocity head and pressure head at the upper ends are 1.27 meter and 2.5 meter respectively. The velocity head and pressure head at the lower end S2 are 0.203 meter and 5.407 meter respectively. The loss of head and the direction of flow. Two things he's asking. Very simple question. If you observe over here, he has mentioned loss of head. That means when we write our Bernoulli equation, we are supposed to include head loss. First thing. Second thing, he's asking the direction of flow. How do we decide direction of flow? We have discussed this already. To decide direction of flow, are we going to look at which end is having high pressure, which end is having high velocity or high datum? Is this how we decide the direction of flow? No. We decide direction of flow based on which end is having high head. Remember, a real flow takes place from higher total head to lower total head in the absence of any work being done on the fluid. Again, I am repeating, a real flow takes place from higher total head to lower total head unless some work is being done on the fluid in the form of, let us say, a pump work or something like that. A fan also can be used in the case of gases. Anyway, let us start this question. Quite simple question. Smaller end is upward. So if I draw a schematic diagram, the diagram should be something like this. Let us say something like this. This is S1 and this is S2 I am having. At S1, he has given me the value of velocity head and pressure head. So basically, V1 square by 2g is equal to 1.27 meters. Apart from this, P1 by gamma is also given to me. The value of P1 by gamma is equal to 2.5 meters. Fine. At the lower end, he has given you the velocity and the pressure head again. V2 square by 2g is equal to, this value is equal to 0.203 meters. P2 by gamma is equal to, the value of P2 by gamma is 5.407 meters. 5.407 meters. This much is given. What he has not given is the values of Z1 and Z2. Please do not expect the values of datum to be given. Instead, they'll just give you the length and inclination. He has given you both the things. He has given you length and also the inclination. He has mentioned that this length over here is equal to 2 meters. And what about the inclination? He has mentioned that it is kept vertically. If it is kept vertically, let me myself assume that the value of Z2 is equal to 0. If the value of Z2 is equal to 0, automatically it makes the value of Z1 as 2 meters. Z1 becomes equal to 2 meters. Now I can write the equation as P1 by gamma plus V1 square by 2g plus Z1 has to be equal to capital H1, that is total head 1, which implies the value of total head at section 1 is equal to 2 plus 2.5 is 4.5, 5.77 meters therefore. So this is 5.77 meters. Let me highlight this value. H1 is 5.77 meters. Similarly, let me calculate the value of H2. The value of H2 is P2 by gamma plus V2 square by 2G plus Z2 is going to be the value of H2. This value of H2 is equal to, if you calculate, it is going to be 5.61 meters. Let me highlight this value, 5.61 meters. Now first thing, which total head is greater? Is it capital H1 or capital H2? You can observe over here, capital H1 is greater than capital H2. If it is greater, therefore the flow should take place from section 1 to section 2. So one thing is done. We have identified the direction of flow. We have to now look at what is the value of head loss. We can say, according to Bernoulli equation, that the value of head loss has to be equal to delta capital H, because there is no work being done. So delta capital H itself is the value of head loss. If you look at the difference in total heads over here, that is equal to 0.16 meter. Therefore, the head loss over here is equal to 0.16 meter. Now check which option is correct. It should say head loss 0.16 and direction of flow S1 to S2. So therefore, the answer that is correct is option C, 0.16 meter, and from S1 to S2. Let us take this question now. The question says a nozzle has inlet and outlet diameters of 100 mm and 50 mm respectively. So I'm underlining the given data. Initial diameter is 100 mm, final is equal to 50 mm. So please, while I'm doing, you parallelly write down the given data as well. If it discharges air, the fluid is air, density is given to you as 1.25 kg per meter cube. Question continues saying, if it discharges air through it at a rate of 100 liters per second, discharge is given as 100 liters per second into atmosphere. So output or outlet here is in atmosphere. The gauge pressure at the nozzle in kilopascal is how much? And you can assume the value of G to be 10 meters per second square. This is a question, quite a direct question. So let us say the nozzle is something like this. I am drawing a diagram, a line diagram. Let us say this is a nozzle. Now you can ask me why I have taken a horizontal line. How can I assume that the nozzle has to be horizontal? You see, nowhere in this question he has mentioned you regarding the length of the nozzle and the inclination of nozzle. If nothing like this is mentioned, we are supposed to make a standard assumption. And what better standard assumption than assuming that it is horizontal? So let us say the nozzle is horizontal. This, let us say, is some section 1 and this over here is some section 2. Regarding section 1 and section 2, we know that the pressure at section 2, P2, has to be equal to 0. Why is it so? Which point is mentioning that the pressure P2 is equal to 0? This point, that it is discharging into atmosphere. Since it is discharging into atmosphere, the gauge pressure in atmosphere has to be 0. Fine, P2 is equal to 0 I am having. Next thing, the question is asking what is the value of P1? P1 is equal to how much is the question over here. Also he mentions that the discharge through over here, Q, is equal to 0.1 meter cube per second. 100 liters per second is equal to 0.1 meter cube per second? This is a question asked. He has given you density also. So if you want, I'll mention the value of density. It is equal to 1.25 kg per meter cube. Further, I want to ask you, what is the value of head loss over here equal to? Has he mentioned anything regarding head loss? No, he hasn't mentioned anything regarding head loss. If he has not mentioned, I can make an assumption that head loss over here is also equal to 0. So this diagram along with the data is giving me a picture of this question. The question is, P1 is how much? Let us see how do we solve this. I am going to start with Bernoulli equation. Bernoulli equation says that P1 by gamma plus V1 square by 2g plus Z1 has to be equal to P2 by gamma plus V2 square by 2g plus Z2. This is the equation we are having. Now in this equation, let us see what all can we cancel off. I am not writing head loss. I hope you all remember this thing. I can cancel over here Z1 and Z2 values. The reason being, I have assumed that this system is horizontal. I can also cancel over here the value of P2 because we have mentioned already P2 is equal to 0. So now this equation comes down to P1 by gamma is equal to V2 square minus V1 square whole divided by 2g. This is the equation. Further, what I can do is, I can cancel g on both the sides. I'll be left over here with density. If I am left with density, I can mention that the value of P1 therefore is equal to density upon 2 multiplied to V2 square minus V1 square. Half the problem is done. I have developed an equation for pressure at section 1. This is the equation of pressure at section 1. Now I have to get the values of V1 and V2. How do I get the values of V1 and V2? I know that the value of V1 has to be equal to Q upon A1, Q upon A1, and this is equal to Q upon pi by 4, therefore I am multiplying 4 over here, into d1 square, that is equal to 0.1 multiplied to 4 whole divided by pi times 0.1 square. If you calculate this value, you are going to get the value of V1 is equal to 12.73 meters per second. This is the value of V1. So let me take this as some, let us say this was equation number 1 and this is some equation number 2. Furthermore, I can continue with the value of V2. By continuity equation again I can say V2 is equal to Q upon A2, which is equal to Q times 4 upon pi times d2 square. That equal to 0.1 times 4 upon pi times 0.05 square. If you calculate this value, the value of V2 comes out to be equal to 50.93 meters per second. Let us save this as some equation number 3. Now this value of V1 and this value of V2 I am going to put in equation number 1. if I put over here, I'm continuing over here, I'd be getting P1 is equal to density is 1.25 upon 2 multiplied to V2 square is 50.93 square minus V1 square is 12.73 square. If you calculate this value, the approximate answer you're going to get is 1500 Pascal. But since the question is asking you in Pascal, you can say that the approximate answer is 1.5 kilopascal. Now I can mention over here, this is equal to 1.5 kilopascal. The pressure at this particular point, at this initial point over here, at the entry point is equal to 1.5 kilopascal. Let us take this question now. The question says water enters a turbine steadily at the rate of 100 liters per second with a pressure of 3 into 10 power 5 Pascal and a velocity of 100 meters per second. So he has given you the discharge and the initial conditions at which the water is entering into the turbine. It leaves the turbine at the pressure of 10 power 5 Pascal with a velocity of 50 meters per second. If no losses occur, so he has mentioned over here, there are no losses. Therefore, the value of head loss I can assume is to be 0. If no losses occur, the power produced by the turbine in kilowatt is equal to how much? So very basic question. Water is entering into a system. It is moving out with a lesser amount of energy. It has delivered the residual energy into turbine. The turbine is producing that much amount of power. We are assuming ideal conditions, no losses whatsoever. Let us see. Let us draw a schematic diagram to understand this thing. So suppose you have some turbine over here. Let us see. This is some section 1. This is some section 2. Regarding section 1 and section 2, he has given you the value of P1. He has given the value of P1, that is equal to 3 into 10 power of 5 Pascal, and the value of V1, which is equal to 100 meters per second. These two things he has given at section 1. At section 2, he has given you the value of P2, which is equal to 10 power of 5 Pascal, and the value of V2, which is equal to 50 meters per second. These things he has mentioned. Again, I am assuming a horizontal pipe system. The reason is he has mentioned nothing regarding the elevation difference. Next, he has mentioned the value of discharge, Q, is equal to 0.1 meter cube per second. Density, since he is saying it is water, he won't be giving you the density, you are supposed to remember it, and it is equal to 1000 kg per meter cube. 1000 kg per meter cube. And you're supposed to find out the value of power, also given to you the value of G is equal to 10 meters per second square. Now whenever G is 10, you can say gamma for water is also 10 kilonewton per meter cube. So till here we are having our given data. So this is our given data. Now let us start solving the question. If I write the Bernoulli equation for this system, I am going to have P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2. It's not finished, I have to further continue. I know the head loss is 0, but since there is some turbine involved over here, I am supposed to include the head by the virtue of turbine. Now please tell me, am I supposed to add HT over here or subtract HT over here? Now you see, turbine is taking away the power or taking away the energy, therefore I will be adding HT over here. When something is eliminated from the system, it is as good as subtracting over here or adding over there. Now, after writing this equation, let us see what all can be cancelled off. Only two things can be cancelled over here, that is Z1 and Z2, because both of them we are assuming them to be same. Now, if I wish to find out the value of HT, head of turbine, it is going to be equal to P1 minus P2 whole divided by gamma plus V1 square minus V2 square whole divided by 2G. This is going to be equal to, now P1 minus P2 is going to give me 2 into 10 power of 5. Since I am writing pressure in SI units, I am supposed to write gamma also in SI units, and the value of gamma is equal to 10 power 4 Newton per meter square plus V1 square minus V2 square. Now V1 over here is 100, so 100 square is over here 10 power 4 minus V2 is 50. So 50 square is equal to 2500 whole divided by 2G. 2G is 20 over here. If you calculate this value, the value of T comes out to be equal to 395 meters of water. So this much of head is taken away by the turbine. Now how do I calculate the value of power? We know that the formula for power is equal to, gamma into Q into H. If I want the power by turbine, I am supposed to write HT over here. So this value is going to become, equal to, now gamma is equal to 10, Q is equal to 0.1 and HT is equal to 395. Now since I am taking gamma in kilonewton per meter cube, I will be getting the value of power in kilowatts. Now if you calculate that, you would get the value of power produced by the turbine is equal to 395 kilowatts. Therefore the answer over here is 395 kilowatts. Let us take this question on velocity measurement. The question says water flows through a large size pipe. The stagnation pressure and static pressure measured by a pitot static tube are 0.3 meters and 0.2 meters of water respectively. The velocity of flow in meters per minute he is asking over here, meters per minute is how much? Now you see, the static pressure and stagnation pressure is not given in terms of pressure, it is given in terms of head. So I actually have over here H static and H stagnation. I have these two values. The value of H static, if you see over here, it is equal to 0.24 meters, and the value of H stagnation is equal to 0.3 meters. For finding velocity, we need h dynamic, that is dynamic head. And we know that the value of h dynamic has to be equal to h stagnation minus h static. H stagnation minus h static is equal to, which is equal to 0.3 minus 0.24, 0.3 minus 0.24 meters, which is equal to 0.06 meters. Now I have the value of h dynamic. The value of velocity is equal to coefficient of velocity multiplied to root over of 2g times h dynamic. Now CV is not given. If you see this entire question, nowhere the value of coefficient of velocity is given. If coefficient of velocity is not given, you are supposed to assume the value of CV is equal to 1. If we assume the value of CV is equal to 1, this implies that the value of velocity is equal to 1 into root over of 2 times 9.81 times h dynamic is equal to 0.06. If you calculate this value, the value of velocity comes out to be 1.08 meters per second. But he is not asking you the question in meters per second, he is asking you in meters per minute. So I can multiply over here by 60, then I am going to get this answer in meters per minute. And if you check this value, it comes out to be equal to, the velocity comes out to be equal to 65 meters per minute. This is the answer to the question. Let us take this question now. It is on velocity measurement. The question says a pitot static probe is inserted in an airflow. Over here, you are not having a liquid flow, you are rather having airflow. A manometer connected to this probe having mercury as the manometric fluid shows a difference of 30 mm. Show the difference of 30 mm. So we have the value of HM given. The value of HM is equal to 30 mm. 30 mm. Assuming the probe factor of 1, probe factor over here is same as coefficient of velocity CV. Density of air being 1.23 kg per meter cube and density of mercury being 13,600 kg per meter cube, and the acceleration due to gravity as 10 meters per second square, the speed of airflow in meters per second is how much is asked. Now let us see how to solve this question. We know that the value of velocity is equal to coefficient of velocity multiplied to root over of 2g into hm multiplied to density manometric by density working minus 1. This is the equation we have, standard equation. But you see over here, the value of density manometric is much greater than density working. If you observe, density manometric in this case is equal to 13,600 kg per meter cube, and density working is equal to, it is equal to 1.23 kg per meter cube. So So there's a lot of difference. In these cases, this ratio becomes much greater than 1. So I can say density manometric upon density working has become much greater than 1, which implies density manometric upon density working minus 1 is approximately equal to density manometric by density working. That means I can neglect this 1 over here. If I neglect that 1 over here, I am going to get the value of V is equal to CV times root over of 2G multiplied to HM times density manometric by density working. Now, please do not use this equation directly everywhere. Use it only when this condition is valid. Let us put in the values now. CV he has given is equal to 1. 2G is 2 times 10. HM over here is 30 mm. If I write in SI units, I am going to get 0.03. Density manometric over here is 13,600. Density working is equal to 1.23. If I calculate this value, this answer comes out. The answer comes out to be velocity is equal to 81.5 meters per second. So for this question, the answer is 81.5. This is a very interesting question and a very good question worthy of examination. The question says the discharge coefficients of Venturi meter and an orifice meter, both installed on a single pipeline of internal diameter 100 mm. Now, please highlight this part over here. Both installed on a pipe. You're talking about a single pipe. Both these meters are installed on the same pipe. Of internal diameter 100 mm are 0.95 and 0.65 respectively. Okay? CV's coefficient of discharge is given. The Venturi throat diameter is same as the orifice diameter. Okay, so the internal diameter of Venturi meter and the orifice diameter, both of them are same. If the pressure drop across the orifice meter is measured to be 300 mm of water, so this over here 300 mm of water is as good as delta H star, but this delta H star is in orifice meter. Let us say OM stands for orifice meter. The corresponding pressure drop for Venturi meter is how much? So he's asking what is the value of delta H star in the case of Venturi meter then. In mm of water, nearly approximate value you are supposed to give. Let us understand this by drawing a schematic diagram. Let us say there is a pipeline. Some pipeline over here. In between, I am installing a Venturi meter. Let us say I install a Venturi meter. The pipeline further goes forward. And let us say somewhere over here you are installing an orifice meter. An orifice meter. Now the device I have installed and you have installed, both of them are having different coefficients of discharge. So the coefficient of discharge over here is equal to 0.95 and the coefficient of discharge over here is equal to 0.65. These are standard values actually. It is better if you remember these values. He has also given you that the value of delta H star over here, delta H star over here is equal to, it is equal to 300 mm of water column, 300 mm of water column. The question asked is, what is the value of delta H star in mm of water column over here? he has also given you that the internal diameter of venturimeter, let us say internal diameter would basically mean D2 over here. D2 of venturimeter is equal to D2 internal diameter of orifice meter also. D2 of orifice meter. If you remember the nomenclature, we have taken D1 for the pipe diameter and D2 for the throat part for venturimeter, or orifice part for orifice meter, smaller diameter. So internal diameters are same, this is mentioned. How do we solve this question? This question is a very simple question based on continuity equation. You see, if 10 people further install some devices, even they are supposed to get the same discharge what discharge this venturimeter is getting. Basically, the discharge in every device is supposed to be same by continuity equation. So I can write over here that the value of discharge in venturimeter has to be equal to discharge in orifice meter. Now please tell me, is this I am writing over here regarding the actual discharge or theoretical discharge? Actual discharge. The reason is you cannot apply continuity equation for theoretical discharge as long as the coefficient of discharges are same. So over here these are actual discharges. These are actual discharges. Now I can write the formula for discharge for venturimeter as coefficient of discharge multiplied to pi by 4 times d1 square minus d2 square. D1 square times d2 square, d1 square times d2 square upon root over of d1 power 4 minus d2 power 4 multiplied to root over of 2g delta h star. Now this much over here is for venturimeter. I am supposed to write the same thing again but for orifice meter this time. So CD multiplied to pi by 4 times d1 square into d2 square upon d1 power 4 minus d2 power 4 under root of multiplied to root over of 2g delta h star. Now this is for orifice meter. Orifice meter. Now please observe, total can be cancelled off over here. Pi by 4 d1 power 2 into d2 power 2 and all these things are same over here also. Furthermore, the value of 2g also is same. So 2g also cancels off. From here I can say that the value of CD into root over of delta h star in venturimeter has to be equal to CD into root over of delta h star in orifice meter. Now put in the values of CD and delta h star. So what do we get over here? I get over here, let us say, delta h star for venturimeter therefore is equal to delta h star for orifice meter multiplied to CD of orifice meter upon CD of venturimeter. CD of orifice meter upon CD of venturimeter whole square. Now if I calculate this part, let us say If I calculate this part, I am going to get the value of delta H star in venturi meter, therefore is equal to, in orifice meter we know the value is equal to 300 mm. So let us write 300 over here multiplied to 0.65 upon 0.95 whole square. This value comes out to be approximately equal to 140 mm of water. 140 mm of water. So the answer to our question is 140 mm of water. Let us take one assertion reasoning question. Statement 1, that is assertion, says that after the fluid has re-established its flow pattern downstream of an orifice plate, it will return to the same pressure that it had upstream of the orifice plate. Let us draw a diagram to understand this thing. Suppose you are having over here a pipeline and you have over here an orifice plate. You have over here an orifice plate. Let us say something like this, and let us say the fluid is flowing over here. It has converged. You know that it forms vena contracta forward. After formation of vena contracta, it is going to expand. So now he is talking about two sections. Which two sections is he talking about? After the fluid has re-established its flow pattern, that means somewhere over here, this is his section 2. After re-establishing the flow pattern, downstream of an orifice plate, it returns to the same pressure that it had upstream of orifice plate. That is, upstream of orifice plate is this particular section, section 1 over here. He is saying that according to statement 1, this statement 1 is basically saying the pressure at section 1 is equal to pressure at section 2. Simple language, no need of any statements. Equation, basically what he is saying is P1 is equal to P2. Let us check whether it is correct or not. Now, whenever we talk about these devices like orifice meter, venturi meter and all, we always assume that the datum heads are same. Fine. So if I write the Bernoulli equation, I get over here P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2. Not to forget, you are going to have head losses. Whenever we talk about these devices, we are going to have head loss, especially in the case of orifice meter, because we know in the case of orifice meter, the losses are more significant. Please recall the formula for head loss. The value of head loss was equal to delta H star into 1 minus CD square. The value of CD is going to be much lesser in the case of orifice meter. Therefore, the value of head loss is going to be more significant. Now, if head loss is significant, let us say head loss is significant over here. I know that the datum heads are same. I know that the velocity heads are also same because continuity equation says so. Now, what should happen? In order to maintain this head loss, or in order to develop this head loss, who has to sacrifice over here? It is the pressure. Therefore, the value of head loss over here is also equal to P1 minus P2 by gamma. If this head loss is not equal to 0, if head loss is not equal to 0, I can say that P1 minus P2 is not equal to 0, which further implies P1 is not equal to P2. P1 is not equal to P2. I am getting a result which is contradicting statement 1. So straight away, if you remember, this was statement 1, statement 2, reason effect. I have over here statement 1 itself wrong. When statement 1 is wrong, straight away you can say the answer for assertion reasoning has to be D. But still, since we are practicing, let us also read statement 2. If you are in examination, my suggestion is don't read anything further. The moment your statement 1 is wrong, write the answer D, move forward to the next question, save time. But since we are practicing, let us go further to statement 2. What does statement 2 say over here? Bernoulli equation, when applied between 2 points having same elevation, same velocity, gives the same pressure at these points. Now this is a slightly ambiguous statement. Why? Same elevation, same velocity. Does it give same pressure? Yes, as well as no. It gives same pressure if head loss is 0. It does not give same pressure if head loss is not equal to 0. Therefore, this statement is slightly ambiguous, but looking at statement 1 itself to be wrong, I can say that the only thing possible over here is statement 2 has to be correct. So basically here the assumption is already made that head loss is equal to 0. Now if this is happening, this is not required now, not applicable basically. Answer of course has to be D. So please remember, whenever you talk about these kind of devices, especially in statement 1 over here, you are supposed to consider head losses, especially in the case of 45 meter. Let us start the topic of vortex motion now. This topic of vortex motion is especially important for mechanical people, and if you are looking for IES examination, then it is important for both mechanical as well as civil people. It's a small topic, very brief topic, and it is quite simple to understand provided you do some visualization. Now, whenever we talk about a fluid flow, in general a person imagines a flow taking place through a particular pipe or a flow taking place outside a tap, something like this. But try imagining a flow where you are having a flow taking place along a curved passage. Let us say, for example, you take a bucket of water and you try to create a whirlpool of water in that particular bucket. You might have tried this thing. Almost everyone does this. When you create a whirlpool, then you find some kind of a peculiar motion which is known as vortex motion. So how do we define this vortex motion? Vortex motion. How do we define this? Let us start with the definition of vortex motion. Definition. I can say a vortex motion is a motion of fluid, a motion of fluid along a curved path, is known as vortex motion, vortex motion. So whenever you are having a fluid flowing or moving along a curved path, we call it as vortex motion. Now, regarding vortex motion, you can think of some examples. Very basic example is of whirlpool. You can say examples over here can be whirlpool or a tornado. Now, one more example which you might have seen is if you take a sink in which water gets clogged because of some obstruction, if you suddenly remove that obstruction, then what happens? Water tries to pass through that passage. When it is passing through the passage, it creates some kind of a whirlpool. Again, that is a case of vortex motion. Now, regarding vortex motion, let us establish some fundamental points. The first fundamental point about vortex motion is, first point is, the radial velocity over here is going to be equal to 0. So you are going to have VR is equal to 0. That means we are going to be interested only in one velocity, which is tangential velocity. In other words, you can say V theta is a tangential velocity. V theta is going to exist. This is the first point. Second point regarding vortex motion. Imagine that flow is taking place along a curved path. How would the streamlines then be? The streamlines also have to be curved. So you are going to have curved streamlines. So second point over here is the streamlines are going to be curved. In most of the cases, you will be seeing circular streamlines. Finally, third point over here we are having is, we are going to discuss two types of vortex flow. So we are having two types of vortex flow. There are actually multiple types of vortex flow, but our subject is constrained only till two types of vortex flow. The first type of vortex flow is known as free vortex flow, free vortex motion or free vortex flow. The second kind of vortex motion is something which we are generating by some application of force. Therefore, it is known as forced vortex flow. It is known as forced vortex flow or forced vortex motion. Free vortex motion is something which is naturally existing. which is existing by the virtue of motion itself. Forced vortex motion is something in which you are applying some external torque. You can say water, when it flows through the sink, the vortex formed over there happens to be a free vortex motion. And the whirlpool you generate in a particular bucket of water, that happens to be forced vortex. Because in that whirlpool, your hand is generating, or whatever instrument you're using, it is generating the rotation. It is generating the vortex. So external torque is provided. Therefore, that happens to be forced vortex motion. Now let us look at the differences between these two vortex motions. Let us say I'm having over here two vortex motions. The first one, let us say, is free vortex motion. Free vortex motion. Second one is forced vortex motion. Forced vortex motion. Let us see the differences now. The first difference, in the case of free vortex motion, the net external torque is going to be equal to 0. So first point I'm having over here, external torque is equal to 0. This I have already mentioned. It is naturally taking place, therefore you are not having any external agent to create this vortex motion. Now let me elaborate this external torque equal to 0. If I say torque happens to be equal to 0, it implies, now we know from basic mechanics that torque is basically rate of change of angular momentum. If it is rate of change of angular momentum, then I can say d by dt of mvr happens to be equal to 0. mvr over here is angular momentum. Its rate is d by dt of mvr. If d by dt of mvr is 0, it implies further that the value of mass times velocity times radius has to be equal to constant. Now imagine that the mass of the fluid chosen is already a constant. If mass of the fluid chosen is already a constant, let us say I eliminate this off, saying it is already a constant. Okay, fine. If it is a constant, then this implies over here, this implies that the value of velocity times radius has to be equal to constant. What is the meaning of velocity times radius? Imagine you are having some container, something like this. In this, let us say you have a fluid over here. You are having an axis about which you are creating the or the natural vortex or the free vortex is created. Let us say I choose a fluid element. I choose a fluid element over here. This fluid element is supposed to have tangential velocity, which is represented by the v over here. And this fluid element is present at a distance of r. It is at a distance of r. So now it is having some velocity which is v. It is present at a distance of r. The multiple, or you can say the product of velocity times radius is constant. That means as I keep increasing the radius, as I keep going farther from the axis of rotation, as I keep moving away, the value of velocity keeps on decreasing. So this basically is implying that the tangential velocity has to be inversely proportional to radius. Please remember this thing. I am later going to use this result in deriving some equations. So I am having over here velocity is inversely proportional to r. In free vortex motion, as you keep moving away from the axis, the velocity keeps on decreasing. Now one problem appears. The problem is, what if you are taking r equal to 0? If r equals 0, then velocity has to become infinite, is it not? Because velocity is inversely proportional to r. At this particular point, we define that at r equal to 0, velocity is not defined. Velocity is not defined. This point is known as singularity point. It is known as singularity point. When r equal to 0 at this particular point, velocity is not defined, and this is known as singularity point. So this is a first point under free vortex motion. If you want to summarize while writing your notes, the summary of this entire point is only one thing, and that is velocity in free vortex motion is inversely proportional to r. If you understand this much from this entire thing, that is more than sufficient. Now come to the parallel difference in forced vortex motion. In the case of forced vortex motion, you are applying a constant external torque. So I can say over here, I can say constant external torque, constant external torque, let us say capital T is functioning over here. Capital T is functioning. Now this constant external torque is going to create something which is very important, and that is every particle in the case of forced vortex motion is going to have same angular velocity. So let me write over here that the angular velocity of every fluid particle is identical or is same. It is same. So from here I can conclude that the value of omega is going to be constant. This is the gist of forced vortex motion. Omega is over here going to be constant. Now, if omega is constant, from here I can say that omega, we know from basic mechanics that it is equal to V by R. It is equal to tangential velocity upon radius. So V by R over here is going to be constant. If V by R is constant, this implies that velocity over here is proportional to R. It implies that the velocity is proportional to R. This is the difference. Now you see over here, it is easy to remember. You are having velocity inversely proportional to R. Over here, velocity is directly proportional to R. What does this mean? Let us say I take a container. Suppose this is a bucket filled with water up to some level. About a particular axis, you are creating some forced vortex motion. So let us say you're using your hand to create a forced vortex motion over here. At any distance r, let us say some distance r1, you're choosing a particle. Let us say this particle has a velocity v1. At some distance r2, you choose a particle v2, which is having a velocity v2 over here. The value of v1 upon v2 has to be equal to r1 upon r2. So I can say that, I'm writing this over here, v1 by v2 will be equal to r1 by r2 in the case of forced vortex motion. Are you following this thing? And what happens at the axis? If you take a particle at the axis, over there what velocity are you going to have? You see, at the axis the radius is equal to 0. If radius is equal to 0, since velocity is proportional to radius, automatically the velocity also should become equal to 0. I hope you are following this thing. So I have only taken first point till here. I'll let you see this point. The summary over here is, in free vortex motion, velocity is inversely proportional to r. In the case of forced vortex motion, velocity is directly proportional to r. Let us move forward to the next difference. Next difference I'm having, let us say, over here I write free vortex motion. Over here I'm having forced vortex motion. Now I'm going to straight away give you the differences, but later on we will be proving these differences also. Fine. So whatever I write over here, this should go into your short notes straight away. Let us see what is the second difference. In the case of free vortex motion, the flow has to be irrotational. The flow is irrotational. The flow is irrotational. Now what happens if the flow is irrotational? This irrotational flow gives you an advantage, and that advantage is, because of irrotational flow, you can say Bernoulli equation can be applied between any point or any set of points, regardless of whether these points are lying on the same streamline or whether they are lying on different streamlines. You can easily apply Bernoulli equation, it should be valid. So free vortex motion has irrotational flow, therefore Bernoulli equation between any two random points is valid. Fine. Now come to forced vortex motion. I hope you can guess what difference you are going to have. Straight away you can say that the flow over here has to be, flow is rotational in nature. Flow is rotational in nature. If the flow is rotational, what does this imply? What does this imply? It implies that you cannot straight away apply Bernoulli equation between any two random points. Then between which points is Bernoulli equation going to be valid? This is the question. I hope you all recall from the limitations of Bernoulli equation we have discussed. In the case of rotational flow, you can apply Bernoulli equation along streamline but not across streamline. So you can say over here, Bernoulli equation can be applied between points lying on same streamlines. That means if I take any two random points, let us say point A and point B, I cannot apply Bernoulli equation. If you tell me that these 2 points are lying on same streamline, fine, I can apply Bernoulli equation then. Let us move further to the last difference over here. The last difference is basically the concept of Bernoulli equation itself. So if I take any two random points A and B, can I write Bernoulli equation over here? Yes. That means I can write over here PA by gamma plus VA square by 2G plus ZA, let us say for point A, has to be equal to PB by gamma plus VB square by 2G plus ZB. So this is a valid equation in the case of free vortex motion. So point A and point B are random points. I have applied Bernoulli equation. Everything is fine over here. Now come over here. Tell me, if A and B are random points, what equation are we going to write? the equation now. Please concentrate. If you remember this, it will be easy for you to solve some questions. The equation over here is PA by gamma minus, please be careful over here, minus VA square by 2G plus ZA has to be equal to PB by gamma minus VB square by 2G, VB square by 2G plus ZB. So in the case of forced vortex motion, when you take the velocity head, you are not going to write plus velocity head, instead you are going to write minus velocity head. This equation is valid between any two random points, regardless of whether these points are lying on same streamline or on different streamlines. So if you are having a case of forced vortex motion, you can straight away use this equation. If you have free vortex motion, you can use this equation. This is regarding the concept of differences between free vortex motion and forced vortex motion. Let me quickly summarize. The first difference was regarding the variation of velocity with radius. In free vortex motion, you had velocity inversely proportional to radius. In forced vortex motion, directly proportional to radius. Second difference was regarding the concept of rotational nature. In free vortex motion, the flow was irrotational. Forced vortex motion happens to be rotational flow. Third difference is regarding the application of Bernoulli equation. In the case of free vortex motion, since the flow is irrotational, you can apply Bernoulli equation between any two random points. Come to forced vortex motion. Since the flow is rotational, you can't directly apply Bernoulli equation between two random points. Rather, you are having this equation over here, which later on will be deriving as well, which says that pressure head minus velocity head plus datum head is going to remain constant between two random points. Now, there is a possibility of a vortex motion which is having a combination of free vortex and forced vortex, and that is known as Rankine vortex motion. It is known as Rankine vortex motion. So how do we define this Rankine vortex motion? We can define it as vortex motion having a combination of free vortex and forced vortex. Free vortex and forced vortex. This is known as Rankine vortex motion. To understand this, let us take an example. Let us say I have a container, quite a big container, let's say. Let us say some container like this. In this container, I am having a fluid filled in. Suppose exactly at the center, I take a paddle wheel. And let us say I rotate this with a constant omega. Let us say omega. Now, till here, till this particular portion, let us say I am having a radius equal to capital R1. In this particular portion, let us say I am having forced vortex motion. In this region, the vortex motion I am having, by the virtue of application of torque on the paddle wheel, the vortex motion over here is forced vortex motion. Beyond this region, again vortex motion is taking place. and that vortex motion happens to be free vortex motion. This vortex motion happens to be free vortex motion. Now let us say I have to draw the graph between velocity and radius. Suppose this is the radial axis. This is the radial axis. The question, let us say, is, let us construct a question over here. Suppose I am supposed to draw the graph between velocity and radius. By velocity, of course, we mean over here tangential velocity. There is no point of normal velocity or radial velocity over here. It does not exist. We have already discussed that. Now, how will the velocity vary with respect to radius? Let us do one thing. Let us break down the problem into two parts. From radius r equal to 0 till r equal to capital R1, I am going to have forced vortex motion. By forced vortex motion, we mean that velocity is directly proportional to radius, which is a straight line graph. So I am supposed to have over here, a graph which is something like this, a straight line graph. This is how the velocity is going to vary. I can write down that this is radius, this is at radius r1, and over here velocity is directly proportional to r. If you look for the slope of this particular graph, we know that velocity is equal to r into omega. Now you see over here, this is dv and this is dr. That means the slope of this graph has to be equal to omega. Moving further, how do we continue from there on? From r equal to r1 onwards, if you go further, you are having free vortex motion. Free vortex motion says velocity is inversely proportional to r. If you are having inverse proportionality, it means you are having a rectangular hyperbola kind of graph over here. Since it is rectangular hyperbola, I am supposed to continue something like this. This is how it is going to take place. And I can mention over here that this is velocity proportional to r power minus 1. Imagine that the boundary is at infinite distance. Then this curve is going to become asymptotic to r. That means it will become tangential but never meet. So this is a case of Rankine vortex motion. Regarding Rankine vortex motion, it is sufficient if you remember that it is a combination of free vortex and forced vortex, and if you know how to draw this kind of graph, then it is quite enough. Let us now talk about the equation of pressure. This is probably the most important point in entire vortex motion topic. And let me tell you, whatever we are discussing in this slide, in this phase of vortex motion, is applicable for both free vortex motion and forced vortex motion. So whatever we discuss has no limitations in vortex motion whatsoever. So let us write down over here equation of pressure, and vortex motion. And let me tell you, while you're writing notes specially for this topic, I would recommend you to don't write anything, just listen to the story, and after I finish, you pause the video once, or if you want, repeat the video and then write down. Okay, let us see. Now first of all, regarding the concept of pressure, we have discussed already in hydrostatic law how to understand the variation of pressure. So let us recall the concepts from hydrostatic law. Suppose you are having some container. Let us say this is a container you are having. In this container, let us say you are having a fluid up to some level. then what you do is you define over here an axis. Let us say this axis is z axis. Then you have mentioned that in the case of hydrostatic law, pressure was just a function of z axis. Pressure was purely a function of z axis. And then we have also found out that the rate of change of pressure with respect to z axis. Okay, we have mentioned, if you remember, dp by dz. I am over here writing dou p by dou z. You will understand later why I am writing so. But we have discussed that this rate of change of pressure with respect to z axis was equal to minus gamma or equal to minus rho g. It was equal to minus rho g. Fine. Now let us see what happens in the case of fluid flowing in a curved path or in vortex motion. Let us again take a container. Let us again take a container over here. And let us say you are having some fluid up till here. And suppose about a particular axis there is some vortex motion taking place. Now I am not saying whether it is free vortex or forced vortex. Let it be any kind of vortex motion, I don't care, because whatever we discuss is valid for every vortex motion. Now once this vortex motion is taking place, please ask yourself that if you take any fluid element over here, which let us say is at a distance of r, from the axis of rotation, how many acceleration terms is it going to experience? First of all, it is going to experience one acceleration in z axis. Let us say this is acceleration in z axis. Apart from this acceleration z axis, since it is experiencing some kind of rotation, what happens is it is going to have one more acceleration, which is centripetal acceleration. And let us say this centripetal acceleration is in this direction, and let me call it as acceleration radial. Now please understand, had I taken the same fluid element over here, then this fluid element would have had only one acceleration, and that was acceleration in z. That's it. It was having only one acceleration. Since it was having acceleration only in z axis, therefore the pressure was varying only with respect to z axis. Now come over here. Over here it is having acceleration in z axis as well as in radial axis. So please tell me that the pressure should vary with respect to which axis? Logic says that the pressure over here is not going to be a function only of z. Apart from z, it is also going to be a function of radial axis. Are you following this thing? This acceleration basically was by the virtue of weight. I hope you understand this thing. It was by the virtue of weight, even though it's not moving down, but it is having a weight component. Over here it is having weight component as well as this component. Therefore it is a function of radial as well as z axis. Now if it is so, I can say that the value of dp has to be equal to dou p by dou r times dr plus dou p by dou z times dz. This is how the equation of pressure in the case of vortex motion is supposed to appear. Now please observe over here, I am having change in pressure in radial axis as well as change in pressure in z axis. I have to find out the result, but luckily for me, I have already done my homework in this matter. What is the value of dou p by dou z? We have already found out from hydrostatic law. That means this part is already done with. We only have to work with this part over here. So my next slide is going to be discussing how pressure is going to vary with respect to radial axis. Once you get that, we can completely finish this equation. And once we get that equation, we can go further deeper into the differences between free vortex and forced vortex motion. Let us see now. Let us say this is a container I'm having, and let us say the fluid level is up till here. I'm choosing a particular axis and I have chosen a fluid element over here. Now please understand, the fluid element I have chosen over here, this element actually is a part of a ring. Let me complete this ring for you to visualize. Please imagine that there's a ring over here, a ring fluid I have chosen. This ring of fluid is having a radial distance of r. I hope you are following this thing. It is having a radial distance of r. It has its own thickness of dr. And let us further say that this is also having some height over here, dz. You can pause the video to visualize this thing. I'm again repeating, a container in which you have a fluid. About a particular axis, vortex motion is taking place. My fluid element of interest is a ring element. A ring is described by its radial distance from the center, thickness of the ring element, height of the ring element. The thickness of the ring element is dr, the height of the ring element is dz. Now what I do is, I try to visualize this ring element from the top. I try to visualize the ring element from the top. So the top view would look something like this. This is a top view, and let us say that from center, if I measure this distance, of course it is going to be r, and this thickness over here is equal to dr. This is a thickness I'm having. I hope all of you are following till here. Now we are going to start the derivation. Please understand, this dr is very, very small. It is extremely small. If you want to imagine how thick is the value of dr, think of it as the thickness of a paper. How thick is it going to be? Very small, is it not? So now, if this dr is very small, let us say I choose a portion of this ring element over here. I choose a portion of ring element over here. Let us say the inner portion is having some area, surface area dA. What would the outer portion have surface area? Please imagine, dr very small, as thick as a paper, so even he should have the area as dA only. So this is also equal to dA and this is also equal to dA. Fine. Let us say the inner portion is experiencing some pressure. Since pressure is compressive, I am going to represent like this. Inner portion experiences some pressure. By the virtue of pressure, it is experiencing some pressure force. The pressure force over here is equal to P times dA. The pressure force is P times dA. And what about this position? Since you are going slightly away in radial direction, and we know that pressure is going to vary in radial direction as well, I am supposed to say that the pressure over here is P plus a small change in P along radial direction whole multiplied to dA. Whole multiplied dA. Now at this moment, if you are finding difficulty to imagine, I'll help you with this. Let us say what I am mentioning over here is this portion over here is representing this part. This portion is representing this part, and this portion is representing this part. So I am saying over here I am going to have some pressure intensity. Let us say it is equal to P, and over here I am supposed to have. Now if there was no vortex motion, then the pressure over here also would be same, because you are at same datum level. Pressure would be same. But since there is vortex motion, since the pressure is supposed to vary with respect to r, the pressure here is equal to P plus some del P with respect to r. I hope you are following this now. Lastly, this element is going to experience a centrifugal force, and that centrifugal force, or let us say it is having, forget about centrifugal force, let us say this element is having an acceleration over here, centripetal acceleration AR, centripetal acceleration AR. I hope this free body diagram for this fluid element is clear. For this fluid element, this is a free body diagram, two forces, one net acceleration we are having. Now let us define some things. First of all, what is the volume of the fluid element we have chosen? The volume is equal to how much? We have mentioned that this is having a surface area dA, and this height is equal to dr. So what volume will be having? You should be having over here dA times dr. This is the volume of the fluid element. If it is a volume, what is supposed to be the differential mass? The differential mass should be density times volume, that is equal to density times dA times dr. Fine. This is a differential mass. Next thing, what about the radial acceleration? This radial acceleration is actually centripetal acceleration. And you know, regarding centripetal acceleration's formula from your basic physics, it is equal to r into omega square. It is equal to r into omega square. Next thing, I'm also going to write down regarding this del P with respect to r. What is the value of del P with respect to r? It is supposed to be equal to dou P by dou r times dr. Now whatever I have written over here is basically fundamental for the equation I'm writing next. The next equation I'm writing over here is, for this elementary portion, summation of force has to be equal to mass times acceleration. Now since I am considering the forces in radial direction, I am supposed to write r also, acceleration also in radial direction. Fine. Let us move further now. Let us say inward direction I am taking positive. You see, conventions are up to you sometimes. When you do these derivations, you can decide what direction is positive. For me, my convenience is inward direction is positive. If inward direction is positive, I'll be writing over here P plus del P with respect to r whole multiplied to dA, whole multiplied dA. This is the force. Now this has to be a negative force, so minus P times dA has to be equal to mass times acceleration. The mass is a very small mass, dm. Acceleration is equal to AR. This is what I have. Now you observe over here, I can cancel off P and P times dA over here and the P times dA over here. These two things have got cancelled off. So what am I remaining over here with? I am remaining over here with this portion, that is dou P by dou R times dr. One moment please. Dou P by dou R times dr times dA has to be equal to differential mass, that is, let us say differential mass only, times acceleration with respect to r. This is a value we are having. I'm going to repeat this in the next slide so as to continue. The equation we were having was dou P by dou R times dr times dA was equal to differential mass times acceleration radial. Now I can continue saying dou P by dou R is equal to dr times, dou P by dou R times dr times dA, left hand side as it is. The value of differential mass we have seen was density times dr times dA, and the value of acceleration was equal to r into omega square, r into omega square. Now let us see what all can be cancelled off. I can cancel off dr over here and dr over here. I can cancel dA and dA over here. If I cancel these things, the equation now comes out to be dou P by dou R is equal to rho omega square times R. This is the result I was looking for. What is this result telling me? This result over here is telling me that the rate of change in pressure with respect to radial axis is equal to density into omega square R, or density into centripetal acceleration. Fine. How will I use this? Let us continue. We know that in the case of vortex motion, be it free vortex or forced vortex, pressure has to vary with respect to radial as well as z-axis. Therefore, the value of dP has to be equal to dou P by dou R times dr plus dou P by dou Z times dz, which further implies that the value of dP is now going to be equal to, from here I can conclude, the value of dP is now going to be equal to dou P by dou R I have got from here. So it is rho omega square R times dr. Dou P by dou Z was equal to minus gamma or minus rho g. So minus rho g times dz. This is the ultimate equation I am looking for. This is the equation I am looking for. So this is how the pressure has to vary in the case of vortex motion, be it free vortex motion or forced vortex motion. Now at this point, let me tell you how I like to remember this. I like to remember this equation as density times acceleration times differential length plus density times acceleration times differential length. So I am having density, acceleration over here is omega square r, differential length I am having is dr. Next I am having density, acceleration over here is equal to minus g, and differential length over here is equal to dz. This is how I like to remember this equation. This is regarding the concept of variation in pressure in the case of not forced, rather vortex motion, be it forced or free. After having derived the equation of pressure for vortex motion, let us apply this equation in the case of free vortex motion and then in the case of forced vortex motion. So let us say I take over here first case, free vortex motion. Free vortex motion. Now regarding free vortex motion, what do we recall? We recall that velocity over here is inversely proportional to r. I hope you all remember this thing. So this implies that I can say velocity is equal to some constant c divided by r. Velocity itself is r omega, is it not? So I can say this implies r times omega, velocity itself is r omega, is equal to c by r, which further implies that the value of omega is going to be equal to c by r square. I am going to use this relationship in the derivation later on. So wherever we see omega, we are going to say C upon R square. Now let us start. The equation we have derived some time back was something like this. dP was equal to rho omega square into R times dr minus rho g times dz. This was the equation we were having. Now what I am going to do is, in place of omega, I am going to put this value. So what do I get now? I get over here dP is equal to rho into omega square is supposed to be equal to C square upon R power 4 times R times dr minus rho g times dz. Now if I simplify this thing, I am going to get dP is equal to rho into C square multiplied to R power minus 3 times dr minus rho g times dz. This is the equation I am having, differential equation. Now what I am going to do is, I am going to integrate this equation by choosing two random points, let us say point 1 and point 2 in the fluid flow, in the free vortex motion fluid flow. So let us say I integrate this equation. I will put integral over here. Rho and C square, both of them are constant, integral over here. Rho and G constant, so integral over here. Between point 1 and point 2, so therefore at point 1 let us say Z is equal to Z1, R is equal to R1, P is equal to P1. At point 2 Z is equal to Z2, R equal to R2, let us say, P is equal to P2, let us say. This is how I integrate. Now this is going to give me, the left hand side is going to be P2 minus P1 is equal to rho C square as it is. Rho C square as it is. Now this has to multiply with R power minus 3 R dr. Integral is going to be equal to how much? It is going to be R power minus 2 divided by minus 2. Is it not? It is supposed to be R power minus 2 divided by minus 2, ranging from R1 to R2, fine, minus rho g into Z2 minus Z1. This is the value we are having over here. Now please understand that I am having a minus sign over here. If I remove this minus sign, I can shuffle the limits. I can interchange these limits. So if I do so, I am going to get the equation as P2 minus P1 is equal to rho into C square multiplied to, now you see I am interchanging the limits, therefore R1 square upon 2 minus R2 square upon 2, Now minus I am writing as plus rho into G times Z1 minus Z2. This is the equation I am having. In the next slide I am going to start again with this equation. So I have over here P2 minus P1 is equal to rho C square multiplied to, if you remember, it was R1 square by 2 minus R2 square by 2 plus rho G times Z1 minus Z2. This is the equation. Now let us take terms belonging to point 1 on one side and point 2 on the other side. So I am going to get over here P2 Now I am having rho c square r power, one second, I am supposed to have minus 2 over here, I am sorry. Rho c square r power minus 2 for point 2 with a negative. So if it comes over here, I am going to have rho c square r power minus 2 whole divided by 2. Fine. Whole divided by 2. This is for R2, right? Next, if this also comes on the left hand side, I am having plus rho g z2. Fine. This has to be equal to P1 plus rho c square r power minus 2 for point 1 by 2 plus rho g z1. This is the equation. Now recall, in the previous slide we have seen that the value of v is equal to c into r power minus 1. This was the value of v. If this is a value of v, then this is basically representing v square. So I can write over here P2 plus rho V2 square by 2 plus rho GZ2 has to be equal to P1 plus rho V1 square by 2 plus rho GZ1. This is the equation. Now let us say I divide this entire equation, dividing this by rho g. If I divide this entire equation by rho g, the result is now going to be, let us take right hand side first. So I am going to have P1 by gamma plus V1 square by 2g plus Z1 has to be equal to P2 by gamma plus V2 square by 2g plus Z2. This is the ultimate equation we are going to get once we divide it by rho g. This is the equation we are having. Now what is this equation telling you basically? It is telling that in the case of free vortex motion, if you take any two random points, point 1 and point 2, then Bernoulli equation is valid between these two random points. If Bernoulli equation is valid between these two random points, it basically means the flow has to be irrotational. So I can say over here, therefore the flow is irrotational. Therefore the flow is irrotational. Moving further, let us say we apply the same equation in the case of forced vortex motion. Let us say I am taking B bit now, forced vortex motion. Forced vortex motion. Forced vortex motion. Now recall what all things we have discussed in forced vortex motion. We have said that in the case of forced vortex motion, omega is equal to constant. So straight away we are having omega constant over here. So whenever you see omega in this equation, treat it as omega itself. And the value of velocity, of course, has to be equal to r into omega. This is something which is very fundamental. Chaliye, let us now start the differential equation. Differential equation says dP is equal to rho omega square r times dr minus rho g times dz. This is the differential equation we are having. Let us integrate this by taking any two random points. Let us say integral here, integral here, integral here. Any two random points, let us say point 1 and point 2 are the two random points I am having. So now for point 1 I can say z is equal to z1, r r1, p p1. For point 2 z is equal to z2, r is equal to r2, p is equal to p2. Now you see, since omega was constant, I don't have to manipulate omega. I just as it is. Fine. If I integrate this thing, what am I going to get? If I integrate over here, I am going to get P2 minus P1 on the left hand side has to be equal to rho omega square multiplied to R2 square by 2 minus R1 square by 2 minus rho g into Z2 minus Z1. This is the equation we are having. Fine. Let us do one thing. Let's take terms belonging to the point 1 on one side and point 2 on the other side. So what have we got? We have got over here P2. Fine. Now look over here. Rho omega square R2 square by 2 is positive over here. If it comes on the left hand side, it has to be negative. So minus rho omega square R2 square by 2. Rho g Z2 is negative over here. If it comes on the left hand side, it has to be positive. So plus rho g Z2 has to be equal to. Now P1 was negative, so it goes over there, positive. Rho omega square R1 square by 2 negative, remains negative over here. Rho omega square R1 square by 2 remains negative over here. And rho g Z1 is positive, so plus rho g Z1 over here. Now next slide, what I am going to do is, I am going to write the same thing, only differences. We know that omega times r is equal to velocity. Therefore, omega square r square I am going to write as v square. You are seeing omega square r square over here. You are seeing omega square r square over here. These will be converted into velocity. So let us say, now I am writing, I am having over here P2 plus, I am sorry, not plus, P2 minus rho V2 square by 2 plus rho G Z1, sorry, rho G Z2, I am sorry, rho G Z2 has to be equal to P1 minus rho V1 square by 2 plus rho G Z1. This is the equation. Again, let us do one thing. Let us divide this by rho G or gamma. If I divide the entire thing by gamma and I write terms belonging to the point 1 on left hand side and point 2 on the right hand side, I am going to have P1 by gamma. Now please be careful over here. You do not have plus, you have minus. Minus V1 square by 2G plus Z1 has to be equal to P2 by gamma. Again you are having over here minus V2 square by 2G plus Z2. This is the ultimate equation we are getting in the case of forced vortex motion. This is the equation we are obtaining in the case of forced vortex motion. Now what does this imply? It implies that since Bernoulli equation is not valid between any two random points in forced vortex motion, it means that you are having rotational flow. So I can conclude over here by saying, therefore the flow is rotational. Therefore the flow is rotational. This is regarding application of the equation of pressure in the case of free vortex motion as well as in the case of forced vortex motion. Now, after having discussed regarding the equation of pressure in free vortex motion and forced vortex motion, we are now going to concentrate only on forced vortex motion. Forced vortex motion is very important for us, and many times questions have appeared in examination from forced vortex motion. The reason why forced vortex motion is important is, if you recall, there was a topic by the name rigid body motion in which you are having rotation also, that we did not discuss. That is what we are discussing now. Please remember that forced vortex motion, forced vortex motion happens to be a part of rigid body motion. It is a part of rigid body motion. It's a part of rigid body motion. Now, since it's a part of rigid body motion, we have to conclude some more results in the case of forced vortex motion. The first result we are discussing right now is the equation of isobar. The equation of isobar. Now, what do you mean by isobar? Mechanical people know very well what isobar is. Civil people, you might have heard of isobar in your 11th, 12th class. If you have forgotten, recall isobar basically means line of constant pressure. Line of constant pressure. Isobar means line of constant pressure. So now we are going to look at the equation of isobar in the case of forced vortex motion. Let us see. Look at this diagram over here. In this diagram you are observing that there is a container in which there is some vortex motion created, forced vortex motion is created, and the interface which was previously horizontal has taken a new shape. Okay. If I can get the equation of this particular curve, then that equation is true for the equation of isobar also. The reason is, throughout this particular line, the value of gauge pressure is equal to 0. Throughout this particular line, the value of gauge pressure is 0. This itself is my isobar. This itself is an isobar. The other isobars are going to be curves which are exactly parallel to this one. So free surface itself is behaving as isobar. Let us do one thing. Let us take 2 points of interest. The first point I am considering over here is this particular point. This point, let us say, is point A, denoted by R equal to 0 and Z also is equal to 0. R equal to 0 and Z equal to 0. Let us say this is another random point I am having on the isobar. Let us say this point is point B. It is denoted by R equal to R and Z is equal to H. Z is equal to H. That basically means that, this height over here is equal to H, and this radius over here, from here till here, this radius is equal to R. If I can establish a relationship between this R and H, then I have found out the equation of isobar. Let us see now. We know that in the case of forced vortex motion, the value of PA by gamma minus VA square by 2G plus ZA has to be equal to PB by gamma minus Vb square by 2g plus Zb. Okay, this is an equation we have discussed already. Okay, now in this equation, since I am saying that A and B are lying on isobar, it means that this term has to be equal to this term. Both cancel off. If both these terms cancel off, then I can say that the value of ZB, the value of ZB minus ZA, ZB minus ZA has to be equal to VB square minus VA square whole divided by 2G. This is the equation we are having. Now what is ZB minus ZA? You can observe from the diagram and tell me what is the value of ZB minus ZA. ZB is equal to H, ZA equal to 0. That means this is equal to H. Next, what is the value of VB? VB has to be equal to omega into RB whole square. This is the value of VB square. Likewise, VA has to be equal to omega into VA. Then you put whole square over here, whole divided by 2G. Whole divided by 2G. We already know that the value of R, I'm sorry, I made a mistake over here. Let me correct it. It's a printing mistake. This is supposed to be omega times RA. Omega times RA over here. Fine. Now we already know that the value of RA is equal to 0. That means this entire term becomes equal to 0. Fine. If it becomes equal to 0 and RB is equal to R, this ultimately implies that H has to be equal to omega square R square by 2G. This is the equation of isobar we are having. H is equal to omega square R square divided by 2G. Now please observe over here. You are seeing that the value of omega is a constant, 2 is a constant, G also is a constant. If all these things are constant, I can conclude from here that the value of H is proportional to R square. H is proportional to R square. Now you see that if H is proportional to R square, what does it imply? What kind of curve is it? Is it circular curve? No, it is going to be parabolic curve. Therefore, isobar in the case of forced vortex motion have to be parabolic in nature. Have to be parabolic in nature. Please remember these things. Very important in the case of 1-mark questions as well. Isobars in the case of forced vortex motion have to be parabolic in nature. And the relationship also is very important, very simple relationship. It is given by H is equal to R square omega square by 2G. Previously we have discussed the first result in the case of forced vortex motion, and that was the value of H in terms of R, or you can say equation of isobar. The next thing we are going to discuss is something known as volume of paraboloid. Volume of paraboloid. Volume of paraboloid. Now the question is, what is this paraboloid over here? What is this paraboloid over here? I can define this paraboloid. I can define paraboloid as volume of revolution, volume of revolution of a parabola. Paraboloid is volume of revolution of a parabola. Now which parabola are we speaking about over here? Please observe that this is forming some kind of a parabola. The line of constant pressure isobar over here, or the free surface is forming a parabola. Now this parabola is having certain volume of revolution. That means if you can imagine that this parabola in 360 degrees, a 3D image if you imagine, it is going to create some kind of a cup shape, a cup or a bowl shape it is creating, and that particular 3D shape is known as our paraboloid. So now we have to identify how much is the volume of this paraboloid. Let us see. Imagine this is a paraboloid we are having over here, such that its complete radius is equal to capital R. Its complete height is equal to capital H. My aim over here is to find out the volume of a paraboloid as a function of capital R and capital H. This is my aim over here. Before I start proving this or deriving this thing, I want you to do some imagination over here. The imagination you are supposed to do is, please imagine that this paraboloid is completely fitting inside a cylinder. This paraboloid is completely fitting inside a cylinder such that the cylinder also is having a radius of capital R, such that the cylinder also is having a height of capital H. So the paraboloid is fitting inside a cylinder of radius capital R and height capital H. This cylinder over here is called as circumscribing cylinder. It is called as circumscribing cylinder. It is called as circumscribing cylinder. Now why am I mentioning this thing? The reason is volume of a paraboloid will have a relationship with the volume of circumscribing cylinder. Now at this moment, tell me what is the volume of circumscribing cylinder? Very simple. Circumscribing cylinder's volume has to be equal to pi r square times h. Is it not? This cylinder is going to have a volume of pi r square into h. Now the volume of a paraboloid is going to be a portion of pi r square h. How much portion? We are going to see now. That is a very simple result. You can easily remember it. Let us say that I am having a paraboloid over here. Let us say this is a paraboloid I am having. Complete radius is capital R, complete height is equal to capital H. Now what I do is, in this paraboloid, I am going to take a very, very small portion. Suppose I am taking a small portion over here. Suppose this is having certain radius R and this portion is having a height equal to, dh, let us say. So I am taking a disk over here. Please imagine this disk. A solid disk I am choosing over here, and this disk is having a radius small r and height equal to dh. Now what I'll do is, I'll say the differential volume of this paraboloid, differential volume is equal to pi small r square times dh. I have got the differential volume. If I integrate this, put in the suitable limits, I should get the value of complete volume. Fine. But there's a small problem. That small problem is R is a variable and H also is a variable. I am having the differential term which is not in terms of variable R. So somehow I am supposed to convert dH in terms of dr. Okay. So substitution method we are going to use over here. So what I do is, I recall that H can be written as R square omega square by 2g. If so, the value of dH has to be equal to 2 times r into omega square by 2g times dr. 2 and 2 cancel off over here. So let us say 2 cancels off with 2 over here. 2 cancels off with 2. Now, once I have this value of dH, I can say now that the differential volume of the paraboloid's disk is equal to pi r square multiplied to, in place of dH I am going to put this thing, so it is r into omega square by g times dr. This is a value. Now complete volume is supposed to be integral of this thing. It is supposed to be the integral. So let me take all the terms which are constant aside. So I have over here pi omega square by g aside. I am going to integrate r cube times dr. And what are the limits? The limit is ranging over here, the value of r equal to 0, over here the value of r equal to capital R. So limit is from r equal to 0 to r equal to capital R. From here I get that the volume has to be equal to pi omega square by g times r power 4 divided by 4. This is the answer. But I can't remember that. I don't want to remember that also. Okay. I have to get a refined answer over here. So what do? Let us say this volume is equal to, let me rearrange this now. It is equal to pi into r square. I have taken pi r square aside, multiplied to omega square r square. Omega square r square. Now you see the numerator has been set. Pi r square omega square r square is the numerator. Fine. By 4g I am having. Let us say by 2 and by 2g I put over here. No problem at all. Now what you observe over here is this part omega square r square by 2g is basically equal to the complete height over here h, that is this height h over here. It is equal to omega square r square by 2g. So now what happens? The volume now becomes equal to half of pi r square h. Now this is something which I can remember easily. So the value of volume of paraboloid is equal to half of pi r square h. What is it telling me? Half of pi r square h is equal to how much? I can say this is equal to half the volume of, what is this? This is the volume of circumscribing cylinder. So I can say volume of paraboloid has to be equal to half the volume of circumscribing cylinder. Very, very simple result. Please remember this thing. Volume of a paraboloid is equal to half the volume of circumscribing cylinder. That is equal to half pi r square h. With this, we conclude the concept of rigid body motion in rotation. Let us start the concept of momentum equation and applications. Last chapter seen was energy equation. Now we are looking at momentum equations. Momentum equation and application. Now first of all, let us understand the concept of momentum, and let us also recall how momentum is related to force. We know that force is equal to mass times acceleration. Force is equal to mass times acceleration, and force also is a vector quantity. Acceleration also is a vector quantity. I can also write this as force is equal to m into dv upon dt. So let us say this is one more way I can write force. Further, I can say that if I take this mass inside, then the equation becomes force is equal to d by dt of mv, d by dt of mv. So we have over here F equal to d by dt of mv. This mv term is a vector quantity. Mv term over here is a vector quantity, and it is known as linear momentum. It is known as linear momentum. It is known as linear momentum. Furthermore, let me tell you one more thing. This linear momentum is represented by letter capital P. This is how we represent linear momentum. Now this is all something which you have studied in your basic physics. From here you can also define that force has to be equal to rate of change in linear momentum. So I can basically say that this equation over here, in words I can write it as rate of change in linear momentum, rate of change in linear momentum is known as force. Rate of change in linear momentum is known as force. As a matter of fact, from this equation there is one more equation derived, very famous equation known as impulse momentum equation. There is an equation known as impulse momentum equation. Impulse momentum equation. Now what is this impulse momentum equation? What I am going to do is, this equation I am going to rewrite as force times dt. Force times dt is equal to dmv. All these things are from basic physics. You might have seen this in your mechanics as well. Force times dt is equal to dmv. This term over here, force times dt, is known as impulse. It is known as impulse. Now this impulse basically means the product of a force with the duration over which the force is acting. This is impulse. And this dmv over here is change in linear momentum. It is change in linear momentum. Change in linear momentum. So impulse has to be equal to change in linear momentum. So till here whatever you have seen has nothing to do with fluid mechanics. It is only the basics of mechanics, which is I am trying to introduce the concept of momentum over here. Now what we'll do next is we will see how this equation can be extended to understand the concept of forces acting in the case of fluid flow. Now let us see how to apply the impulse momentum equation in our subject of fluid mechanics. Please try to understand where our subject is differing from mechanics. I always emphasize on this thing that if you understand how mechanics and fluid mechanics are different, then it will be easier for you to extend the ideas of mechanics. You see, when it comes to mechanics, you are having a particular body or a system of bodies and you are exerting some forces over there. But the problem with fluid mechanics, you do not have a particular amount of body. There is a continuous flow in our body, that is fluid. It is continuously flowing. So the body is not a constant. The mass is not basically a constant. Probably mass flux might be a constant. That is why you see in our subject we are not interested in mass of the body, we are rather interested in mass flux. Similarly, I want you to tell beforehand that we won't be interested in momentum of a particular system. We would rather be interested in the rate of momentum. Let us see now. I'm having over here an equation which says that force is equal to dmv by dt. This is the equation I'm having. In general, what happens for your mechanics is mass happens to be a constant, it comes out, and velocity takes the variation with respect to time. This is what happens in mechanics. But now in our subject, what is happening is, since mass is not a particular value or not a constant value, we are going to give rate of time concept to mass. From here what we get is force is equal to d of m dot into velocity, d of m dot into velocity, where this is a vector quantity as well as this over here is a vector quantity. Force over here, of course we know what force is. This m dot v over here, this term m dot v over here, m dot v over here is known as momentum flux. It is known as momentum flux. It is known as momentum flux. So from here I can say that force is equal to change in momentum flux. Change in momentum flux. Change in momentum flux. So this is how we are going to define force in the case of fluid mechanics. Now this momentum flux, I can say, if I want to write this equation in a particular axis, for example, let us say I want to look at the net force in x-axis, then I can say that, let us say, summation of force in x-axis has to be equal to delta m dot into velocity in x-axis, which basically means that it is equal to m dot into velocity in x final minus m dot into velocity in x initial. This would be the equation in the case of x-axis. Likewise, if I have any direction, let us say k-axis, then I can write for any direction summation of force, let us say in some k-axis, is equal to delta m dot into velocity in k-axis, which further is equal to m dot into velocity in k-axis final minus m dot into velocity in k-axis initial into k-axis initial. This would be the equation for momentum flux in any axis in the case of fluid mechanics. Now, before we start using the equation of momentum flux, you have to understand that there is a part of analyzing the fluid flow also required. Then we are going to write the equation. If you are finding it difficult to understand this, just recall that in mechanics also, when you are solving a question, before writing Newton's second law equations and all, you draw something known as free body diagram. This free body diagram was letting you visualize how the forces were acting and what the net result of these forces. Something similar in our subject also is required. The free body diagram kind of modeling in our subject is known as control volume. It is known as control volume. Control volume. How do we define this control volume? Definition. See, control volume is basically a fictional volume chosen in a fluid for the sake of analysis. In this analysis, we are talking about forces. So in a way, you can say the fictional volume, which might be static or might be moving, that is chosen in a fluid flow, that on which the force interactions are taking place. So let us say I define this as the volume chosen in a fluid flow, analysis, for analysis. This is known as control volume. Right now, the analysis we are talking about is force interactions. So you can say that the fictional volume chosen in a fluid flow, you can replace this part by the statement I am writing over, on which the force interactions are taking place. The force interactions take place. The force interactions take place. So this kind of volume is known as control volume. Further, there is one more thing you are supposed to, an important thing, that is the boundary of control volume. The boundary of control volume, is known as control surface. The boundary of control volume is known as control surface. Now this control volume is going to serve the purpose of free body diagram in our subject. Now before drawing this control volume for an example problem, I would want you to know some rules or some extra points regarding this control volume. Let us see these points. It will be helpful to draw control volume once you know these points. Let us start with the first point over here. Regarding control volume, the first thing you are supposed to know is a control volume can be static or moving. Both these things are possible. It is possible for a control volume to be static or moving, but it should not have any acceleration. It should not have acceleration. It should not have acceleration. This is the first point. So please don't think that the control volume is going to be always static. It can as well be moving. I'll give you an example where you're having a static control volume and a moving control volume. You'll be seeing this later in impact of jets also. Imagine that a jet of liquid is striking on a particular plate. If the plate is fixed, then the region of volume you are choosing over here is a static amount. It is also possible that the plate keeps on moving forward because of the force exerted. So in that case, what happens? The control volume at first instant would be over here, next instant probably over here, next instant over here, likewise. So control volume might be static or might be moving continuously. But over here you have to make a note that you are not supposed to have acceleration. You are not supposed to have acceleration. This is the first point we are having. Second point regarding control volume. Second point regarding control volume. Second point says that whenever you draw a control volume, it can have any shape and any size. So control volume can have any shape or size. Again, you are having a but clause over here, but it should be drawn in such a way, it should be drawn in such a way that the velocities, by velocities I mean over here initial and final, the velocities which are initial velocities and final velocities are supposed to be perpendicular to the control surface, perpendicular to the control surface. This is the second point we are having. So don't think that a control volume is supposed to have a particular shape only, not required. It is an arbitrary kind of volume you are yourself choosing. And this volume can have any shape and size. But see to it that the volume you are choosing is going to have, such a way you are drawing it that the velocities of entry and exit are supposed to be perpendicular to control surface. This is the second point you are having. Now comes the third point. The third point regarding control volume is, you see, the control volume can sometimes come with some supports. Let us say you are having a nozzle. To the nozzle you would have some kind of clamping support. Similarly, any kind of device you are having, you might be having some support. What you are supposed to do to these supports? Now think back from your concept of free body diagram. In free body diagram you might have studied that whenever there is a support, you are going to replace the support by equivalent reactions. Exactly same thing has to be done in the case of control volume as well. So third point I have over here says that the supports in a control volume should be replaced by equivalent reactions. So this is something which is very, very natural to you. Actually, it comes from the concept of free body diagram itself. So keep these three things in mind and then you will be able to draw control volume. Now since this might be a new topic for you, so what I'm going to do is I will take an example kind of question and draw the control volume and write the equations. Okay, let us see now an example question over here. Imagine that you are having a passage which is something like this. A passage which is something like this. Let us say there is some passage like this. The cross section area over here, let us say, is equal to, cross section area over here is equal to A1. The pressure over here is equal to P1. The cross section area over here is equal to A2. The pressure here is equal to P2. And let us say this angle is certain angle theta over here. Now let us say through this particular piping passage, there is a fluid flowing from here. The fluid is flowing from here. Let us say it has certain discharge Q. The discharge over here is Q. Furthermore, using a support, you are having some kind of support to hold this particular passage over here. The question asked over here, let us say, if the density of the fluid is rho, the question asked over here is find the net reaction at the support, find the net reaction at the support. This is a question, let us say, asked. How do you solve this kind of question? Okay, again you see the fluid is continuously flowing. You are realizing that it is different from your basic mechanics, because in the case of basic mechanics you would have a particular mass on which forces would be acting. That would have been easy, but over here mass is continuously flowing. So how do we approach this kind of question? First thing you are supposed to do is you are supposed to decide what is the control volume over here. Let us decide the control volume. I see the entry velocity is from this particular section and the fluid is exiting from here. So velocity is from here. So I can choose this entire portion. Let us say I can choose this entire portion over here as my control volume portion. This entire portion as control volume portion. So if I draw my control volume, now look over here, this is a control volume I'm drawing. Let us say this is the control volume I'm having over here. Let us say this is a control volume I'm having. Now next thing, after having chosen control volume, it is time for you to denote all the forces acting on this control volume. The first thing I'm going to start with are reactions. You see, I am supposed to eliminate off this support. I'm going to eliminate the support now. So if I eliminate the support, let us say I get two reactions over here. One, let us say, is a reaction in x-axis. One, let us say, is a reaction in y-axis. A reaction in y-axis. Okay, two reactions I'm having over here. Now, you might worry about the direction sense. See, generally in these kind of direction sense, you assume something. Once you assume, if you get a wrong answer, the answer itself will correct. If imagine at the end I get the value of Rx as something negative of something. Fine. Negative of something basically says that same magnitude but opposite direction, that is assumed. Anyway, let us move further. What are the other forces acting on this? The other forces acting over here are the pressure force at section 1. At section 1, I am supposed to talk about the pressure forces. Now, the pressure force, remember one thing regarding pressure force, it is supposed to be always compressive in nature. That means at this section, the pressure force is going to act in this direction. Let us say it is equal to P1 A1. This is the pressure force I'm having. Now, if the pressure force is compressive in nature, help me with this. How should the pressure force be acting at section 2? How should the pressure force be acting at section 2? It should be acting again in compressive manner. Therefore, let us say it is equal to P2 times A2, let us say. This is how the pressure force is acting. Next thing, I am supposed to also show the velocities over here. Now, I know that the velocity over here is in this direction. So let us say this is velocity V1. Likewise, I am having velocity over here in this direction. This is the velocity V2. Furthermore, we also know this angle. This angle is equal to theta. I am done with my control volume diagram. What do I have to do next? Next thing I have to do is I have to write the equations. Okay. Let us see how to write the equations. Let us write the equations now. Let us start with equation in x-axis first of all. Equation in x-axis. For that purpose, what I do is I take a convention. Let us say this is positive x-axis and this over here is positive y-axis. Having taken this convention, let me start writing the equation. Summation of force in x-axis according to our momentum equation has to be equal to delta m dot times velocity in x-axis. That is equal to m dot into velocity in x-axis final. By final, in this case I mean section 2, minus m dot into velocity in x-axis initial. By initial I mean over here section 1. Now this is the value of summation of force in x. This is what we know from the equation of force and momentum flux. What do we do next? Next thing, we are supposed to talk about what are the forces in x-axis. If you observe over here, there are 3 forces contributing towards x-axis. The first force over here is this P1 A1 itself. The second force over here is Rx. The third force over here would be the component of P2 A2. These 3 forces are going to contribute in x-axis. So now I can write over here by taking the convention of positive x. I can write this value left hand side over here. Please be with me. Understand this thing. This value is equal to P1 A1 is positive. Look at Rx. Rx is in negative direction, therefore minus Rx. Look at P2 A2. P2 A2 is not completely in x. It is having a component in x-axis. It has a certain component in x-axis. What component would it have in x-axis? What component would it have in x-axis? Now if you see over here, this angle would again be equal to angle theta. So I am having over here plus P2A2 into cos theta. P2A2 into cos theta. This would be the value of left hand side. Fine. I am done with my left hand side now. Has to be equal to. Come to right hand side over here. If you observe m dot and m dot at section 2 and section 1 both of them are actually same, because I do not see that the fluid is moving out from any passage over here apart from section 2, is it not? It is moving from section 1 and going out to section 2. There is no accumulation taking place. So m dot at section 1 and section 2 are same. So I can say m dot common to m dot common to. Now what is a velocity in x final? Please observe this thing. Velocity in x final basically means you are supposed to take over here, you are supposed to take the component of velocity over here. Please observe, if this angle is theta, this angle again is equal to theta. It is again equal to theta. Moreover, it is in the negative direction. So I can write over here, excuse me, I can write over here, if this angle also is equal to theta, I can write over here minus of V2 times cos theta, minus of V2 cos theta. Furthermore, minus again from here, Vx initial is equal to how much? If you observe, Vx initial is purely in x-axis. So I have over here V1. This is the value. Now, our question was regarding the value of Rx. So I can write the value of Rx from here would be equal to how much? Rx would be equal to, let us say Rx I am taking on one side, rest of the things on the other side. It would be equal to P1 A1 plus P2 A2 times cos theta, P2 A2 times cos theta. Next thing, plus m dot into V2 cos theta, V2 cos theta plus V1, V2 cos theta plus V1. This would be the value of Rx in this particular case. In this setup, this would be the value of Rx. Similarly, I would want you to pause the video right now and try the value of Ry also. Fine. Once you have finished, then you watch me how I have done the value of Ry. Let us start. Let us start the value of Ry now. Let us start the value of Ry. To get the value of Ry, again look at the control volume diagram. Look at the control volume diagram. I can start the equation by saying sigma Fy is equal to delta m dot into velocity in y-axis, which implies sigma Fy has to be equal to m dot into velocity in y final section means section 2 minus m dot into velocity in y initial section means section 1 over here. This would be the equation. Now again I have to write the value of summation of force in y-axis. What are the various forces in y-axis? This time around P1A1 has no contribution whatsoever in y-axis. In y-axis I am only going to have Ry and a component of P2A2 contributing. So if I look over here, Ry is positive. Ry, I have chosen positive y-axis. Ry is positive. P2A2, if you observe over here, it is going to have a downward component, therefore negative of P2A2 into, if you go by trigonometry, basic trigonometry, it is going to be sine theta. Fine. This is the value for the left hand side. It should be equal to m dot is common again. The reason is both these sections are having same value of m dot. One more thing, if you observe, the value of initial velocity is completely in x-axis. That means even this is not contributing, so I can cancel this completely. So I'm only left with m dot into velocity in y-axis. If you observe over here, what is the velocity in y-axis? Please observe. The component in y is this component, that is equal to v2 sine theta. So I can write over here m dot times v2 sine theta. This would be the value. Now from here I can further say that the value of ry is equal to p2 a2 sine theta, p2 a2 sine theta plus m dot into v2 sine theta. This would be the value of ry. I hope you are getting this value. Once you get both these values, let us say some numerical values were there. Once you get both these values, then what you can further say is, you can further say that the net reaction force, let us say net reaction force, suppose, is equal to capital R. How much would that be equal to? It would be equal to root over of Rx square plus Ry square. This would be the value of reaction. Furthermore, if you wish to say that the net reaction is R like this, it is at an angle alpha. What would be the value of this angle alpha? The value of angle alpha would then be equal to tan inverse of Ry upon Rx. So this is how you are going to use momentum flux equation and control volume diagram in order to find out the forces whenever a fluid flow takes place. The next thing we are going to see is a correction factor. I hope you recall that in previous chapter we came across a correction factor known as kinetic energy correction factor. Now we are going to talk about something known as momentum flux correction factor. Momentum flux correction factor. Correction factor. This momentum flux correction factor is represented by beta. Kinetic energy correction factor was represented by alpha. This is by beta. Let us first of all understand why do we need this thing. You see, in general, when I ask you what is the value of momentum flux, let us say, if anyone asks you the value of momentum flux, then a general answer over here would be momentum flux is equal to m dot times velocity. Now, which velocity is this? If you observe over here, this velocity v over here is average velocity of flow. It is average velocity of flow through a particular pipe or a passage or something. It is the average velocity of flow. Now you have calculated the value of momentum flux by considering average velocity of flow. This would create error if the velocity profile is non-uniform. So I can say that this particular value over here creates an error. It creates an error if the velocity profile is non-uniform. If the velocity profile is non-uniform. So in the case of non-uniform velocity profile, we are having an error induced over here. We have seen something similar in the case of kinetic head also. There was an error induced whenever the velocity profile is non-uniform. So now let us see how to develop the equation of this this momentum flux correction factor. Let us say you have a particular passage. Let us say this is a cross-sectional view over here, okay, through which the flow is taking place. Fine. The entire area over here is equal to capital A and the average velocity over here is equal to V. So I can say that momentum flux, which we assume it is equal to m dot into V. This is what we are assuming is. But in reality, the momentum flux is supposed to be equal to correction factor times m dot into V. So say this is the actual momentum flux. So this over here, this over here is the actual momentum flux. Actual momentum flux. Momentum flux. Before we were having the idea of beta, we thought momentum flux was m to V. If we multiply this m dot into V by the correction factor, then we get the value of actual momentum flux. Now, differential actual momentum flux would be equal to how much? Just imagine this thing, that you are having a small area over here. Let us say you have chosen a small area over here. This small area, let us say, is equal to dA. This is a small area dA. Suppose something like this. A small dA I have chosen over here. dA. And let us say the local velocity over here is equal to u. u over here is the local velocity in the small area dA. So I can say the value of differential actual momentum flux, I can say differential actual momentum flux, momentum flux. So I'm choosing a small area. In this small area, the momentum flux itself is going to be the actual momentum flux over here. How much is this going to be equal to? Differential actual momentum flux would be equal to differential m dot times the local velocity over here. What would the value of differential m dot be equal to? This differential m dot would be equal to, it would be equal to density into differential area times velocity. This is differential, multiply again with u. This would be the value. So I can say differential actual momentum flux is equal to density times differential area times u square. This is the value. Now I can further say that actual momentum flux for the complete passage, actual momentum flux for the complete passage would be equal to how much? Integral of this thing, it would be equal to integral of density times area times u square over the entire area A. This would be the value. Let us do one thing. Let us save this as some equation number 1 and this as some equation number 2. Both of them are representing actual momentum flux. So let us equate both of them. If I equate both of them, if I say equation 1 and 2, both of them are same, then what do I get from there? I get from here beta times m dot into v is equal to integral of density times u square times differential area over the entire area A. Furthermore, I know that this m dot itself is equal to density into area into velocity times velocity, and beta over here has to be equal to, density is constant, so take density outside, integral of u square times dA. I can cancel over here density and density. Therefore, I have over here beta times area into v square has to be equal to integral of u square times dA over the entire area A. From here I can conclude that the value of beta has to be equal to, that is momentum flux correction factor has to be equal to 1 upon AV square into integral of u square times dA over the entire area A. This is going to be the value of momentum flux correction factor. This is the value of momentum flux correction factor. Now at this moment I want you to recall the value of alpha. What was alpha? Kinetic energy correction factor. Very small difference was present in alpha, and that is you are having 1 by AV cube integral of u cube times dA. The power over here is u square, over there it is going to be u cube. Similarly, the power over here is v square, over here it is v cube. So kinetic energy correction factor would be this thing, momentum flux correction factor would be this thing. Very simple equations. Again, the integral is over the entire area A over here. Now regarding some standard results of this momentum flux correction factor, standard results of momentum flux correction factor. I am going to take two cases. First case, let us see. First case, when you are having uniform velocity profile, uniform velocity profile. In the case of uniform velocity profile, there is no error in the momentum flux. If there is no error, there is no need to multiply beta, or you can say if you are multiplying, let us say beta itself is equal to 1. Multiplying by 1 is as good as multiplying by nothing, is it not? So beta over here is equal to 1, and let us recall that the value of alpha also was equal to 1 over here. Second thing, in the case of non-uniform velocity profile, non-uniform velocity profile. In the case of non-uniform velocity profile, beta of course has to be greater than 1, and let me recall also alpha also has to be greater than 1. If anyone asks you the inequality between alpha and beta, please remember that in this case alpha will be greater than beta. Remember, if you are having a non-uniform velocity profile, kinetic energy correction factor is supposed to be greater than momentum flux correction factor. One more case, let us say, standard case, which you have to remember, and questions from here can appear. It is, what in the case of laminar flow through pipes? If you are having a fully developed laminar flow through pipe, laminar flow through pipe. In such a case, the value of beta is equal to 4 by 3. Remember this value. Beta is equal to 4 by 3, and I hope you remember alpha was equal to 2 over here. Again, you can check alpha is greater than beta. So this is regarding the concept of momentum flux correction factor. Please do not use it unless the question asks you to use in GATE, in IES or any examination. Mostly they won't ask you to use. When it comes to IES conventional examination, that is when they ask you to use the value of alpha and beta. Only then use it. Fine. So if you are writing the equation using momentum flux correction factor, the equation of force now changes as summation of force has to be equal to delta beta m dot into velocity. Let us say you're talking about some direction k, then this is in some direction k. That means summation of force has to be equal to beta into m dot into velocity final minus beta into m dot into velocity initial. Again, if you have a particular direction k, then you are supposed to take velocities in k over here. And again, the values of beta need not be same over here. They might be different. Let us say your initial section is having a laminar flow, final section, for example, is having a turbulent flow. Of course, the value of betas will change then. So betas need not be same over here. If betas are included, then the equation changes in this form. After having seen the concept of momentum equation, we are going to start a very important topic. And this topic you'll be finding questions from here very frequently in almost every examination. This is known as impact of jets. So let me write over here. Impact of liquid jet. Impact of liquid jet. Now before we start talking about this, let me brief you regarding what we are going to find out over here. Imagine a jet of liquid is issued from a particular. Now this jet is striking over a plate. When it strikes a plate, there is going to be some force acting on the plate by the virtue of jet. Our first aim over here will be to identify how much force is acting. After finding out the force, you are going to see if the plate starts to move or if the plate is moving continuously, then because of this force there is some work that has been done. So second aim will be to identify the value of work done. Third thing, you see, work done is a kind of output. For output to be there, you require an input initially. The input over here is the kinetic energy with which the fluid has come out of the nozzle. So mentioning over here is the input energy or kinetic energy. Finally, if you are having input and output, you can talk about efficiency. So finally, efficiency. So let me write down whatever I have mentioned over here. The top act of liquid jet. There is a nozzle over here. Through this nozzle, jet is moving out. A liquid jet is moving out. Now, this liquid jet is mentioned. There are two important things you are supposed to know. Right? First thing you are supposed to know is what liquid is it? In other words, what is the density of this liquid? Second thing you are supposed to know over here regarding this jet, what is a cross-section area? Let's say this cross-section area, capital A, you are supposed to know. Third thing is, what is the velocity of the jet leaving the nozzle? Let us say the velocity is V. So third thing we are supposed to know over here is the value of V. If these three things are defined, then you can say the jet is perfectly defined. Next, let us say in front over here you are having a plate, some plate over here. Now as the jet is going to strike on this plate, let us say it is striking and moving out. Striking and moving out. Now what happens is, there is going to be some force developed. There is going to be some force developed. So over here, the jet is going to create amount of force. So in our to find list, the first thing we are supposed to find out is this value of force. The value of force is equal to how much? Second thing, now there is a possibility of this plate being fixed. It is possible that this plate is fixed. That is one thing. The other thing is probably the plate is free to move. Let us say the plate is free to move. For example, let us say over here this plate is having certain velocity u. Please understand there are two velocities. One is v. V over here is jet velocity. V stands for jet velocity. And u over here stands for plate velocity. U stands for plate velocity. Now if the plate is allowed to move with the velocity u, let us say a velocity u over here, then what is happening? Because of this force, there is some motion taking place. Now we know that force times displacement in the same direction will give you work. But please find out, look over here, we are not having displacement given. We are rather having velocity given over here. So now, second thing we are going to find out over here, second thing is, it is not going to be work, it is rather work per unit time. So second thing over here is work per unit time. Work per unit time is also called as power. Work per unit time is also called as power. So second thing we are supposed to find out over here is the value of power. And what shall be the formula for power? The formula for power over here is supposed to be equal to. Now we know that work is equal to force into displacement. Therefore power should be force into displacement per time or velocity. Therefore force multiplied to velocity. This is going to be the formula for power. Now before I go any further, let me tell you one more important thing regarding this power. You see, work is a scalar quantity and its product or its value is equal to F dot S. That means you are taking force and displacement both in the same direction, dot product. Something similar you have to do over here. You are supposed to see to it that the force and velocity you have chosen, both should be in the same direction. Imagine if they are in two different directions, then you have to convert one thing into the direction of other by component. Anyway, after having seen this, I am going to treat this power as my output. So treat this as output. I told you there is no possibility of output without an input. The question now is, who is behaving as an input over here, or what is behaving as input over here? You see, when the fluid came out of this nozzle, it came out with some kinetic energy. That kinetic energy is the input to the system. So third thing I'm going to mention over here is kinetic energy per unit time. Kinetic energy per unit time, and you are going to treat this as your input. You are going to treat this as input. What will be the formula of kinetic energy per unit time? Now recall, the formula for kinetic energy itself is half mv square. Per time means you are going to take half m dot v square. So this is going to be equal to half into m dot into v square. This is a third formula we are having. After having found this, finally, fourth thing, easiest thing actually. Why easy? Because the moment you see an input and output, you are supposed to instinctively get that the next thing we'll speak about is efficiency. So final thing over here is the concept of efficiency. I represent by eta, efficiency, and the value of efficiency is supposed to be equal to how much? Output upon input, that is work per unit time, upon kinetic energy per unit time. This will be the value of your efficiency. So this is what you are supposed to identify once you are having a problem based on impact of jets. Now it is not necessary that all the four things are asked. It is not necessary. He can ask you only regarding the value of force. Let us say you are having a 1 mark question, a simple question coming in, where he is asking you only the value of force. Sometimes he might ask you what is the value of power. Sometimes he can go on till asking you what is the value of efficiency. So anything can be asked, but I would recommend you, whenever you solve any question for practice, go on for all these four things. That will be sufficient practice for you. After having seen this, what is the next thing we are supposed to do? The next thing is, for solving these problems, there will be some assumptions required. So next thing we are doing over here is talking about the assumptions required. So now let us speak about the assumptions required in the concept of impact of jets. Assumptions in the concept of impact of liquid jet. Now what assumptions will we have? I am going to discuss over here three assumptions, very simple assumptions. Let us talk about the first assumption, the first one. Imagine you have over here a nozzle, and this nozzle is issuing a jet of liquid, a horizontal jet of liquid. When it is issuing a horizontal jet of liquid, and think about it, you're having gravitational acceleration on Earth. By the virtue of gravitational acceleration of Earth, what is going to happen? Eventually, this will keep on sagging down. This jet keeps on sagging down. We have talked about projectile motion previously in the concept of free liquid jet. Over there also what happens? A parabolic trajectory is developed. Something similar will be taking place over here. Let us say initially the plate was over here. It could strike the plate. The plate went forward. After some time, the jet is going to lose contact with the plate. So there is no possibility of impact of jet taking place over here. In order to overcome this problem, we are making an assumption. Now these assumptions might seem unreasonable, but they are important. The first assumption is we neglect gravity in horizontal jets. Please remember, we are not always neglecting gravity, we are only neglecting gravity in the case of horizontal jets, only in the case of horizontal jets. Now I told you, these assumptions will look unreasonable, they will look not true, but then we have to accept them the way they are. This is the first assumption we are having. Second assumption now. Second assumption. Now you see, again, let us say I am having a nozzle. There is a particular plate over here. The jet is striking and moving out. Jet is striking and moving out. The question over here is, how is the jet going to exit? Because we know that when a jet strikes any surface, there is going to be a splash back taking place. Some amount of fluid will be splashing back. Is it not? We have seen this happening practically. We do not know what percentage or what portion of liquid is splashing back. Therefore, we make an assumption over here that there is no splashing back whatsoever. We assume that the jet will move perfectly tangential with respect to the surface. There is no flow taking place in this tangential direction whatsoever. So second assumption is exit of the jet after striking is tangential to the surface. Tangential to the surface. Exit of the jet after striking is going to be tangential to the surface. Again, this doesn't happen. We assume it is happening. That is why they are called as assumptions. Third assumption and the final assumption. What is the third assumption? Now, let us say the jet is striking over here with a certain velocity. The jet is striking over here with, let us say, 10 meters per second. After striking over here with a certain amount of velocity, when the fluid particle is changing its path and moving this way, it is going to observe some friction along the surface of the plate, is it not? Let us say it is striking like this and moving tangentially over here. Since it is moving tangentially, there is going to be shearing taking place, some frictional force will be created. So what should happen? The exit velocities over here are supposed to be less than 10. Now, in general, we do not know what is the friction taking place over here. Since we do not know what is the friction taking place over here, I hope you have guessed what is the third assumption. The third assumption over here is we neglect friction. So third assumption is neglect friction along the plate's surface, Now what happens if you neglect the friction along the plate surface? Then whatever is the velocity with which the jet is striking on the plate, with the same velocity the jet is supposed to exit also. So I can say that the implied meaning of this thing is, implied meaning over here is the velocity at exit after striking is, after striking is equal to the velocity of striking. Is equal to the velocity of striking. So these are the three assumptions you should bear in your mind while solving questions based on impact of jets. The first assumption, neglect gravity only in the case of horizontal jets. Please remember this thing. Second assumption, the exit is supposed to be perfectly tangential. Third assumption, no friction. If there is no friction, whatever is the velocity with which the jet is striking on the plate, the jet is supposed to exit also with the same velocity. Now, after having seen these three assumptions, let me take a very important case for solving questions on impact of jets. Once we finish this case, you will be good to solve any question based on impact of jets. This case is very important, and I have seen many times people find impact of jets difficult only because they don't understand this case. Let us see. Imagine there is a nozzle. A jet is coming out from here. It is issued out from here. There is a plate over here. The jet is striking on this plate. Over here. Let us say the plate is allowed to move forward with certain velocity u. The plate is having velocity u. I already mentioned to you that the jet velocity is represented by v. I'll be representing jet velocity by v. Let us say crossing area is a, density is rho. Fine. Now I'm going to ask you two things. One is velocity, one more thing is mass flux. Okay. While looking at this video, imagine that you are sitting in a class and try answer questions, please. It will be helpful for you. Let us say I take a section over here, this section, just after the fluid has left the nozzle. At this section, if I ask you, what is the velocity of the jet? The issued velocity basically. You will of course answer, this is equal to v. Let me ask you, what is the mass flux over here issued? How much mass flux of liquid is issued at that particular point? The mass flux issued is equal to how much? Rho A V. I hope there is no difficulty in answering this thing. The velocity issued is equal to V, mass issued is equal to rho AV. Now let me concentrate at this particular point. Let me call this point as striking point. So if I ask you, what is the velocity striking? How much velocity is striking over here? If I ask you this question, can you answer me? Imagine that the jet is running with V, plane is running with U. What is the velocity with which he is going to catch up? With which he is going to strike? The velocity now is supposed to be relative velocity. Therefore, the velocity striking is supposed to be equal to V minus U. Next thing, come to mass flux striking. M dot striking is equal to how much? How much is the mass flux striking over here? Now you'd answer me. Mass flux striking over here is equal to rho into A into, yes please, what would the value be? Rho into A into V or rho into A into V minus U? I hope you're getting this is V minus U. Now till here, I believe everything is clear. Now what I'm going to do is, I'm going to slightly complicate this by a very important case which has given birth to the concept of turbines. And that case is, imagine that you are having a wheel. To this wheel, you are having a number of plates mounted. The number of plates, of course, will be many. For the sake of understanding, I am showing you 4 over here. And let us say this is moving with a velocity u when a jet has struck over here. When a jet has struck over here, let us say the jet is exiting from a nozzle. Something like this. Let us say the velocity over here is equal to V, and of course u is the velocity of what do you call the plate over there. So you're having multiple plates over here. Now again, I'm going to ask you same question. It is for this point. First of all, the first question is, what velocity issued over here equal to? What is the mass flux issued over here equal to? The second set is over here at the striking point. What is the velocity striking equal to? And what is the mass flux striking equal to? Mass flux striking equal to. Let us start with velocity issued. Velocity issued, not a big deal. You can say it is equal to V. Fine. Mass flux issued over here, again very easy. It is equal to rho A V. Now come to this point. What is the velocity with which the jet is striking? The velocity of striking again is a relative velocity that is equal to V minus U. Next question. What is the mass flux striking over here? Now when you talk about the mass flux striking over here, if you are getting rho A into V minus U, then let me tell you, you are mistaken. That is wrong. The value is not rho A into V minus U, the value is equal to rho A V only. In this particular case, the mass flux issued and mass flux striking, both of them are going to be equal to each other. Now this might be a problem to you. Let us now discuss why this is happening, and this is where people many times do mistakes. First thing, I want you to come to conclusion that mass flux striking need not be understood from velocity striking, because if you take the idea of velocity striking, again you would get over here V minus U, is it not? You would get over here V minus U. But I'm not having V minus U, I'm rather having rho AV only. So first thing you have to understand over here is velocity striking need not influence mass flux striking. Chaliye, let us see why all these things are happening. Let us come back to the first case. Come back to the first case. This is correct. Mass flux striking is rho A into V minus U. Why is it so? Please try to understand this. This might be slightly tricky. You see, initially I'm having the plate over here. At this position I'm having the plate. Let us say next instant the plate moves forward by distance. Next instant, let us say the plate has moved forward till here. Now this distance over here is equal to u. So plate has moved forward by a distance u. Fine. Now what happens when the mass flux starts from here and moves forward? When it reaches at this particular point, it is not finding the plate. Since it is not finding the plate, what happens now is, the jet length is supposed to increase. The jet length was only till here. Now the jet length increases and moves forward till here. The jet length has increased by how much distance? It has increased by a distance equal to u. When the jet length increases, every instant it is increasing by a distance u. Let us say next instant, again the plate has moved forward. The plate is right now over here. So what would happen? Next instant again, the jet length would have to increase itself. Let us say jet length is increasing itself. Again it is increasing by what magnitude? It is increasing by a jet length equal to u. Is it not? So every instant the jet length is increasing. So now I can say that there are three mass flux. There is one mass flux which is m dot issued mass flux is there. The value of mass flux issued is rho A into V. Second thing, there is some amount of mass flux which is consumed in increasing jet length. So let us say I am having some m dot which is consumed in increasing jet length. I am writing in short form, please understand. Which is used up in increasing or changing jet length. Need not be increasing always, but changing jet length, let us say. So there is some mass flux used in changing jet length. How much is this mass flux equal to? It is equal to rho into A into whatever is the velocity of the plate, same is the value by which jet length is changing. So rho into A into U. I hope you are following this thing. Are you following? So rho into A into U. Now the question is, how much is the mass flux striking? What is the value of mass flux striking over here? Mass flux striking should be equal to issued mass flux minus mass flux consumed in changing jet length. So it is supposed to be equal to m dot issued minus m dot consumed in changing jet length. Therefore, this value has to be equal to rho AV minus rho AU. Therefore, this value becomes equal to rho A into V minus U. Are you following this? Please don't think that since velocity striking was having V minus U, therefore m dot striking is also having V minus U. That would be wrong understanding. Even though the result over here is correct, but understanding would be wrong. The actual understanding is whenever the jet length changes, some amount of mass flux is consumed in changing jet length. Because of that, the mass flux striking is going to change now. Now, after having understood this, come over here. Come over here. I told you there are many plates over here. I might have not shown sufficient enough, but please imagine there are many plates to this thing. Over here, as the rotor moves, let us say it is rotating. Please create this idea in your mind. As it moves, let us say this, which is marked 1, 2, 3, 4 and so on. 1 has gone over here. The moment 1 goes over there, 2 will take its position. If 2 has taken this position, tell me, is there going to be any change in jet length? No. if the jet length is not changing, then tell me, is there any mass flux consumed in changing jet length? No. Whatever is the mass flux issued, entire mass flux is able to strike over here. It might not be able to strike the same plate every time, but it is still striking the plate. Are you following this thing? So whenever jet length does not change, that time you are going to say mass flux striking a plate is supposed to be equal to mass flux issued itself. When jet length changes with respect to time, that time mass flux striking should be corresponding to velocity relative. Let us now take the cases, various cases in impact of jets. Let us start with the first one. The first one we are going to start with is horizontal jet striking normally on a flat vertical plate. Flat vertical plate. This is the most basic of all cases. Let us say I am having a jet over here which is coming out of a nozzle. Suppose this is a nozzle, jet of liquid is coming out. You are having a plate over here, the jet is striking and then moving out tangentially. Let us define some things. The cross section area over here is equal to capital A. Velocity of jet, I have mentioned already, it is represented by V. Density is rho. The plate itself is moving forward with a velocity equal to u. Now we are going to find out all the four things. I hope you remember. We started with force, then power, then kinetic energy per second, then efficiency. Before I do that, let me draw the control volume, and I am going to draw the control volume for this much of region. So I can draw this as let us say this is my control volume. I can say this is my initial section, and this is my final section. These two are the same, they are the final section. Now through the initial section, how much is the velocity? I am having? The velocity of striking over here is supposed to be equal to how much? It is supposed to be equal to the relative velocity, which is V minus u. Whatever is the velocity at entry, same should be the velocity at exit. So this is equal to V minus u. This again is equal to V minus u. Next thing, the fluid is going to push the plate with certain force F. The plate is getting back the push over here. So I can write there is going to be certain amount of force over here. That force is completely in x. So let me write it as Fx. Fx is a force. This is my control volume diagram. Very simple diagram. Now we are going to have the equation written. Let me do one thing. Let me drag this further. let us now write down the equation of force. I can write the equation of force by summation of force in x has to be equal to delta m dot into velocity in x. Now this is also equal to m dot into velocity in x final. Final basically means section 2 over here minus m dot into velocity in x initial. Initial means section 1. So this is my net force. If you look at this entire diagram of control volume, you are seeing that there is no pressure force involved because everything is exposed to atmosphere. Since everything is exposed to atmosphere, my net force itself is equal to minus F. The reason being, I have taken the convention over here, this as positive X and this as positive Y. So now since the force Fx is in negative direction, I am writing minus F. Let me write minus Fx otherwise is equal to m dot into velocity in x at section 2. If you look at both these section 2 over here, I see that the net velocity is purely in y axis. So therefore this value has to be equal to 0. It has to be equal to 0 minus m dot velocity in x initial, that is section 1, it is equal to v minus u. So now I can say that this vanishes off. So from here I am having Fx is equal to m dot multiplied to v minus u. Now the question is, what is the value of m dot? Please answer me. M dot over here is equal to how much? Is it equal to rho a into v, or it is equal to rho a into v minus u? Which one is correct? The answer is rho a into v minus u. The reason being, jet length is going to keep on changing over here. The plate will keep moving forward, jet length will keep on changing. So therefore I am going to write in place of m dot rho a into v minus u, this is my m dot, multiplied again to v minus u. Therefore the value of force, that is the first thing we are supposed to find out, the value of force Fx has to be equal to rho a into v minus u whole square. This is my first equation. Let me save it as equation number 1. Now you see, in general it will be this equation that will take some time to find out. Once you have found this out, rest everything will follow very easily. The second thing I am going to find out over here, after having found out the value of force, is the equation of power. Equation of power, or you can say power or work per unit time. Equation of power or work per unit time. Now we know that the equation of power or work per unit time is equal to F multiplied to velocity. But I told you previously also, and again I am stressing this, you are supposed to take force and the velocity of plate both in the same direction. I see that force is in x, velocity of the plate also is in x. Fine. So Fx times u. Therefore the value of power has to be equal to Fx, we know, is equal to rho a into v minus u whole square times u. So let me rewrite this and highlight it. The value of power or work per unit time Some books also mention it as work per second. Okay, don't get confused. Work per second is as good as work per unit time. This value is equal to rho A into V minus U whole square times U. Let me highlight this as equation number 2. This is our equation number 2. Now, I told you that whenever you find this out, you are going to treat this as your output. This is as good as output for us. If it is output, our next aim is to identify the value of input. So let us say the input value now, the input value, that is kinetic energy per unit time, kinetic energy per unit time. How much is this going to be equal to? How to find out the value of kinetic energy per unit time? We have already mentioned that kinetic energy per unit time is equal to half into m dot into v square. Now one very important question, okay, and that is, what is m dot over here? Is it mass flux issued or mass flux striking? Or striking, think over it. This is input. Input basically means something which is just given from the nozzle. Okay, so in this case, let me go back to the diagram if you are finding any difficulty. Now, if you look here, this is the position we are looking for input. Input. Output is over here. This is the position of output, let us say. If you want to understand like this, you can even take this as input position and this as output position. So tell me, when we are looking at kinetic energy per unit time, are we looking for mass flux issued or mass flux striking? We are looking over here at mass flux issued, is it not? And that is always going to be rho A into V, regardless of whether jet length is changing or not changing. So over here, this is equal to rho AV multiplied to V square. Therefore, kinetic energy per unit time, kinetic energy per unit time over here is equal to half into rho A into V cube. This is the value of kinetic energy per unit time. This is as good as input for me. Let me save this as some equation number 3. So this was my input. Finally, we are going to find out the value of efficiency. Efficiency is supposed to be out upon input. Fine. So let us write down next thing. Fourth thing, efficiency. Efficiency. This efficiency over here is equal to output is work per unit time, input is kinetic energy per unit time, kinetic energy per unit time. So the value of efficiency, the value of efficiency has to be equal to work per unit time. What was equal to rho A into V minus U whole square times you are having U. Kinetic energy per unit time is equal to half rho A into V cube. This is a value. Now if you simplify this thing, you are supposed to get the value of efficiency as 2 will go on top, 2 times V minus U whole square times U whole divided by V cube. This is the value of efficiency. This is the final equation. I hope you are following. So we have seen four things over here. First was force, work done per second or work done per unit time. Next, kinetic energy per unit time, and P for efficiency. Let us take the second case now. The second case is a horizontal jet, striking on a series of flat plates mounted on a wheel. Let us see. Imagine there is a wheel to this wheel you are having multiple plates let us say a jet of a liquid is issued from a nozzle and again the same story continues. You are having cross section area capital A, velocity of jet V, density rho. Each of these plates is moving with a tangential velocity u. This is rotating over here. Fine. Now again we are supposed to find out the value of efficiency. So for that we are supposed to draw the control volume first of all. Again the control volume I am choosing is in this region. It is in this region I am choosing the control volume. Let us see. I am going to have control volume something like this. This let us say is a control volume. The input velocity again is going to be equal to the relative velocity, which is equal to V minus U. The velocity at the exit is also going to be equal to V minus U and V minus U. And the force over here is going to be Fx. Why am I showing it this way? The reason is the fluid is going to exert the force on the plate. The plate, by the virtue of action-reaction pair, will reply back exactly in the opposite direction. So this is our control volume diagram. Now before I start, let me drag this. Let us see. Now let us write the equation of force in x-axis. The equation of force in x-axis would be summation of force in x is equal to delta m dot into velocity in x-axis. Delta m dot into velocity in x-axis. If you look at the net force in x-axis, it is equal to minus Fx. It is equal to minus Fx, and the value of minus Fx is equal to m dot into velocity in x final minus m dot into velocity in x initial. Now if you look at these final sections, this is final and this is final section, the velocity is completely in y-axis, therefore this value has to be equal to 0. Now what I can do is, I can write over here minus fx has to be equal to minus m dot into velocity in x initial. This is a value. Again, I can cancel off minus on either side. Now the question is, what is the value of m dot over here? M dot over here has to be equal to how much? In this particular case, I hope you all remember that the jet length is not going to change. If one plate moves forward, the other plate is taking its position, therefore jet length remains same. In such a case, whatever is the mass flux issued, same is the mass flux striking. Therefore this value is equal to rho AV. So now what I can do is, I can say Fx is equal to rho AV multiplied to velocity in x initial is equal to V minus U. This is the value of Fx. So what I'll do is, I'll highlight this value. I'll highlight this value, mark it as some equation number 1. This is the value of our force. After getting the value of force, same story repeats again. We are going to find out the value of power. The value of power or work per unit time. Work per unit time. How much is this value equal to? Now we know that the formula for power or work per unit time is equal to force multiplied to velocity in the same direction. We know that the value of force is equal to rho A into V minus U times V times U. So now I can say, I can rewrite this as power is equal to rho AV into V minus U times U. This over here is the equation of power. This is the equation of power. Let us save this as equation number 2. After having found the value of power, next thing we are going to find out is the value of kinetic energy per unit time. Next thing is kinetic energy per unit time. Now this kinetic energy per unit time is having the formula. I can say kinetic energy per time or per second is equal to half m dot into v square. Half m dot v square. We have already discussed regarding this m dot. This m dot is supposed to be the value of absolute mass flux. So therefore kinetic energy per unit time is equal to half into m dot is rho AV multiplied to v square. Therefore the value of kinetic energy per unit time is equal to half rho A V cube. This is the value we have. Let me save this as some equation number 3. Equation number 3. Finally, we are going to talk about efficiency. The final thing is the concept of efficiency. Efficiency. Now we know that efficiency is equal to power upon kinetic energy per unit time. Now you see, if you want percentage, you can multiply with 100. Okay, if I'm not multiplying, don't worry. I'm not finding percentage, I'm just finding the ratio. If you want percentage, multiply by 100. You would get the same thing. Power over here is equal to, if we have just now seen, it is rho AV multiplied to V minus U multiplied to U. Kinetic energy per unit time is half rho A V cube. Rho A V cube. Now, if you look at this value, I can cancel off over here rho AV, excuse me, I can cancel off over here rho AV, and rho AV cancels off, V square is left. Therefore, the value of efficiency now would be equal to, efficiency would be equal to, 2 would go on top, V minus U times U whole divided by V square. This is the value of efficiency. Efficiency. Let me save it as equation 4. So this is the concept of a jet striking on a series of flat plates mounted on a rotating wheel. Fine. Now sometimes what happens, for this particular case, there are some more extra conclusions which are asked in examination. This is a very special case. So it is better if you remember some extra conclusions in this case. And one of those things is the concept, when is the efficiency going to be highest? So that is, we are looking for condition for maximum efficiency. Maximum efficiency. Condition for maximum efficiency. Now you see, this condition for maximum efficiency is going to be present in every case, but we are specifically discussing for this case. Okay. Just now we have seen that the value of efficiency is equal to 2 times V minus U times U whole divided by V square. This is the value of efficiency we are having. Fine. What I am going to do next is, I am going to rewrite it in a particular manner which seems to be easy for me. I see that efficiency over here can be written as 2 times V minus U whole divided by V times U by V, times U by V, or efficiency is equal to 2 times 1 minus U by V times U by V, times U by V. Over here I see that efficiency has now become purely a function. Efficiency has now become purely a function of U upon V. It has become purely a function of U upon V. At this stage what I do is, I define this U by V, I give it a name, I call this U by V as speed ratio. This U by V I am going to represent by phi. I call this U by V as speed ratio. Speed ratio. I am going to call this as speed ratio. If I call this as speed ratio, then the value of efficiency is going to become 2 times 1 minus phi times phi, or efficiency is equal to 2 times phi minus 2 times phi square. This is the value efficiency I'm having. Over here I see that efficiency is purely a function of phi, let us say. It has become purely a function of phi. Fine. If it is a function of phi, I can say that if I want the extremum, maxima or minima, extremum of efficiency, then the value of d efficiency by d phi has to be 0, is it not? So I write over here, for efficiency maximum, the value of d efficiency by d phi has to be equal to 0. Now what is d efficiency by d phi? If you look over here, if I differentiate 2 phi minus 2 phi square, I am going to get over here this value as 2 minus 4 phi, and this has to be equal to 0. If this is equal to 0, from here I get the value of 4 phi is equal to 2, or phi is equal to half. So this is when you are going to have maximum efficiency. What does it mean? If phi equal to half, it means that u by v is equal to half, which means that u is equal to v by 2. That means I can write it in a statement form that for efficiency maximum, the condition is plate velocity should be equal to half of jet velocity. Plate velocity should be equal to half of jet velocity. This is a condition required if you want to have efficiency maximum. Now let us see what is the value of efficiency maximum going to be. Now efficiency maximum will be equal to how much? It will be equal to 2 times, in place of phi I am going to write half, minus 2 times half square. Now that is equal to efficiency maximum is equal to 2 times half is equal to 1 minus 2 times half square. Half square is equal to 1 by 4, so this is going to be equal to 1 by 2, which is equal to half, which means that efficiency maximum in this case has to be equal to 50%. It has to be equal to 50%. This is the value of maximum efficiency that can be attained. And please understand that maximum efficiency does not mean maximum power. Okay, it does not. Maximum fine, I'm sorry, this is the value of maximum efficiency. Fine, let us move forward and do one thing. At last, let us plot the graph over here. Of efficiency versus phi. If you remember, the value of efficiency was equal to 2 phi minus 2 phi square. How would the graph over here look like? First of all, what type of graph is it? It is a parabolic graph. And what are the zeros of this particular graph? The zeros are 0 and 1, is it not? That means at phi equal to 0, I'm going to have efficiency 0. At phi equal to 1, let us say phi equal to somewhere over here. At this point also I'm going to have 0. I'm going to have a parabola over here. So this is phi equal to 0 and this is phi equal to 1. And I'm going to get the maxima. I'm going to get the maxima at phi equal to half. And what is the maximum value over here? The maximum value over here for efficiency maximum is equal to 50%. This is the value of efficiency we are having. With this we conclude the second case. Let us take the case 3 now. The third case is a jet striking normally on a symmetric curved vane. The word vane is generally used whenever you are having a curved plate. So vane is as good as a plate, so don't get confused. Let us see how to take this case now. Imagine there is a nozzle. A nozzle is there. And there's a jet of liquid coming out from this nozzle. A jet of liquid is coming out. You are having over here a symmetric curved vane. Let us say something like this. The jet would go out something like this. Let us say the velocity is over here v, density is rho, cross section area is E. The velocity of this blade or vane, let us say, is equal to u. This is the velocity. Furthermore, if I take tangent over here, then let us say this tangent is making an angle of theta with respect to horizontal. Same thing in this case also, since it is symmetric, I can say that if I take tangent over here as well, I am having the same angle theta over here. Fine. Now, if I draw the control volume diagram, how should the control volume diagram look like? I am going to take this much portion for control volume. So a control volume would look something like this. Let us say something like this is the control volume we have. This is a control volume. The velocity coming in over here is equal to v minus u, and the velocities moving out are supposed to be same. We have discussed why. The velocity is again over here equal to v minus u, and the velocity over here is again equal to v minus u. These are the velocities we are having. Now, if I take the component of velocity in x-axis over here, this component of velocity, if I see, then this component is equal to V minus U, and since this angle is theta, I can write over here cos theta. Similarly, if I take over here, this is again equal to V minus U times cos theta. This is what we have. And again, the fluid is pushing the vane, therefore the vane is going to push back over here. Let us say the vane is pushing back with the velocity, with the force F. Fine. This is a control volume diagram. Let me do one thing. Let me choose this portion and bring it down. Now let us write the equation for summation of force in x-axis. Now if I write over here summation of force in x-axis, then it has to be equal to delta m dot into velocity in x-axis. This is the value we have, delta m dot into velocity in x-axis. If you look at the force is equal to minus F. Minus F has to be equal to m dot into velocity in x final minus m dot into velocity in x initial. This value. Now if you see, the value of m dot is going to remain the same in both the cases. The question is, how much is the value of m dot? We have already discussed that m dot, if the jet length is changing, should be in relative terms, and that value is equal to rho a into V minus U. So now I can say over here minus F is equal to m dot common to velocity in x final minus velocity in x initial, that is equal to, yes, m dot is rho into a into V minus U multiplied to. Now velocity in x final is equal to how much? Now this is slightly tricky, sometimes people do mistake over here. Final section basically means this section and this section. In x-axis, if you see, first of all, it is not positive in x-axis, it is negative in x-axis. Fine, negative. How much is it equal to? Is it equal to V minus U times cos theta, or twice V minus U times cos theta? Now answer me this thing. Is it equal to only single times V minus U cos theta, or you are going to consider V minus U cos theta from here and from here, therefore twice V minus U cos theta? Which one will be the answer? The answer is only once you are going to consider V minus U cos theta. V minus U cos theta, only once. Why is it so? Some of you might think that since the velocity is twice, I am supposed to write twice over here. The reason is, when the mass flux is entering at this particular section, half of that mass flux has gone here, half is going over here. For the entire mass flux, the velocity is only once. I have chosen entire mass flux. For the entire mass flux, the velocity is only once. If I write over here 2 times, then what happens is, what does it mean? It means that that single mass flux is going at twice the speed. It is not happening. It is only getting bifurcated, but every particle is still having velocity only once. That is why I am writing only once over here. Next, I am writing this minus over here. What is the velocity at initial section? If you see, at initial section, it is equal to V minus U. This is the value I am having. This is the value of minus F. Let me cancel off minus throughout. If I cancel off minus throughout, then what I have over here is the force has to be equal to rho into A into V minus U Let us take one more v minus u outside. So v minus u whole square multiplied to 1 plus cos theta. This is the value of force when you are having a jet striking normally on a symmetric curved plate. This is the value of force. So let me save this as some equation number 1. Now at this stage, I want to take a special case. Let us say a special case I am taking. So special case. Imagine that the plate or the vane is exactly a semicircle. So let us say if the vane is semicircular. Now what happens if the vane is semicircular? The value of theta this time becomes equal to 0. This implies the value of theta becomes equal to 0. Exactly semicircle you are having, value of theta becomes equal to 0. So now what is happening? If theta becomes equal to 0, you can say this further implies that the value of cos theta becomes equal to 1. Now put in this cos theta equal to 1 in equation 1, then this equation will now become force is equal to rho into A into V square, rho into A into V minus U whole square times 1 plus 1, that is basically force is equal to 2 times rho A into V minus U whole square. This would be the value. Now recall, when you are having a plate over here, a flat plate over here, and a jet is coming and striking on this. Then and it is moving, let us say, at u, and this is moving at, let us say, v. We have seen the value of force was equal to rho A into V minus U whole square. This was the value of force. Now, if you are having exactly semicircular plate such that the jet comes over here and moves back, exactly moving back. If this is happening, for the same conditions, density, area and velocity conditions, now the answer is going to become 2 times rho A into V minus U whole square. It is exactly twice. So you can say the force is going to become twice provided the fluid is getting deflected exactly by 180 degrees. Fine. Moving further. After having seen this, next thing we are going to talk about is work done per second or power. So let me write over here. So second thing we are going to speak about over here is the concept of power. Let us say power represented by P, or you can also say work per unit time. We know that the formula for power is equal to force into velocity. We have discussed all these things previously also. The value of force, just now we have seen, it was equal to rho into A into V minus U whole square multiplied to 1 plus cos theta, and this is multiplied to velocity u. So I can say ultimately the value of power happens to be equal to, power ultimately is equal to rho A V minus U whole square times U times 1 plus cos theta. So this is the formula for power. This is the formula for power. Let me save it as some equation number 2. Fine. After having seen power, the next thing is for us to look at the value of kinetic energy per unit time. So third thing, let us see kinetic energy per unit time. What is the value of kinetic energy per unit time? We have seen the formula previously also. Kinetic energy per unit time happens to be equal to half m dot into v square. And needless to say that m dot over here has to be m dot striking. Therefore, kinetic energy per unit time is equal to half. M dot striking was equal to rho a v times v square. Therefore, this value has to be equal to half rho a v cube. Now from here I can write down ultimately value of kinetic energy per time is equal to half rho a v cube. This is the formula. Last thing. The last thing over here is the concept of efficiency. We know that the formula for efficiency is equal to power upon kinetic energy per unit time. Power upon kinetic energy per unit time. Therefore, the value of efficiency has to become. Just now we have seen the value of power was equal to rho a v minus u whole square times u into 1 plus cos theta. This was the value of power. And kinetic energy per unit time, just now we have seen, it is equal to half rho a into v cube. I can cancel off over here density and area. So I get the value of efficiency as 2 times v minus u whole square times u into 1 plus cos theta whole divided by v cube. This should be the value of efficiency. This is the value of efficiency. So let us save this as some equation number 4. This is regarding the case where a jet is striking on a symmetric curved plate, and that too the jet is striking normally. Let us take case 4 now. This is a relatively simple case. Let us say a jet is striking tangentially on a fixed curved plate or curved vane. Fixed curved vane. A jet is striking tangentially on a fixed curved vane. Let us see. Imagine there is a curved vane, something like this. Suppose it is fixed over here. It is fixed over here. And let us say a jet of liquid is striking on this curved vein. It is striking over here, and after striking, the jet is moving along the surface and emerging out over here. It is emerging out over here. Fine. Let us say the velocity over here is equal to v. This is the velocity over here. Suppose the angle of inclination, if I take over here the angle of inclination the angle of inclination is equal to theta. So I am going to have over here v cos theta and over here v sin theta. Similarly, let us say the angle of inclination over here is equal to phi. So I have over here v cos of phi, and let us say over here I am having v sin of phi. Fine. These are the velocities I am having. If I draw the control volume diagram, the control volume diagram over here is going to be something like this. Let us say this is a control volume diagram. This is the initial section. At this section I am having a velocity entering in, let us say with v. I have over here v cos theta, and I have over here v sin theta. I have an outgoing velocity over here, which is again supposed to be equal to v. I have over here v cos of phi, and I have over here v sin of phi. And if I look at the forces, let us say the fluid is pushing this curved vein in the right hand side direction, so the vein is giving over here a force, let us say Fx. Next, let us say the fluid is pushing the vein in the downward direction, so the vein is giving it a reaction in the upward direction. Let us say this is Fy. Okay. Next, if I start writing the equation, let us say I am writing it over here. I am writing the equation for summation of force in x. Summation of force in x has to be equal to delta m dot into velocity in x. That means the net force over here is equal to minus Fx. On this control volume, it is minus Fx. It has to be equal to m dot into velocity in x at final section minus m dot into velocity in x at initial section. This is a value. So I have over here minus Fx is equal to, I can take m dot common over here. What is the value of common m dot? It is equal to rho a v. This is the value of m dot, and I have velocity in x final minus velocity in x initial. So I have over here minus Fx is equal to rho a v as it is. Now look at what is the velocity in x final. This over here is the velocity in x final. It is in negative x axis, therefore I am going to write minus v cos phi, minus v cos phi. Next, minus velocity in x initial is equal to how much? Velocity in x initial is this value. It is equal to v cos theta. It is equal to v cos of theta. I can cancel off minus throughout over here. If I cancel off minus throughout, then the value of fx, we are going to get is equal to rho a v square times cos theta plus cos of phi. This is the value of fx we are having. This is the value of fx. Let us save it as some equation number 1. This is equation number 1. Now next we are supposed to talk about summation of force in y, because we are having y component of force also over here. So let us say summation of force in y is equal to delta m dot into velocity in y. Now if you see over here, the net force in y in this diagram I have shown is upward. So I have Fy is equal to m dot into velocity in y final minus m dot into velocity in y initial. So I am having over here Fy is equal to, if I take m dot common, the value I know is equal to rho a multiplied to Fy final is equal to how much? Let me open it over here. Fy final, if you see Fy final, it is equal to v sin phi. Vy final, I'm looking at Vy final, it is equal to v sin phi, and Vy initial is equal to v sin theta. So I can write over here for Vy final, v sin phi minus Vy initial is equal to v sin theta. Now from here I can say the value of Fy is equal to, let us take v common, so it is equal to rho a into v square multiplied to sin phi minus sin theta, sin phi minus sin theta. This is the value of force in y-axis, value of force in y-axis, and this, let us say, is equation number 2. So we are having the value of fx as well as the value of Fy over here. Now let us take a special case. Let us say I push it over here. Suppose if the value of theta is equal to phi. What does it mean when I say theta equal to phi? It means the vane is symmetric. If the value of theta equal to y, that means the vane is symmetric. In such a case, what should be the value of fx? What would the value of x be equal to? Look from there and tell me. The value of fx will now be equal to rho a v square common 2. Now cos theta and cos phi, both of them are same, so I can write cos theta plus cos theta. So the value of fx would now become, 2 times rho a v square into cos theta. 2 times rho a v square into cos theta. And if we look at the value of Fy, the value of Fy would be equal to how much? It would be equal to rho a v square multiplied to sine theta minus sine theta, sine theta minus sine theta. From here I can say the value of Fy would now become equal to Fy would now become equal to 0. So if you are having a symmetric vein, in such a case, results are going to be something like this. Now this was a case of striking tangentially on a curved vein when it is fixed. If the vein is moving, then it becomes slightly more complicated, which you will be seeing in hydraulic machinery in the form of velocity triangles. Let us take case phi now. Case phi. A jet striking on a fixed inclined plate. Let us say a jet is striking on a fixed inclined plate. Imagine that you are having a plate which is something like this. This is a plate, let us say. It is fixed over here. The plate is fixed something like this over here. Suppose a horizontal jet is coming over here and it is striking, and we have discussed already it is going to move out something like this. It is going to move out something like this. Suppose you are having a nozzle over here. A nozzle over here. Again, same story. You are having the velocities over here. The velocity over here is equal to V, density rho, area is capital A. There is no velocity to this plate given over here. Furthermore, since it is inclined, we need to define one more thing. Let us say we take over here a normal direction. This is a normal direction, and this over here is tangential direction. Two directions we have chosen. This is normal direction and this is tangential direction. Suppose this angle over here is equal to theta. So theta also is something which is defined. Now first thing I'm going to do is I'm going to draw the control volume diagram. So if I draw the control volume diagram, let us say the control volume diagram is something like this. Suppose this is the control volume diagram we have. Let us say this is a control volume diagram. The incoming velocity over here is equal to V. The velocities moving out over here are equal to V and V. Velocities moving out are equal to V and V. Now at this point, let me tell you one more thing. Remember that whenever the fluid is going to strike on a surface, the force produced is going to be normal to the surface. So if it is normal to the surface, let us say this entire fluid is pushing the surface in the normal direction down. Therefore, what will happen is there is going to be a force developed over here in the form of reaction. Let us say this force is Fn over here. The force is Fn over here. And this Fn is supposed to have two components. Fn is supposed to have two components. One component is in x-axis other component is in y-axis. Let us say this is fx and this over here is fy. This is fy over here. Now the question is, what are the angles we have? To understand the angles, I am going to spoil this diagram now. Okay, please be with me. To understand the angle, you can say straight away that if normal direction is going to make an angle theta with x, that means I have over here same angle theta. I have over here same angle theta, is it not? If the angle is theta over here, then I can say that this angle over here is equal to 90 degrees minus theta. From here I can say that the value of fx, has to be equal to fn cos theta, and the value of fy is equal to fn sin theta. It is going to be fn sin theta. Now if I want to find out the value of fx and fy, I am supposed to first find out the value of fn. Let us see how to find out the value of fn. Now what I will do is, I will take a direction convention over here. Let us say this direction is positive for normal and this direction is positive for tangential over here. Now I can write that. The value of summation of force, in x, is equal to delta m dot into velocity in x. I'm sorry, I'm not supposed to write for x actually. Excuse me. Let us say the value of summation of force in n has to be equal to delta m dot into velocity in n. Now look over here. Since upward direction of n is positive, I am having upward direction over here, so I can write minus fn is equal to m dot into velocity in n final minus m dot into velocity in n initial. This is what we have. If you look over here, what are the final sections? You observe that this and this over here are the final sections. In both these positions, the velocity is completely tangential. Since velocity is completely tangential, I can cancel this off, because in the final section there is no component of velocity involved. If I cancel this off and I cancel this minus and minus, from here I can write down that the value of fn has to be equal to m dot multiplied to velocity in n initial. M dot multiplied to velocity in n initial. Now the question is, what is the velocity in n initial equal to? Observe over here. This is v. This angle is theta. This is velocity in n initial. The value of velocity in n initial has to be v cos theta, is it not? If it is equal to v cos theta, from here I can say fn is equal to m dot is equal to rho a v times this is equal to v cos theta. From here I can write the value of fn. The value of fn comes out to be equal to rho a v square times cos theta. This is the value of force in normal direction. Once you get the value of force in normal direction, from here you can say that the value of force in x is equal to and the value of force in y is equal to, yes, how much is the value of force in x going to be? Fx is equal to Fn cos theta, therefore its value times cos theta. So it has to be equal to rho a v square times cos square theta. And Fy has to be equal to Fn sin theta, therefore it is equal to rho a v square times cos theta times sin theta. These are the values. So let me save these values. These are the values of Fx and Fy. We are not done still. Now you see over here, once in GATE examination, civil, a question appeared for 2 marks. That question was, if you are having over here a discharge of Q, then obtain the value of Q1 and Q2, in terms of Q and theta. So let me write the question over here. For the same setup, the question is, obtain the values of Q1 and Q2 in terms of Q and theta. So let us say over here you are supposed to find out Q1 and Q2 in terms of Q and theta. This is the question we are having. Let us say I take this control volume diagram for the sake of understanding here. This is the control volume diagram we are having. Now we are supposed to find out the value of, let us say Q over here is Q itself, over here you are having Q1, over here you are having Q2. We are supposed to get the value of Q1 and Q2 in terms of Q and theta. Now before I start this thing, recall that the force acting on any surface is going to be purely normal. If it is going to be purely normal, I can write a note over here. Let us say the note over here is the value of net force in tangential has to be equal to 0 since net force is purely normal to the surface. Net force is normal to the plate. Net force is normal to the plate. Fine. If it is so, I can start writing over here as summation of force in tangential has to be equal to delta m dot into velocity tangential, and it should also be equal to how much? 0. Which implies m dot into velocity tangential final minus m dot into velocity tangential initial has to be equal to 0, which further implies that the value of m dot into velocity tangential final must be equal to m dot into velocity tangential initial. This is the setup we are having right now. I hope you have followed till here. If you have any difficulty, you can pause at this and again view for yourself. Let us move forward. After getting till here, let us look at m dot into velocity in tangential final. By final, I am having two sections. You see, both these sections are final sections. This section over here is positive final and this over here is negative final. So I can say that this can be broken down into two parts. One is for positive part, one is for negative part. What is a positive? The value of m dot at this particular point is equal to, m dot over there is equal to rho into q1. This is the value of m dot over there, and the velocity is equal to v. Fine, rho q1v we are having. Okay. Next thing, I am having this portion, so I am writing minus over here. The value of m dot over here has to be equal to how much? It should be equal to rho q2. Again, velocity is equal to v, so rho q2 into v. So I am done with m dot into velocity tangential final. This has to be equal to m dot initial. M dot initial is complete rho into q. Now the question is, how much is the velocity tangential equal to? Please answer me this thing. Velocity tangential initial is positive and it is equal to v sine theta. So I am having over here v sine theta. It is equal to v sine theta. Now you see what all things can be cancelled off. If you observe over here, I can cancel off rho and v, rho and v, rho and v. If I cancel these things off, then I get an equation from here which says that q1 minus q2 is equal to q sine theta. q1 minus q2 is equal to q sine theta. Let me save it as some equation number 1. If q1 minus q2 is equal to q sine theta, we also have by continuity equation that q1 plus q2 has to be equal to q. This, let us say, is some equation number 2. Now I can say the sum of these two equations is going to give me, both of them cancel off. I have over here 2q1 is equal to q into 1 plus sine theta. From here I can conclude that the value of q1 has to be equal to q by 2 common to 1 plus sine theta. If you put in the value of q1 over here, then you will get the value of q2. The value of q2 happens to be equal to q by 2 into 1 minus sine theta. So this is the result for q1 and q2 as functions of q and sine theta. I hope this is clear to all of you. Let us continue. I am going to take the case which is similar to the previous one, but only thing, this time the plate is allowed to move. So I am having, let us say, an inclined plate over here. It is not fixed. It is allowed to move. Let us say with the velocity u. You have a jet of liquid coming, which is moving away over here. Over here. Suppose there is a nozzle. A nozzle over here. The velocity is v, over there u, density rho, cross section area is a. Again, what I do is I take over here an axis which is normal to the plate, and let us say I mark this angle as angle theta. The angle is equal to angle theta. After all this, I'm supposed to find out the efficiency of the jet. For this purpose, I'm going to start again with control volume diagram. So we know the control volume diagram should be something like this. Let us say this is a control volume diagram we have. The inlet velocity over here is equal to V minus U. The velocity over here again is equal to V minus U, and the velocity over here is again equal to V minus U. Again, let us say the net force acting is normal over here. The net force acting is something like this. This is Fn, and this Fn has two components. One component is Fx, another component is Fy. We have already seen that this angle is supposed to be the angle theta. Fine. This is my initial section. Let us say this is initial section, and these over here are final sections. Fine. Now if I write the equation for summation of force in normal direction, I am going to have summation of force in normal direction has to be equal to delta m dot into velocity in normal direction. Now if you recall, previously also we had taken a sign convention. We have mentioned that this is positive normal and this is positive tangential direction. So from here I can say that the force acting is negative Fn is equal to m dot into velocity in normal final minus m dot into velocity in normal initial. This is the equation we are having over here. Now if you observe, final section is completely tangential, so I can cancel this off again over here. This is cancelled off, and I can also cancel off negative over here and negative over here. From here I get that this implies that the value of normal force has to be equal to m dot into velocity in normal initial. This is the value. Now from here I can say that the value of Fn is equal to. Now the question is, how much is the value of m dot? Again, in this case also, the jet length is keeping on changing, so m dot has to be equal to rho into a into v minus u, and velocity in normal initial is equal to v minus u times, recall this thing, how much is it going to be equal to? This component, excuse me, this component would be equal to how much if this angle is theta? Cos theta, is it not? It is going to be v minus u times cos theta. So I can write over here cos theta, v minus u times cos theta. So from here I obtain that the value of Fn has to be equal to rho into a into v minus u whole square times cos theta. This is the value of Fn I am having. Once I have the value of Fn, then I can write the value of Fx and the value of Fy. The value of Fx, if you see from this diagram, it is equal to Fn cos theta. Therefore, if I write Fx as Fn cos theta, I am going to have rho into A into V minus U whole square cos theta times cos theta is cos square theta, and Fy is equal to Fn sin theta. Therefore, rho into A into V minus U whole square into cos theta into sin theta into sin theta. These are values. After having obtained the values of forces, next thing is we have to look for the value of power. Let us say power. Power is equal to, how much is the question? Let me do one thing. Let me save this as first set of equations. This, let us say, is my first set of equations. Now, regarding the value of power, we recall the formula for power. Power has to be equal to force times velocity. Now, here's a catch. I am having three forces. Which force am I supposed to take? Should I take Fn or Fx or Fy? I should take the force which is in the direction of u. That means I'm supposed to take Fx over here. Fine. If it is so, then the value of power has to be equal to rho into A into V minus U whole square times cos square theta times u. From here I can conclude that the value of power has to be equal to rho A V minus U whole square times u times cos square. Let me save this as some equation number 2. This as equation number 2. Third we have to look for is kinetic energy per unit time. Kinetic energy per unit time. What is the formula for kinetic energy per unit time? We call kinetic energy per unit time has never changed. Its formula is half m dot into v square. M dot over here is which mass flux? Issued mass flux or striking mass flux? It has to be issued mass flux. Therefore, the value of kinetic energy per unit time, kinetic energy per unit time is equal to half m dot is equal to rho AV times v square. Therefore, the value of kinetic energy per unit time is equal to half rho A v cube. Let me save this as some equation number 3. Next, last thing we are having over here is the concept of efficiency. Final equation, fourth one, efficiency. The concept of efficiency. Now, regarding efficiency, we remember that efficiency is equal to power upon kinetic energy per unit time. This is the value of efficiency. So, from here I can say efficiency is equal to power, if you remember, was equal to rho A into V minus U whole square times U times cos square theta upon kinetic energy per unit time is half rho A V cube. This is the value of efficiency. If you simplify this, the value of efficiency would come out to be equal to rho A cancel off, 2 goes on top, so 2 times V minus U whole square times U times cos square theta whole divided by V cube. This is going to be the equation of efficiency. Let us say this is equation 4. With this, we conclude the concept of impact of jets. Let us take some basic questions on momentum equation. You're seeing a question over here, very simple question, no need of a calculator for solving this question. The question says a jet of oil, relative density is 0.8, has an area of 0.02 meters square and a velocity of 10 meters per second. If it strikes a plate normally, the force exerted in newtons is how much? Direct question, can't get any simple. So now we are having over here S is equal to 0.8, which implies density is equal to 800 kg per meter. Fine, this is a given quantity. The cross section area over here is equal to 0.02 meters square, 0.02 meters square. Fine. The velocity v over here is equal to 10 meters per second. 10 meters per second. It is striking on the plate normally. So this is our given data. This is our given data. Now, let us see how to solve this question. We know that a jet of a liquid, it's striking on a stationary plate over here. On a stationary plate. If he is not mentioning the speed of the plate, it means that the plate is stationary. Let us say the cross section area is capital A over here. The velocity is equal to V over here. Now in this case, we know that the value of force has to be equal to rho A V square. This is a formula. So now I can say that the value of force over here has to be equal to density, we know, is equal to 800. So 800 times area is equal to 0.02. So 0.02. Next, velocity is 100. So sorry, velocity is 10. V square has to be equal to 100 over here. Now what I can do is I can cancel both these zeros. I can push this decimal place over here. We are doing without calculator. So 2 times 800. Therefore, the value of force acting has to be equal to 1600 newtons. This is the answer to the question asked. So the answer over here is 1600 newtons. He is asking in newtons, so we will mention in newtons only. Now very simple question. These kind of questions you will be finding in IES papers, you will be finding in SSC JEE papers and all. Okay. Let us look for the next question. The next question is saying a water jet 0.015 meters square in area has a velocity of 15 meters per second. Fine. If this jet impinges normally on a plate which is moving at a velocity of 5 meters per second in the opposite direction of the jet, the force on the plate due to this impact in newtons has to be equal to how much? Let us start with the given data now. Given data. Again, no calculator required for this question. It says the water jet. Water jet means density has to be equal to 1000 kg per meter cube. Cross section area also is given to you. Cross section area over here is equal to 0.015 meter square. Fine. The velocity of the jet is given. We represent velocity of the jet by V. It is equal to 15 meters per second. It is impinging normally on the plate, moving with a velocity of 5 meters per second in the direction opposite to that of the jet. Now you have to draw a diagram now. Let us say this is a plate you are having. You are having a nozzle over here which is issuing a jet. Let us say it is issuing a jet. So jet is moving over here, something like this. We know that the velocity over here is equal to V. But the plate velocity over here is not in the direction of the jet, it is in the direction opposite over here. So U is directed over here. So when I write U, I am supposed to write its magnitude but with a negative sign over here. So negative of how much? It is saying 5 meters. So I'll write 5 meters per second. At this very instant itself, let me tell you what is the value of V minus U. V minus U over here will be using, of course. V minus U has to be equal to how much? It has to be equal to 15 minus of minus 5. That is equal to 20 meters per second. This is the value of V minus U. Now let us move further. After having got this value, now we are supposed to find out the force. We know that the value of force in this particular case is equal to rho into A into V minus U whole square. That is equal to density rho is 1000 over here. Since it is water, area is given to us as 0.015, and V minus U we have already established, it is equal to 20, so 20 square. I can cancel off these 3 zeros, push the decimal place forward. I'm having force is equal to 15 times 20 square is equal to 400. So the value of force comes out to be equal to how much? Excuse me. The value of force comes out to be equal to 6,000 newtons. 6,000 newtons. So this is the answer to the question asked. Now please check whether he is asking in newtons or kilonewtons. Be careful with the units. He is asking in newtons over here. So I can answer it as 6,000. This is the answer to the question asked. Again, a 1 mark question with the IAS examination, or you can say even GATE examination for 1 mark. Look at this question now. It is again where a plate is moving and a jet is striking. The question says a jet of water issuing horizontally from a stationary nozzle with a velocity of 100 meters per second impinges on a vertical plate which is moving away from the jet with a velocity of 50 meters per second away from the jet. If the jet diameter is 0.1, then the force on the plate in kilonewtons is how much? So this time he is asking in kilonewtons. Fine, let us start now. Given data. Let us start with the given data. Jet of water, therefore density is given to us. Density is equal to 1000 kg per meter cube. 1000 kg per meter cube. It is striking horizontally, fine. with a velocity of 100 meters per second. So the value of v over here is equal to 100 meters per second. Fine. Next thing, it is hinging on the plate, on a vertical plate which is moving away. This is important for me. It is moving away. That means the value of u is in this direction only, which is equal to 50 meters per second. 50 meters per second. Fine. The jet diameter is 0.1 meter. So diameter over here, d is equal to 0.1 meters. Fine. The question again is regarding the value of force. Again, I am going to require the value of v minus u. Tell me, what should the value of v minus u over here be equal to? Is it 100 minus 50 or 100 minus 50? It is going to be 100 minus 50 only. 100 minus 50. So therefore the value of v minus u is equal to 50 meters per second. Fine. The value of force we know is equal to rho into a into v minus u whole square. That is equal to 1000 multiplied to area is pi by 4 d square multiplied to v minus u whole square. Now this is equal to 1000 multiplied to pi by 4 times diameter is 0.1, so 0.01. V minus u is 50, therefore 2500. I can cancel this and this off. Now I want the answer in kilonewtons. Therefore, divide this by 1000, so 1000 also cancels off. You are left here with 25 into pi by 4 kilonewtons. This is the value. Now if you calculate 25 into pi by 4, the value comes out to be equal to approximately 19.625 kilonewtons. So the value of force over here is equal to 19.625 kilonewtons. So for the question asked, the answer is 19.625 kilonewtons. Moving further, let us see. I think this question also was quite simple. All the three questions previously were of one kind. Let us see the next question. The next question over here is when a jet is striking and then deflecting by 180 degrees. You see, when a jet is striking and deflecting by 180 degrees, I have mentioned already to you, it is as good as twice of jet striking on a flat plate, is it not? So over here, if someone asks you what is the value of force equal to, then you can say it is equal to 2 into rho a v square, is it not? Let us see the question now. The question says, a jet of water with a uniform velocity of 5 meters per second and cross section area of 10 power minus 4 meters square is deflected by 180 degrees by a stationary semicircular vane. The force exerted by the jet on the vane is equal to how many newtons? Answers are given in newtons. Fine. Let us start. Given data again. Given data. Uniform velocity, a jet of water, so density we know is equal to 1000 kg per meter cube. Fine. It is moving with a velocity of 5 meters per second. So v is equal to 5 meters per second. Cross section area 10 power minus 4. So cross section area is equal to 10 power minus 4 meters square. It is deflected by 180 degrees. Standard case. So therefore I can straight away write the formula. The formula for force over here is equal to 2 times rho A into V square. 2 times rho A V square. Now if I put in the numbers, I am going to have 2 times density is 1000. Area over here is equal to 10 power of minus 4 and V square over here is 25. Now you see, again without calculator I can do this thing. 10 power 3 and 10 power minus 4, 10 power minus 1 is remaining, and 2 times 25 is 50, so this is equal to 50 into 10 power of minus 1. You can cancel 1 0, therefore the value of force comes out to be equal to 5 newtons. So the answer for this question is force has to be equal to 5 newtons. The answer is 5 newtons over here. Now again a simple question, again based on impact of jets. Let us see the next question. Now this question is dealing again with impact of jets, but in this case he is talking about power. Read the question for yourself once. The question says, a jet of water with velocity of 20 meters per second impinges on a single vane at 5 meters per second. The vane is moving at 5 meters per second in the direction of the jet, and it transmits a power equal to P1. Fine. If the same jet drives a series of similar vanes mounted on a wheel, if you remember the case of a jet striking on a series of vanes mounted on a wheel under same velocity conditions. Please read same velocity conditions. Over here, read same velocity conditions. The power transmitted over here is equal to P2. The question asked over here is the ratio of P1 to P2 is how much? Now, what is the formula for power? What is the formula for power when you are having a jet striking on a plate? On a plate, you know, it's normally strike on a plate. The formula is force multiplied to the velocity of the plate, that is u. And we know the force is equal to how much? It is equal to rho A into V minus u whole square. This is multiplied to u. Fine. So the value of P1 has to be equal to this much. I hope for all of you. Coming to the value of P2. Again, P2 has to be equal to force multiplied to u. Only thing, the formula of force is going to change now. The formula for force over here is equal to rho into A into V times V minus u. This is the formula for force. I hope you remember. In the case of series of vanes, the jet length is not changing. We have had a discussion on this thing already. When the jet length does not change, m dot is going to be absolute. I hope you remember this thing. So therefore rho A V multiplied to V minus u and then multiplied to u over here. This is a value of P2. Fine. With this information, now let me write down the ratio of P1 to P2. The ratio of P1 to P2 is equal to how much? I can write this as rho A into V minus u whole square times u whole divided by rho A into V times V minus u times u. This is the value. Let us see what all can be cancelled. Rho A can be cancelled. V minus u and V minus u can be cancelled. U and u can be cancelled. So now we are remaining over here with P1 by P2 is equal to V minus u whole divided by V. This is the value we are getting, V minus U whole divided by V. Now let me see what are the values of V and U given. The value of V is given as 20. The value of U is given as 5. Fine. In such a case, I can say P1 upon P2 has to be equal to 20 minus 5 whole divided by 20. 20 minus 5 is 15. 15 by 20 you are getting over here. This is equal to 15 upon 20. 3 by 4 or 0.75. So the value is equal to 0.75. The ratio is 0.75. From here I can say the answer is option D, 0.75. Okay. Now again, in examinations you will be coming across many questions dealing with impact of jets. So it is important for you to go through the formulas. If you read them twice or thrice, these formulas you don't have to remember them. They will eventually come whenever required. Don't worry. Let us look at the next case. This is a good question. The question is talking about a reducing elbow. Read the question for yourself once. The question says a reducing elbow is used to deflect water upward by 30 degrees as shown in the figure. The mass flow rate at the inlet is equal to 14 kg per second. Water is entering at a gauge pressure of 200 kilopascal and exits to atmosphere. Exits to atmosphere, please highlight in your brain, it is important phase, because exiting to atmosphere implies that the value of pressure over there has to be equal to 0. Further, the cross-sectional area is 113 centimeter square at inlet and 7 centimeter square at exit. Density of water and acceleration of gravity are taken as 1000 kg per meter cube and 10 meters per second square respectively. Magnitude of X component of water force on the elbow in newtons is equal to how much? Now if X component is not clear to you, this is X, this is Y. He is asking you how much is the X component of force acting on the elbow. This is a question. The question is quite direct, but it is going to be slightly lengthy compared to the previous questions. Whenever you have these kind of questions, I would suggest you to start with control volume diagram. Let us say the control volume diagram is going to be the diagram what we have itself, only with some extra information we are going to mention. Let us say suppose this over here is a control volume. Now whatever is the force exerted by the fluid on the elbow, if the elbow was having some support over here, imagine the elbow was having some kind of a support over here. If the elbow has a support over here, same amount of reaction you would get. So let us say whatever is the reaction, same is the amount of force. So let me say in horizontal the reaction is equal to R. Now next thing, I have to look at all the forces and the velocities. The first force over here is the pressure force, that is equal to P1 times A1. Now good thing that P1 and A1 both of them are given to you. The second force is the pressure force at the section 2. Let me take this as section 1 and this as section 2. Over here again compressive force you are going to have, which is equal to P2 times A2. Now I make it a habit of mentioning this even though it is equal to 0, because conceptually it is present. Value wise it might be 0. Why is its value equal to 0? What phrase over here is telling you that the value of P2A2 is 0? The phrase is the fluid is exiting to atmosphere. If it exits to atmosphere, P2 is 0, Therefore, this entire thing happens to be equal to 0. Now, he is not mentioning anything about the weight of the fluid. Mind you, if he mentions anything regarding the weight of fluid, you are supposed to even show the weight of fluid. But anyway, that is not going to create any disturbance in x-axis. Forget about that. Next thing, I am supposed to talk about velocities. Let us say the velocity over here is equal to v1 and velocity over here is equal to v2. Velocity over here is v2. This velocity in x is going to have a component. Now see over here, this angle is mentioned as 30 degrees. Therefore, the component of v2 over here has to be equal to v2 cos 30 degrees. v2 cos 30 degrees is the velocity at section 2 in x-axis. Fine. This is my control volume diagram. I've always maintained that control volume diagram is like your free body diagram. So once you see control volume diagram, you should not have any need of going back to the diagram initially given to you. That itself is sufficient to solve the question. Now let us see what all things are given to you and what all things you are supposed to find out. The value of P1 is given to me. The value of P1 is given to me. It is equal to 200 kilopascal. That is equal to 2 into 10 power of 5 Pascal. Fine. P1 is given to me. The value of A1 also is given to me. That is equal to 113 centimeter square. 113 centimeter square, or that is equal to 0.0113 meter square. SI units, important. The value of A2 is given to me. That is equal to 7 centimeter square. That is equal to 0.0007 meter square. ठीक है. Density of water is given to me as 1000 kg per meter cube. If it is not mentioned, still you are supposed to take the same. Acceleration due to gravity, even though it won't be required probably over here, I feel so it won't be required, but still let us mention, since he has mentioned, meter per second square. One more important data is given, and that is regarding the value of mass flux entering. The value of mass flux entering over here is equal to 14 kg per second. So mass flux entering over here, that is m dot is equal to 14 kg per second. All this is given. What we do not know over here are the values of V1 and V2. I would suggest first find out the values of V1 and V2, then we can start solving the question. We know that whenever it is a matter of momentum equation, velocities also are important. Let us see. V1. V1 has to be equal to m dot upon density into A. This should be the value of V1, because m dot we know is rho into A1 into V1. So therefore V1 is this much. That is equal to m dot over here is 14 upon density over here is equal to 1000, and A1 is equal to how much? 0.0113. This value of V1 comes out to be equal to 1.238 meters. Okay. This is the value of V1. Now let me save it as some equation 1. This is some equation now. Next thing, I have to get the value of V2. Similarly, I can say V2 has to be equal to m dot upon rho into A2. This is the value of V2, which is equal to m dot is again 14 upon density is equal to 1000, and A2 over here is 0.00 0007. Fine. I can cancel of these things. It jumps over here. 14 by 0.7 is 20. So therefore the value of V2 has to be equal to 20 meters per second. Let me say this as some equation 2. Fine. After getting all these things, it is just a matter of writing the equation of force. I can write over here summation of force in x has to be equal to m dot into velocity in x final minus m dot into velocity in x initial. This is the equation I'm having. Now, what are the various forces acting in x-axis? Please observe over here. You have to carry this forward to the next slide. The various forces acting in x-axis. Let us say this is my positive x-axis. Positive x-axis. I am having P1A1 acting in positive, R acting in negative x-axis. We have already established that this force has to be 0, so its component in x also will be 0. So in x-axis I only have to write P1A1 minus R. So let me write over here. So I am having P1A1 minus R is equal to m dot I can take common, so m dot common to velocity in x final section. Velocity in x was equal to, if you remember, V2 cos 30. It was equal to V2 cos 30 degrees minus velocity in x initial is equal to, it is equal to V1 itself. It is equal to V1. Now we want over here the value of R, so I can say R is equal to P1A1 minus m dot into V2 cos 30 minus V1. This is the value of R. Now put in the numbers. Let us calculate. The value of P1 was equal to 2 into 10 power of 5, and A1 is equal to 113 centimeters, so 0.0113. This is P1A1, fine, minus 14 is the value of m dot, multiplied to V2 cos 30. V2 over here is equal to 20, cos 30 is root 3 by 2 minus V1. The value of V1 is equal to 1.238. Fine. If you calculate this value, this is going to be equal to 2260 minus 14 times 10 root 3 minus 1.283 is going to be equal to 16.08. This is equal to 2260 minus 225. The value of force comes out to be equal to 2035 newtons. So the answer for this question is 2035 newtons. Now this question is worthy of 2 marks in GATE examination. It is not a difficult question though, but still you were having to do some work on this. So the answer for this question is 2035 newtons. This is the answer. Again, I am stressing on this. Whenever you come across questions like these, please start with a free body diagram of our subject, and that is control volume diagram. Moving further to the next question in this set is an assertion reasoning question. Very simple assertion reasoning question. Please read the question yourself. The question says, statement 1, if a frictionless incompressible fluid flows steadily through a convergent nozzle area decreasing, then its momentum must increase. So let us say you are having a convergent nozzle, the fluid is moving forward over here. Fine. As the fluid is moving, he is saying the momentum must increase. Let us see momentum, will it increase or not? Over here, momentum has to be equal to m dot into v1, let us say. Over here, it has to be equal to m dot into v2, let us say over here. The value of m dot by the virtue of continuity equation has to be same. So m dot is same. Now, which velocity is greater, v1 or v2? Of course, the velocity v2 over here is greater. Since the velocity v2 is greater, since v2 greater than v1, I can say m dot v2 greater than m dot v1. Fine. So statement 1 over here is the correct statement. I can see statement 1 is correct over here. Look at statement 2. What does it say? It says that fluid velocity increases in the direction of the flow. Yes, we are observing over here, we have already mentioned fluid velocity is increasing the direction of the flow. That means even statement 2 is correct. Now you look over here, is statement 2 the reason behind the correctness of statement 1? Yes, we could conclude statement 1 is correct only when we understood that statement 2 is correct. So therefore there is a reasoning effect also over here. If all these three things are correct, that means statement 1, statement 2 is correct, and statement 2 is a reason for statement 1 to be correct, then I can say the answer over here is option. This was a very simple question, but still you have to establish reasoning effect also.